Chapter 19. The hydrogen atom and hydrogenic ions. Section 19.1. The Schrödinger equation of the hydrogen atom. In the hydrogen atom, there's one proton and one electron. The energy of the electron is the sum of its kinetic energy and the attraction it feels from the proton. In general, the interaction between two charges Q1 and Q2 is Q1 times Q2 over 4 pi epsilon r. R is the distance between the two charges. Therefore, the attraction the electron feels from the proton in the hydrogen atom is negative E squared over 4 pi epsilon r. We have a negative sign here because the charges of the proton and the electron are opposite to each other. R is the distance between the electron and the proton. R is the magnitude of this vector. The physical constant epsilon 0 is the vacuum permittivity or permittivity of free space over here. Epsilon 0 is 8.85 times 10 to the power of negative 12 farads per meter. The unit farad is the SI-derived unit of electrical capacitance, and each farad is equal to 1 ampere second over volt, or 1 coulomb over volt, or 1 joule over volt squared, or coulomb squared over joule. 1 joule is equal to 1 coulomb times 1 volt. Now the Coulomb constant is defined to be 1 over 4 pi epsilon 0, which is roughly 9 times 10 to the power of 9 joule meter per coulomb squared. So if you have a coulomb charges over here, another coulomb charges 1 meter away, well, the potential energy between this two coulomb charges, 1 coulomb on each side, is roughly 9 times 10 to the power of 9 joule. The kinetic energy operator of the electron is written as negative h bar squared over 2me times the Laplacian operator. The Laplacian operator is the second derivatives with respect to x, y, and z direction for a three-dimensional system. When we have a one-dimensional system, the Laplacian is simply delta squared over delta x squared. Now let's look at the three-dimensional system. We can use x, y, and z to specify the location or position of the electron. For example, here, assuming the center is the proton. But also, we can use the r, theta, and phi polar spherical coordinates to specify the position of the electron relative to the center, which is the proton. In this case, z is r times cosine theta, and x is r sine theta cosine phi, y is r sine theta sine phi. Also, we can express r, phi, and theta in terms of x, y, and z. R is the square root of x squared plus y squared plus z squared. Tangent phi is y over x. Tangent theta is the square root of x squared plus y squared over z. R is from 0 to infinity. Theta is between 0 and pi. Theta corresponds to the latitude of Earth. Phi can be from 0 to 2 pi. Phi corresponds to the longitude of Earth. In Cartesian coordinates, we have the Laplacian equals delta squared over delta x squared plus delta squared over delta y squared plus delta squared over delta z squared. However, if we simply use the Cartesian coordinates to solve the Schrödinger equation for the hydrogen atom, we'll get nowhere. We have to resort to the spherical polar coordinates. In spherical polar coordinates, we have the Laplacian expressed as this: 1 over r squared times the sum of the three terms. The first term is delta over delta r of r squared delta delta r. The second term is 1 over sine theta delta over delta theta of sine theta times delta over delta theta. The last one is 1 over sine theta squared delta squared over delta phi squared. It looks more complicated, but we have to use the Laplacian in spherical polar coordinates to solve the Schrödinger equation for the hydrogen atom. We can see the derivation from the Laplacian in Cartesian coordinates to the Laplacian in spherical polar coordinates in Appendix B. The kinetic energy of the nucleus is much smaller than that of the electron. This is because the total momentum of the two interacting particles, including the electron and the nucleus, must be conserved when there is no external force. So when we study just the hydrogen atom, well, the center of mass of the hydrogen atom is stationary, and we have me times ve equals mp times vp with the negative sign here. So over here we have the momentum of the electron. Over here we have the momentum of the proton. They should be opposite to each other. We can square both sides. We get me ve squared equals mp vp squared. And now, because the mass of a proton is 1800 times that of the electron, we have this equation. So me ve squared over 2me is about 1800 times mp vp squared over 2mp. Now look, me ve squared equals mp vp squared. And over here we have the kinetic energy of the electron. Over here we have the kinetic energy of the proton. So now you can see from this equation, the kinetic energy of the electron is 1800 times the kinetic energy of the proton. Therefore, the kinetic energy of the nucleus, in this case for the hydrogen atom, it's a proton, can be neglected only because the kinetic energy of the nucleus is always much smaller than the kinetic energy of the electrons. Now the Schrödinger equation can be approximated to include only the kinetic energy of the electron here and the attraction, the electron fields. The kinetic energy operator is negative h bar squared over 2me times Laplacian. The potential energy is the attraction, the electron fields from the proton, which is negative e squared over 4 pi epsilon 0 times r. And we apply this Hamiltonian to psi, h psi equals e psi. This Laplacian in Cartesian coordinates is the sum of the three second derivatives with respect to x, y, and z, but in polar spherical coordinates, the Laplacian is more complex. It's 1 over r squared, and then delta over delta r squared, delta over delta r, plus the second term, 1 over sine theta, delta over delta theta, sine theta times delta over delta theta plus 1 over sine theta squared, delta squared over delta phi squared. The derivation from the Cartesian coordinates to the polar coordinates can be found in Appendix P. X is r times sine theta times cosine phi, y is r times sine theta times sine phi, and z is r times cosine theta. Chapter 19. The hydrogen atom and hydrogenic ions. Section 19.2. The wave functions of the hydrogen atom. The kinetic energy of the nucleus being neglected, the Schrödinger equation of the hydrogen atom is approximately h psi equals e psi, where h is the kinetic energy operator of the electron and the attraction felt by the electron. This is the Laplacian operator, which is the sum of the second derivatives in the x, y, and z direction. This Laplacian can be expressed in the polar spherical coordinates r, theta, and phi. It's impossible to solve the Schrödinger equation if we use the x, y, z coordinates, because we have this 1 over r on the bottom over here, and this 1 over r is equal to 1 over the square root of x squared plus y squared plus z squared. When we solve differential equations such as the Schrödinger equations, it's very important to be able to separate the variables. But now if you see this square root of x squared plus y squared plus z squared, we know it's impossible to separate x from y or z. Therefore, we have to solve the Schrödinger equation in the spherical polar coordinates like this. Now we have only r, theta, and phi. How do we solve this? Well, first, we want to simplify this equation a little bit. This equation, this Schrödinger equation, can be simplified when we use the atomic unit system, in which the charge of electron is defined to be one atomic unit of charge. The mass of an electron is defined to be one atomic unit of mass. H bar is defined to be one atomic unit of angular momentum, and 1 over 4 pi epsilon 0. This is the electric force constant. It's also defined to be one atomic unit. Now if you look at SI units, the charge of electron is 1.6 times 10 to the power negative 19 coulomb. The mass of electron is 9.1 times 10 to the power of negative 31 kilogram. H bar is roughly 10 to the power negative 34 joule second. And this electric force constant, 1 over 4 pi epsilon 0, is about 9 times 10 to the power 9 joule meter per coulomb squared. Now if we use the atomic unit system, this H bar squared becomes 1, the mass of electron becomes 1, the charge becomes 1, and this 1 over 4 pi epsilon becomes 1. So again, this is the Schrödinger equation for the hydrogen atom in SI units. It's awfully complicated, but in the atomic unit system, the equation is at least somewhat simplified, because H bar is 1, the mass of electron is 1, the charge of electron is 1, moreover 1 over 4 pi epsilon 0 is 1. Now we have a slightly simpler equation for the hydrogen atom. The use of atomic units makes the derivations also easier in quantum chemistry. The units of other physical properties may be expressed in terms of the 4 fundamental atomic units. For example, one atomic unit of energy is called 1 Hartree, denoted by E sub h. It's defined by this mass of electron times the charge to the power of 4 divided by 4 pi epsilon 0 squared and H bar squared. Again, the 4 fundamental atomic units are the mass of the electron, the charge of the electron, H bar, and 1 over 4 pi epsilon. So now we have the atomic unit of energy. It's about 4.36 times 10 to the power of negative 18 joule. We can also have the atomic unit of length, which is 4 pi epsilon times H bar squared divided by me times E squared on the bottom, and it's roughly 5.29 times 10 to the power of negative 11 meters, or 0.529 angstroms. 1 angstrom is 10 to the power of negative 10 meters. Now when 2 electrons are separated by 1 atomic unit of length, the repulsion between the 2 electrons is plus 1 atomic unit of energy. If 1 electron and 1 proton are separated by 1 atomic unit of length, the attraction is negative 1 atomic unit of energy. Again, the Schrödinger equation in atomic units is this. First, we apply the kinetic energy operator to psi, and then the potential energy operator to psi. The potential energy operator is negative 1 over r only because the charge of the electron is 1. 4 pi epsilon is 1. Now we're going to solve this equation. Solving this differential equation can be non-trivial and tedious. So we will simply present the solutions here. As long as we can verify the solutions, we're good. The wave function of the electron may be expressed as the product of 2 functions, a function of r and a function of theta and phi. The function of r is denoted by uppercase R. The function of theta and phi is denoted by y. So in this r, we have 2 quantum numbers, n and l. We need n and l to determine the form of the function r. And over here, y is determined by 2 quantum numbers as well, but this time quantum number L and its z-component quantum number m sub L, or so-called magnetic quantum number. The wave function is the product of the radial function and the this part is the angular function. So the radial function of R depends on both n and L. N is the principal quantum number, L is the angular momentum quantum number. L can be from 0 to n minus 1. In this y function, the angular function of theta and phi depends on two quantum numbers. One is this L, the angular momentum quantum number, and m sub L, which is the magnetic quantum number. M sub L multiplied by h bar is the z component of the angular momentum. And again, the expression of this angular function y depends on both L and m sub L. Other than n, L, m sub L, the electron in the hydrogen atom, or any electron, has two more quantum numbers, s and m sub s. S is the three-dimensional spin angular momentum quantum number. M sub s denotes the z component of the spin angular quantum number, or it's called spin quantum number. The value of s is always 1/2. The value of m sub s can be plus or minus 1/2. Now let's look at the wave function of the electron. It's always a product of the radial function of the radius and the angular function of theta and phi. Now let's look at a few radial functions. For example, the 1s orbital, we have n equals 1, L equals 0, and this is the function, a normalization constant times e to the power of negative r over a naught. A naught is one atomic unit of length. A naught equals 0.529 angstroms. Now 2s orbital, again a normalization function, a polynomial function, an exponential function. By looking at this, we see a spherical node. When r is equal to 2 times a0, this wave function becomes 0. Therefore, we have a spherical node at r equals 2a0. And 2a0 is simply 2 times 0.529 angstroms. And now we have an exponential function. This time it's e to the power of negative r over 2a0 compared to e to the power of negative r over a0. We have this 2p radial function. So again, normalization factor and then polynomial function. This is just first order. And now we have this exponential function. So 2s and 2p share the same exponential function. Now let's look at 3s, 3p, and 3d. They share the same exponential function, e to the power of negative r over 3a0. Same here and same here. But if you look at the polynomial function, they're different. Over here, we can set this polynomial function to be 0 to obtain the two spherical nodes for the 3s orbital. And over here, we can set this to be 0 to find the one spherical node of the 3p orbital. Obviously, we can look at this and see, well, r is equal to 6 times a0. We're going to get the 36 here and 36 here. 36 minus 36 is 0. So when r is equal to 6 times a0, this function becomes 0. We have a spherical node. Now over here, we do not have any spherical node. In atomic units, the first few normalized radial function of r are this. They look a little simpler. So 1s orbital has a exponential function e to the power of negative r. 2s, 2p, e to the power of negative r over 2. 3s, 3p, 3d, e to the power of negative r over 3. And now if you look at the polynomial function of r over here between 2s and 2p, there's some difference. Over here, you have a spherical node when r equals 2. Over here, when this second order quadratic function of r is 0, you can find two roots that correspond to the two spherical nodes of the 3s orbital. Here, when r is 6, we have a spherical node. Over here, we do not have any spherical node. how do we solve this? Well, it's pretty easy if you remember how to solve the quadratic function. It's negative b over here, negative b, so it's going to be negative 18 plus minus the square root of b squared minus 4ac. That means the square root of 18 squared minus 4 times 2 times 27. And then divided by 2a. That means divided by 4. And you get these two roots, 1.9 atomic unit and 7.1 atomic unit. These two are the two spherical nodes for the 3s orbital. In atomic units, the first few functions of R are as follows. These functions are normalized. Well, we can double check this. If you use Wolfram Alpha, you can just enter this, integrate, this thing from 0 to infinity. So what is this? Well, this is simply this function squared, and then multiplied by R squared. If you integrate this whole thing, you'll get 1. In spherical coordinates, the volume element is r squared sine theta dr d theta d phi. Therefore, when we normalize this function, we need to take this function squared over here, and then don't forget we have r squared and then dr. So we have this equals 1. R is from 0 to infinity. Meanwhile, the angular function of theta and phi must also be normalized, and we have this integral here. Theta is from 0 to pi, phi is from 0 to 2 pi. The reason we have this sin theta here is because it's part of the volume element. Now the first few angular functions are the solutions to the three-dimensional quantum rotation of a two-body system, something like this. The first one is just a constant, and that's not surprising because s orbitals do not depend on theta or phi, so it has to be a constant that does not depend on theta or phi. Now let's look at p orbitals. When you look at p orbitals, well, the solutions are this: cosine theta, which is z over r, or sine theta times e to the power of plus minus I phi. Remember, e to the power of plus minus I phi are cosine phi plus minus I sine phi. So really, we're looking at a linear combination of x plus minus iy over r. Sine theta cosine phi is proportional to x. It's x over r. And sine theta sine phi is y over r. Now let's look at tz squared. dz squared is proportional to 3 cosine theta squared minus 1. So it's actually 3z squared minus r squared over r squared. And because r squared is x squared plus y squared plus z squared, here on top it's equivalent to 2z squared minus x squared minus y squared. Now we have dxz plus minus I dyz. They can be expressed as sine theta cosine theta times e to the power of plus minus I phi, which can be expressed as xz plus minus I times yz over r squared. And now we have dx squared minus y squared and dxy. The linear combinations of these two can be written as this. You have sine theta squared times e to the power of plus minus 2I phi. E to the power of plus minus 2I phi are linear combinations of cosine 2 phi and sine 2 phi. So we can look at sine theta squared times cosine 2 phi. That's equivalent to x squared minus y squared over r squared. Sine theta squared times sine 2 theta is equivalent to 2xy over r squared. We can easily verify this function y00 is normalized. We just need to integrate this. The squared modulus of y times sine theta d theta d phi. The integral is 1. The wave function of the electron of the hydrogen atom may be expressed as the product of a function of r and another angular function of theta and phi, so like this. So we're going to do the multiplication. The 1s orbital is the function of r and the function of theta and phi. So we put this together, we get a normalization constant times e to the power of negative r. Now 2s orbital, the function of r, the function of theta and phi, we multiply them together, we get a polynomial function of r times a exponential function of r. 2p orbitals. 2p0 over here. 2p0 and 2pz are the same thing. It's proportional to z and e to the power of negative r over 2. Now 2p plus minus 1. So what does that mean? Plus minus 1 means m sub l is equal to plus minus 1 when l is 1. And these two orbitals are neither px or py. They are linear combinations of px and py orbitals. So 2p plus minus 1 can be expressed as a normalization constant times x plus minus iy times the exponential function of e to the power of negative r over 2. Again, these two are linear combinations of px and py. And conversely, 2px and 2py are linear combinations of 2p plus minus 1. The wave function of the electron of the hydrogen atom may be expressed as the product of a function of r and an angular function of theta and phi, so like this. Now let's look at this 2p plus minus 1. That can be expressed as this. Now we're going to take the linear combinations of these two. So first we can add up 2p1 and 2p minus 1 divided by the square root of 2. We get the expression for 2px. Now we have similarly the expression of 2py, the same normalization factor times y times e to the power of negative r over 2. What about 2pz? Well, you just need to replace this y. You get 2pz. 1 over 4 times square root of 2 pi times c times e to the power of negative r over 2. That's 2pz. So you can see this 2pz over here. The 2p plus minus 1 wave functions are eigenfunctions of the z component of the angular momentum operator. The corresponding eigenvalues are plus minus h bar. The corresponding eigenvalues for 2p0 or 2pz is just 0 when m sub l is 0. Now the 2px and 2py atomic orbitals are expressed as real functions, which are more tangible than complex functions. However, 2px, 2py atomic orbitals are not eigenstate of the z component of the angular momentum operator, so that means we cannot determine the value of the momentum in the x and y direction. However, we can determine the z component of the angular momentum and also the total angular momentum at the same time. We can, however, determine the 3D plus minus 1 wave function and their z component. It's plus minus h bar. They are linear combinations of 3D xz and 3D yz orbitals. The 3D plus minus 2 wave functions are linear combinations of these two orbitals, 3D x squared minus y squared and 3D xy. So again, plus minus 2 means m sub l is equal to plus 2 or minus 2. If we combine these two wave functions, we can get 3D x squared minus y squared and 3D xy. So now let's look at the shape of some of the functions. Again, the 3s orbital is a exponential function multiplied by a second order polynomial function of r. And we have two roots here. That means we have two spherical nodes. And we also have 3p orbitals. They have one spherical node when r equals 6. So that means we can see a spherical node over here when r is equal to 6. And we have a planar node. When x is 0, y is 0, z is 0, we see a planar node in the 3px, 3py, 3pz orbital. And now look at the 5 d orbitals. We have 5 different d orbitals. They all each have 2 nodes, but different shapes. To normalize these wave functions, we need to solve the following equations. The integral of the squared modulus of psi times the volume element should be 1. R is from 0 to infinity, theta is from 0 to pi, and phi is from 0 to 2 pi. So again, we can examine those wave functions to see where the nodes are. So over here, when x squared is equal to y squared, we have 2 nodes. When x is 0, we have 1 node. When y is 0, we have node. Similar here, we have 2 planar nodes. When y is 0, z is 0. When x is 0, z is 0, we have 2 nodes. Over here, it's a little bit more complicated. When 3z squared is equal to r squared, we have actually 2 nodes with a cone shape. Now finally, let's look at the orbitals over here. The first few wave functions of the hydrogen atom are shown below. Each atomic orbital has n-1 nodes. That includes n-L-1 spherical nodes and L planar or angular nodes. For example, in a 3p atomic orbital, there are 3-1-1 spherical nodes. We just use this equation. When n is 3, L is 1, well, we have 3-L-1, that's one spherical node, and one planar node. In the 3D z-squared atomic orbital, there are two cone-shaped angular nodes when cosine theta squared is equal to 1/3. What does that mean? That means when z over r squared is 1/3, or when z over r is 1 over the square root of 3. Now in the 3D xy atomic orbital, there are two planar nodes, x equals 0 and y equals 0. So now let's look at this. This is the 3D z-squared orbital. I want to show you two conical nodes. One is here, one is here. They correspond to cosine theta is equal to plus minus the square root of 1 over 3. So that's why you have a cone with a constant theta, and over here you have another cone with a constant theta. Because cosine theta can be plus minus square root of 1 over 3, you have two cones as the nodal surface of this 3D z-squared. Now let's examine the spherical nodes of the s orbitals. One s orbital has 0 spherical nodes, 2s orbital 1 spherical node, 3s orbital 2 spherical nodes, and 4s orbital 3 spherical nodes. 2p orbital, no, we do not have any spherical nodes, but we have a planar node. Over here, 3p orbital, we have a planar node and 1 spherical node. Alright, 4p orbital, we have 1 planar node and 2 spherical nodes. So we can see the trend is this. Each atomic orbital has a total of n-1 nodes. And among this n-1 nodes, we have n-L-1 spherical nodes and L planar or angular nodes. Chapter 19. The hydrogen atom and the hydrogenic ions. Section 19.3. The properties of the hydrogen atom. Given the wave functions of the electron in the hydrogen atom, we can determine its physical properties. For example, we can apply the Hamiltonian operator to the wave functions to get the corresponding eigenvalues. Those eigenvalues are the energy of the electron. The 1s orbital has a wave function of e to the power of negative r multiplied by a constant. Now we can apply the kinetic energy operator to the wave function and also the potential energy operator negative 1 over r to the same wave function. And now we can just do mathematical derivations, because in this wave function we do not see theta or phi. Therefore, the first derivative of this wave function with respect to theta is 0. The second derivative with respect to phi is also 0. We have only this term here applied to this function. That's why we can simplify the left-hand side dramatically. And also we have the potential energy operator applied to psi. Now let's evaluate this. We do see n as a constant, the normalization constant. We can take it out. And the first derivative of e to the power of negative r is negative e to the power of negative r. Two negatives cancel. So we have this equation over here with this negative and another negative from here cancel. Now we just need to take the derivative of r squared times e to the power of negative r. And over here again, this is just the potential energy operator applied to the wave function. We expand this using the product rule. It's 2r times e to the power of negative r, and then minus r squared times e to the power of negative r. And we can simplify this expression. In the end, we get 1/2 times this wave function with a negative sign in the front. What does that mean? That means, well, first, this is indeed an eigenfunction of the Hamiltonian for the hydrogen atom. And number two, the corresponding eigenvalue is negative 1/2. And this is in atomic unit. One atomic unit is roughly 4.36 times 10 to the power of negative 18 joules. Again, this n is the normalization factor. So you can see in my derivation, I did not even use the value of n. So we get this result regardless of n. This is because the Hamiltonian is a linear operator, so even if you change the value of n, you're not going to change the eigenvalue. The eigenvalue of the 1s orbital wave function is negative 1/2 atomic unit of energy. That means, well, if the electron is in the 1s orbital, it has an energy of negative 1/2 in atomic units. And also it means, well, the total energy in the 1s electron is negative 1/2. We have this expression here. Now let's look at the 2pz atomic orbital energy as another example. The wave function is this. It's the normalization function over here, times r times cosine theta times e to the power of negative r over 2. Over here, when you have a principal quantum number 2 here, you see this principal quantum number here on the bottom. So it's negative r over the principal quantum number. R times cosine theta is really c, but it's more convenient to use r theta and phi here. Again, n is the normalization factor, so it does not really affect the eigenvalue we will get in the end. We apply this Hamiltonian to the 2pz wave function. So over here we have the kinetic energy operator, and over here potential energy operator being applied to the wave function. Now if you look at the wave function, it does not depend on phi at all, so this term disappears. We have only two terms in this kinetic energy operator. This is just the potential energy operator, negative 1 over r, applied to the wave function. Now we need to apply this operator to the wave function and this operator to the wave function. We do that separately. So over here, well, we just need to use some calculus skills to get this derivative, which is here. Again, you need to use the product rule. We get something here. Over here, it's easier because look, this r terms does not depend on theta, so we can take all those r terms out. We're just gonna take the first derivative of cosine theta and then times sine theta over here, and then whatever the result is, we take its first derivative and then divided by sine theta. So that's why we got this expression over here. And this part is just from the potential energy operator applied to psi. R and R cancel, so we have this. Again, calculus and algebra. So we get this over here. The first derivative of cosine theta is negative sine theta, so we get this. And we keep doing those mathematical operations. It's purely mathematics. All the way to here, it looks really tedious. And this part goes here, this part goes here. But if you look at all those terms, they have a common factor. Well, the common factor is this. Pay attention here. We have n cosine theta, n cosine theta, n cosine theta. So we see this everywhere. We have this n cosine theta. And then we include every other, terms over here just inside. So this goes here, this goes, this two together goes here, because this two can be combined. So this two together goes here, and this term goes here, this term goes here. Finally, the potential energy applied to the wave function goes here. So we can clean it up. I think this two will cancel, this two will cancel. In the end, we get negative 1 over 8 in r cosine theta e to the power of negative r over 2. It happens to be negative 1 over 8 multiplied by the wave function of the 2pz orbital. So we proved two things. One is, indeed, this is a eigenfunction of the Hamiltonian for the hydrogen atom. Alright, so this function is an eigenfunction of the Hamiltonian for the hydrogen atom. And number two, the eigenvalue is negative 1 over 8. That means the energy of the electron is negative 1 over 8 in atomic units. And one atomic unit is 4.36 times 10 to the power of negative 18 joule. It's just a constant. Well, over here we're looking at the wave function for the 2pz orbital in the hydrogen atom again. We apply the Hamiltonian to the wave function. We get negative 1/8 times the wave function. So again, the physical meaning is pretty simple. The eigenvalue is negative 1 over 8. Therefore, the atomic orbital energy is negative 1 over 8. The total energy of the electron in the 2pz orbital is negative 1 over 8. And in general, without proving everything, the energy of the electron in the hydrogen atom is -1/2n² in atomic units. N is the principal quantum number. So if you have n equals 1, it's -1/2. When n is 2, -1/8. N equals 3, like a 3D electron in the hydrogen atom, well, it's going to be -1/18. What if you promote the electron to the 4f orbital? The energy is -1/32. When the electron makes transition from one level to another level, we can compute the energy change. Well, the equation is this: if an electron jumps from the mth level to the nth level, well, we have this equation, and this is the energy change. Now we're going to set an equation over here. We're going to set this, well, hc times over here, this is the Rydberg constant, times 1/m² minus 1/n². Well, this is the energy difference between the transition from level m and level n. When we learned this Rydberg equation in general chemistry. And over here we have the energy difference between the mth energy level and the nth energy level in quantum chemistry. So we can put equal sign in between to determine the value of the Rydberg constant. So you can see H times C times the Rydberg constant is 1/2 atomic unit. 1/2 atomic unit is this much in joule, and the Rydberg constant is 1/2 atomic unit of energy over H over C. We get this value, well, 1.1 times 10 to the power of 7 per meter, and that's indeed the value of the Rydberg constant. Well, now of the wave functions of the hydrogen in the of the electron in the hydrogen atom is an eigenfunction of the potential energy operator. That means we will never know the exact potential energy of the electron in the hydrogen atom. However, we can evaluate the expectation value of the potential energy using quantum mechanical postulate 4. For example, let's look at the 1s electron in the hydrogen atom. We just need to use postulate 4, and this is the expectation value of the potential energy, -1/r. Why -1? Well, it's just negative E². E is the charge of the electron, only because the charge of the proton and the charge of the electron have opposite signs. So now we have this postulate 4 being used here with two integrals, one on top, on the bottom. On the bottom you have psi star times psi. On the top you have psi star multiplied by, well, the operator applied to psi here first. You need to do this operation first and then multiplication. So over here I'm just writing out the integrals. I'm using the volume element in the polar spherical coordinates, which is r² sine theta dr d theta d phi. Again, this is the volume element of a three-dimensional space in the polar spherical coordinates. Alright, and I think I see this n on top twice and on the bottom twice. So the normalization factor will eventually cancel n² and n² will cancel. And there's a trick of evaluating a triple integral. That is, if you can separate the variables, do that. So what I'm going to do is I'm going to just separate the variables over here. We have an integral of r, and over here, sorry about this, I think there's a typo here. I need to quickly fix the typo here. There's no dr in here. Alright, now we're good because we're evaluating the function of r over here. And again, on top you have a triple integral. I'm just separating this to a single integral of r over here on top, and this is on the bottom. Because of this -1/r, we have a negative sign here, and because this -1/r is multiplied by r², so you have r here, and on the bottom you have r² here. If you look at theta and phi, well, on top you have a double integral of theta and phi. On the bottom you have the same double integral of theta and phi. So they will eventually cancel, and then we get this simplified expression for the average potential energy. Sometimes we just use Wolfram alpha to get those values. Make sure you know R is from 0 to infinity, but we can also derive this by hand, this general equation by hand, and then use this equation to get the value of the top integral, which is 1 factorial over 2 to the power 2, and the bottom integral is 2 factorial over 2 to the power 3. The result is -1. So we can prove this by hand, but I'm gonna skip this part. We'll just use this expression and plug in the values of n in the expressions here. We get -1. And when you see -1, it's actually -1 atomic unit of energy, and that's actually -4.36 times 10 to the power of -18 joule. The expectation value of the kinetic energy is going to be the total energy minus the expectation value of potential energy. So it's -1/2 minus -1. We get +1/2 atomic unit. So it's just simple. It's just because the total energy is the sum of its kinetic energy and potential energy. So if you are interested in the average kinetic energy, we can always get the total energy and also the average potential energy. Take the difference, you get the average kinetic energy. Now let's look at the expectation value for the potential energy of this 2pz orbital. We're going to use quantum mechanical postulate for, again, we have the complex conjugate over here. This is potential energy operator applied to the wave function. On the bottom, it's the integral of psi star times psi. So we're plugging all those integrals, and you'll see we can separate this triple integral on top into 3 single integrals. One of r, one of theta, one of phi. And same here on the bottom. But you probably notice that the angular part on top and the angular part on the bottom are exactly the same. So on top, the integrals of theta and phi, and the integrals on the bottom of theta and phi, they completely cancel. So I'm not going to show you the detailed derivation, but you can see over here we need to integrate cosine theta, sine theta, d theta. On the bottom, cosine theta, I'm sorry, I forgot this cosine theta. So on top, we need to integrate cosine theta times sine theta, d theta. On the bottom, we need to integrate cosine theta, sine theta, d theta. They will cancel. And again, on top, we need to integrate this d phi. On the bottom, we'll just integrate this d phi, so they also cancel. That's why you can see there's only the integrals of a function of r on top, and also the integral of a function of r on the bottom. Look, you have r to the power 3 on top, r to the power 4 on the bottom. Well, only because on top we have this 1 over r operator. The negative sign goes here. So, and then we can just evaluate this. How do I evaluate this? One way is to use Wolfram alpha, but also you can actually hand derive this. It's possible to just derive this and plug in the values, and then we have -3 factorial over 4 factorial. We'll get -1 over 4. That's the average potential energy of the 2pz electron in the hydrogen atom. The unit is atomic unit. Again, this n is the normalization factor. You can see n appears on top 2 times and also on the bottom 2 times. They cancel. The expectation value of the kinetic energy is, well, the total energy minus the potential energy. We get a positive 1/8 atomic unit of energy. Well, it is counterintuitive, but the higher energy 2pz electron in the hydrogen atom moves slower than the 1s electron. Alright, so it's kind of strange, but it's true. If you have 2pz electron, its kinetic energy is only 1/8. The kinetic energy of 1s electron is actually 1/2 atomic unit. In general, the total energy of the electron in the hydrogen atom is always -1 over 2n squared atomic unit. the expectation value of the potential energy is negative 1 over n squared. So this is 2 times the total energy. The expectation value of the kinetic energy is 1 over 2n squared, and n is a principal quantum number. So you can see the kinetic energy and the total energy have the same magnitude, but different signs. The total energy is negative, the kinetic energy is positive. The magnitude is 1 over 2n squared. Given the angular part of the wave function of electron in the hydrogen atom, we can also determine its average rotational energy if somehow we can determine the expectation value of 1 over r squared, because the rotational energy is just L times L plus 1 times h bar squared over 2I. I is the moment of inertia. We can determine the exact angular momentum in the 3-dimensional space. It's the square root of L times L plus 1 and then times h bar, and also its z component, which is just m sub L h bar. So how do we know this? Well, again, we can just apply the corresponding operators, to the wave function to get those. For the s orbital, L is 0. Therefore, the magnitude of the 3-dimensional angular momentum is the square root of 0 times 1 and then times h bar, which is 0. M sub L is 0. Therefore, this is just 0. If you have a p orbital, L is 1. Therefore, the magnitude of the 3-dimensional angular momentum is square root of 2 times h bar. What about the z component? We may have 3 different values. It can be 0. It can be plus minus h bar when m sub L is plus minus 1. Again, px and py, they do not really have a specific value for the z component. We need to do a linear combination of px and py to get either plus h bar or negative h bar. So again, p plus minus 1 wave functions are linear combinations of px and py. At the same time, px and py are linear combinations of p sub plus minus 1. When we have a d orbital, well, L is 2. The 3-dimensional angular momentum is just square root of 6 h bar. The z component can be 0 plus minus 1 plus minus 2 h bar. What if we have L equals 3 for f orbitals? Well, the square root of 3 times 4, that's the square root of 12. We have square root of 12 h bar. The z component can be 0 plus minus 1 plus minus 2 plus minus 3 h bar. We have a degeneracy of 7 here. When we have a g orbital, L is 4. The 3D angular momentum is the square root of 20 times h bar. The z component can be 0 plus minus 1 plus minus 2 plus minus 3 plus minus 4 times h bar. Well, now the wave functions of the electron in the hydrogen atom is an eigenfunction of the radius operator. So we will never know the exact radius of the electron in the hydrogen atom. We can, however, evaluate the expectation value of r, the radius. Same thing possibly for the complex conjugate of the wave function, and then the operator applied to the wave function on top. On the bottom is just the integral of complex conjugate times the wave function. We plug in all those expressions for the wave function, for its complex conjugate, and plug in the operator here. When we apply the r operator to a function, it's equivalent to the multiplication by r, and then we have these two integrals. How do we evaluate this? Again, we're going to use this expression over here, and we plug in a equals 3 versus a equals 2. Over here, we have 3 factorial over 2 to the power of 4, and on the bottom we have 2 factorial over 2 to the power of 3. We get 1.5. So the average radius is 1.5 for the 1s electron. Alright, so that's the physical meaning of this. We can also get the average for r squared. It's just we need to use r squared operator instead of the r operator. So on top, this is r cubed, this is r to the power of 4. So that's the difference. We evaluate these two integrals. We get the average for r squared, which is 3. And now we can even determine the standard deviation. It's just the square root of 3 minus 1.5 squared. We have the standard deviation for the radius. of the 1s electron in the hydrogen atom, and this standard deviation is very large compared to the average value. The average is 1.5, and the standard deviation is about 0.9 atomic unit of length already. Remember, 1 atomic unit length is about 0.529 angstrom. We can also look at the most probable radius of the electron in the hydrogen atom. So the probable radius can be determined by maximizing this r squared. This is the radial function. Y times r squared, well, it comes from the volume element. The volume element is r squared times sine theta dr d theta d phi. So we need to maximize this whole thing. So when we set its first derivative to 0, we can expand it using the product rule in calculus. We get this equation. And the lowercase r cannot be 0, the uppercase r cannot be 0. So therefore, we have only one legitimate solution. This radial function is equal to negative r times its first derivative. So we're going to just solve this equation for different wave functions, well, to get the most probable radius, which maximize this over here. This is the probability density as a function of r. So now let's look at the 1s orbital. When you have 1s orbital, the radial function is e to the power of negative r. Again, don't worry about the normalization factor. It does not play a role here. So we're going to just write out this equation. We take its first derivative. We plug it in here. We solve this equation, r is 1. So the most probable radius of the 1s electron is 1 atomic unit of length. It's actually smaller than the average radius, which is 1.5. The root mean squared radius is 1.732 atomic unit. So in general, the most probable radius is smaller than the average radius. The average radius is always smaller than the root mean squared radius. And when the principal quantum number n is larger, well, all those three radii, the most probable radius, the average radius, and the root mean squared radius are all larger. The electron is further away from the nucleus when the principal quantum number is larger. Again, we can just calculate the most probable radius given the wave function. Now let's look at the 2s wave function. We have this polynomial function. Well, it's the first order multiplied by exponential function over here. This is the function of r for the 2s electron. Again, we use this equation. R plus the lowercase r times the first derivative of the function of r is 0. We plug in the expression here. This is the function itself, and this is the first derivative. We have a common factor, e to the power of negative r over 2. So both sides divided by this exponential function, we get this. And then from here, we get a second order equation or quadratic equation. Solving this, we get two roots. Both are legitimate roots. That means if you have a 2s electron, there should be two maxima, one at 3 plus the square root of 5, one at 3 minus the square root of 5. So the numerical values are 0.764 atomic unit and 5.236 atomic unit. Again, there are two maxima in the 2s orbital. And between these two maxima, there's a node, there's a spherical node. I think we determined this spherical node before. When r equals 2, we have a spherical node. Oh, by the way, if you just set this to 0, r is equal to 2 to have this spherical node. So that's pretty easy. Now let's look at a 2p wave function over here. Again, we use this equation. It's just r plus the lowercase r, the radius, times the first derivative of the function. This should be 0. We solve this equation, r equals 4. So if you have a 2p electron, there's only one maximum. That maximum is at 4 atomic unit of length. And for the 2p electron, there's no spherical node. There's only one planar node. Now let's look at this radial distribution of various wave functions of the electron in the hydrogen atom. The most probable radius of the 1s electron is 1 atomic unit. So right here you can see it's 1. For the 2s electron, there are 2 maximum. Let's look at the 2s, the shape here. You have a bump here, another bump here. They are just 2 maximum. Over here, this is 0.764 over here, a bit less than 1. And then another one is 5.236, a bit above 5. So you can see this is a bit above 5, right? For the 2p orbital, we learned that the most probable radius should be the maximum or the most probable radius is 4. So you can see over here, this is maximum of the probability density. It's just 4 atomic units. So again, given the wave function, we can easily calculate the most probable radius. And I showed you how to calculate the average radius, the root mean squared radius, the standard deviation of the radius. At least we know we cannot determine the radius of the electron exactly. However, we can have the distribution, and you can see this distribution for the 1s electron, the distribution for the 2s electron with 2 maxima separated by a node, a spherical node. We can see this 2p distribution, only 1 maximum without any spherical node, and you can see 3D, the wider distribution, all right, and a larger most probable radius. I think this is about 9 over here. 3p has 1 spherical node separating 2 maxima, and then 3s has 3 maxima, 1 2 3 3 maxima separated by 2 spherical nodes. Chapter 19, the hydrogen atom and hydrogenic ions. Section 19.4, the hydrogenic ions. Hydrogenic ions are 1 electron atomic ions such as helium plus, lithium 2 plus, and beryllium 3 plus that consists of only 1 nucleus and 1 electron. The Hamiltonian of hydrogenic ions can be expressed as this: the kinetic energy operator of the single electron and the potential energy operator. The potential energy operator is negative COR because in the nucleus we have a nuclear charge of Z. Z equals 2, 3, or 4 for helium plus, lithium 2 plus, or beryllium 3 plus. The 1s wave function of the hydrogenic ions is the normalization factor n times an exponential function e to the power of negative zr. Z is the number of charges in the nucleus. E to the power of negative zr decays faster than that of the hydrogen atom. We can apply the Hamiltonian operator to the wave function for those hydrogenic ions to get the eigenvalues. So we apply the kinetic energy operator to the wave function, potential energy operator to the wave function. Because the wave function does not depend on theta or phi, we have a simpler term over here that consists of only r as the variable. So mostly it's just calculus here. We take the first derivative of this exponential function, multiply by r squared, take the derivative again, and then divided by 2r squared, etc. So first, the first derivative of this, well, we get this here, and we take nz out of this parenthesis because they are constant. And then we further take the derivative of r squared times e to the power of negative zr. Using the product rule in calculus, we get this. Here we have the potential energy operator applied to the wave function. So we expand this too. We get a total of 3 terms. And fortunately, the first and third term cancel. Now we have only this. It's negative z squared over 2 times the wave function. Therefore, this function is indeed an eigenfunction of the Hamiltonian operator of the hydrogenic ions. The corresponding eigenvalue is negative z squared over 2. In general, the energy levels of the electron in an hydrogenic ion is given by this equation. E sub n is equal to negative z squared over 2n squared. Z is the number of protons in the nucleus, and n is the principal quantum number. For example, the energy of the 1s electron in lithium plus is negative 4.5. We just need to use negative 3 squared over 2 to get the energy of the 1s electron in lithium 2 plus. Similarly, the energy of the 1s electron in beryllium 3 plus can be calculated with z squared over 2, and then of course we need a negative sign in the front, and this is negative 8 atomic unit because the calculation is negative 4 squared over 2. The energy of the 2p electron in beryllium 3 plus is negative 2 atomic unit. Again, it's just negative 4 squared over 2 times 2 squared. You get negative 2 in the end. The expectation value of the kinetic energy of the electron in a hydrogenic ion is z squared over 2n squared. Note that the average kinetic energy with principal quantum number n is equal to negative total energy with quantum number n. The expression is z squared over 2n squared. The expectation value of the potential energy of the electron in a hydrogenic ion is negative z squared over n squared. The expectation value of the potential energy can be expressed as negative z over r enclosed in a pair of brackets, because z is a constant, so this is equal to negative z times the expectation value of 1 over r. And this whole thing is proportional to z squared because the expectation value of 1 over r is proportional to z, the number of charges in the nucleus. Qualitatively speaking, the electron in the hydrogenic ion is closer to the nucleus when the nuclear charge is larger, and therefore the expectation value of 1 over r is larger when z is larger. The energy levels of the electron in hydrogenic ions are given by this. E sub n is equal to negative z squared over 2n squared atomic unit. The expectation value of the potential energy of the electron is negative z squared over n squared. So you can see the average potential energy is 2 times the total energy. Both are negative. Now let's look at one example. The expectation value of the potential energy of the 1s electron in a hydrogenic ion is negative z squared atomic unit. We can evaluate the expectation value of potential energy using quantum mechanical postulate 4. This is the expectation value of potential energy. We can take z out, and then we just need to evaluate this negative 1 over r. Using quantum mechanical postulate 4, we have this division between two integrals. On the bottom is just the integral of the complex conjugate of the function times the function. On top, it's the complex conjugate of the wave function multiplied by, over here, the operator applied to that wave function. D tau is the volume element. D tau is r squared sine theta dr d theta d phi. So we're going to just plug in the expression for this wave function of the 1s orbital, which is n times e to the power of negative cr for the hydrogenic ion. So you can see this on the bottom 2 times, and also on the top, and over here, this is simply the potential energy operator applied to the wave function. Now we have a triple integral on top and a triple integral on the bottom. It can be separated this way. We have now a single integral of r and a double integral of theta and phi. On the bottom also we have a integral of r with respect to r, and then a double integral of theta and phi. Fortunately, the angular part of these two integrals are exactly the same, so they cancel. We have only the integrals with respect to r. And then over here we can see that this z can be rewritten as z squared times z squared over z cubed. Why am I doing this? Well, it's just I'm about to use variable substitution. I see this zr here, so I'm about to convert this r to zr, this dr to dzr. That's why I need z squared on top. I need z cubed on the bottom because I have r squared here times dr. So by doing this, I got this expression, negative z squared. Now on top and on the bottom we have two integrals with respect to zr, and we can then use variable substitution. For example, we can set x to be zr, and then we have the integral of e to the power of negative 2x x dx. On the bottom we have the integral of e to the power of negative 2x x squared dx. And we can hand derive this or get it from Wolfram alpha. And then we get the expression, it's negative z squared times 1 factorial over 2 to the power of 2 divided by 2 factorial over 2 to the power of 3. Or it's just negative z squared. So what we have is this. The potential energy operator is negative z over r. The expectation value of potential energy is negative z squared. So now we know the 1s orbital in the hydrogenic ion has a total energy of negative z squared over 2. Its average potential energy is negative z squared. The 1s average kinetic energy then must be this total energy minus the average potential energy. Therefore, the average kinetic energy of the 1s electron in a hydrogenic ion is z squared over 2, atomic unit of energy. Chapter 20, Many Electron Atoms, Section 20.1, The Schrödinger equation of the helium atom. The helium atom is considered one of the many electron atoms because a helium atom contains 2 electrons. So any atoms that contain 2 or more electrons are many electron atoms. A helium atom contains 1 nucleus with plus 2 charges and 2 electrons, each with a negative 1 charge. It is treated as a 3-particle system in quantum mechanics. Nucleus at the center surrounded by 2 different electrons. Their positions are specified by the R1 factor and R2 factor. Now let's look at the Schrödinger equation for the electrons in the helium atom. It's negative h bar squared over 2m sub e Laplacian plus negative h bar squared over 2me Laplacian for electron 2. The first 2 terms are the kinetic energy operators for the 2 electrons. Now we have the attraction felt by electron 1, the attraction felt by electron 2, and now finally the repulsion between the 2 electrons. E squared over 4 pi epsilon 0 R12. R12 is the distance between the 2 electrons. Now we have the Hamiltonian applied to the wave function of the 2 electrons. We get energy times the wave function of the 2 electrons. There is no way to solve this Schrödinger equation exactly. In general, there's no way to solve the Schrödinger equation for any system that contains 2 or more electrons. But still, we can get some approximate solutions. First, this psi, the wave function, can be written as psi of R1 and R2, Well, because we have two electrons with positions being specified by R1 and R2 vectors. And now this is the general form of the Laplacian, the sum of the three derivatives with respect to x, y, and z. We use this Laplacian for convenience because it's really easy for us to write out the kinetic energy operator for electron 1 and then for electron 2. R1 and R2 are the vectors pointing from the nucleus to the electrons. R1, 2 is the distance between the two electrons. The mathematical form of R1, R2 are just this, the square root of x1 squared plus y1 squared plus z1 squared, where x1, y1, z1 are the Cartesian coordinates of electron 1 relative to the center, which is the nucleus. Same for R2. R1, 2 is a bit complicated. It's the square root of over here. This is delta x squared, delta y squared, delta z squared. Delta is the difference between electron 1 and electron 2. Why don't we include the kinetic energy of the nucleus in the equation? Well, it's just two reasons. One, the kinetic energy of the nucleus is much smaller than the kinetic energy of the two electrons, and therefore it's often neglected. The second reason is if we do include the kinetic energy of the nucleus, that will make the Schrödinger equation more difficult to solve. Anyway, in the future, we will be able to recover the kinetic energy of the nucleus separately. There are four fundamental atomic units. The charge of an electron is 1. The mass of an electron is 1. H bar is 1. 1 over 4 pi epsilon is 1 in atomic units. So in atomic units, the Schrödinger equation for the helium atom can be really simplified to this. Kinetic energy operator for electron 1, kinetic energy operator for electron 2. This is the attraction felt by electron 1. This is the attraction felt by electron 2. And this is the repulsion between electron 1 and electron 2. Everything together, these 5 terms, is the Hamiltonian for the 2 electrons. We apply the Hamiltonian to the wave function of the 2 electrons, H psi equals E psi. The kinetic energy operator can also be expressed in spherical polar coordinates. Alright, because the Laplacian can be written in this form: 1 over r squared outside the square bracket. Inside there are 3 terms. The first term, delta over delta r times r squared delta over delta r. Second term, 1 over sine theta delta over delta theta, and then sine theta times delta over delta theta. The third term, 1 over sine theta squared, and then delta squared over delta phi squared. The derivation of this Laplacian in polar spherical coordinates can be found in Appendix P. It's very tedious. But now let's just assume, we can just simply use this for electron 1, we use this for electron 2. Even if we convert everything into polar spherical coordinates, we can still not be able to solve this Schrödinger equation. Because the Schrödinger equation now contains 6 coordinates, at least 6 coordinates: r1, theta 1, phi 1, r2, theta 2, phi 2. And also the distance between the 2 electrons, r1 and r2, can be really complex. Again, let's look at the Schrödinger equation for the helium atom in the atomic units. Kinetic energy of electron 1, negative 1/2 Laplacian for electron 1, and then kinetic energy operator for electron 2. Attraction felt by electron 1, attraction felt by electron 2, and then over here we have electron-electron repulsion. How do we solve this Schrödinger equation? We have to make approximations. Well, there are different levels of making approximations, so let's try the first level of approximation, which is so-called orbital approximation. We're going to say, well, let's try to separate the variables for the 2 electrons by doing this. the wave function of two electrons is equal to the product of the wave function of electron 1 times the wave function of electron 2. Alright, so it's the product of phi 1 and phi 2. So by looking at this, you know, this psi squared is phi 1 squared times phi 2 squared. And psi squared is the probability density of the two electrons. Is equal to the probability density of electron 1 times the probability density of electron 2. There's a underlying assumption over there when we do this. That's the probability of finding electron 1 at this position and the probability of finding electron 2 at this position are independent of each other. Alright, so two unrelated events for electron 1 and electron 2. But later we'll see, you know, this is not a very good approximation because the probability of electron 1, probability of electron 2 are correlated. Now let's look at this approximation again. Phi 1 and phi 2 are one electron wave functions, also known as just atomic orbitals. The approximate solution to the Schrodinger equation is this. Phi 1 is e to the power of negative zeta R1. Phi 2 is e to the power of negative zeta R2. And then psi of the two electrons is just phi 1 times phi 2, which is e to the power of negative zeta R1 times e to the power of negative zeta R2. Zeta denotes the effective nuclear charge felt by the electron. How do we determine the value of zeta? We will first study two extreme cases to determine the range of zeta. So case 1, let's move electron 2 into the nucleus. And now you have just electron 1 outside the nucleus. Overall, the attraction it feels is only +1 charge, because when we have electron 2 located in the nucleus, now in the nucleus we have +2 and -1. Alright, together it's only +1, and then electron 1 outside the nucleus feels only +1 charge. Case 2, we move electron 2 infinitely away from the nucleus and from the electron 1. And in that case, well, the effective nuclear charge for electron 1 would be 2. So just imagine when we have a helium atom, it has 2 electrons. Now we send one of the 2 electrons to the moon. Alright, and then we have only a nucleus with +2 charge and 1 electron outside the nucleus on Earth. Alright, in that case, the effective nuclear charge is 2. So we consider two extreme cases, you know, when R2 is 0, when R2 is infinity. The real case should be in between. Therefore, we say, well, the value of zeta, the value of the effective nuclear charge, should be between 1 and 2. Over here we have some values for the effective nuclear charge. Let's look at helium. The effective nuclear charge is indeed between 1 and 2. It's roughly 1.7. Well, you can say the 1s electrons in helium repel each other, so there is some electron shielding. And in this case, the electron shielding is approximately 0.3. So the effective nuclear charge is +2 minus 0.3. We get 1.7 approximately. If you look at lithium, well, there's 1s electrons, there's 2s electron. So for the 2s electron, you can say, well, approximately it feels electron shielding of 2. So the inner shell electrons, you know, can effectively shield outer shell electrons. So the effective nuclear charge for lithium is roughly 1. So 3 minus 2 is roughly 1. Now let's look at the 1s electrons. Over here, this is 2.7. Why is that? Well, first, the 2s electron does not shield the inner shell electrons. So we only consider the electron shielding between the two 1s electrons. That's roughly 0.3. And then they both feel attraction from +3 protons in the nucleus. So +3 minus 0.3, I think we get 2.7. So we can qualitatively explain all those trends all those numbers in this table, but let's focus on the helium atom. Again, it's the effective nuclear charge is roughly 1.7. So again, we have approximate solution to the Schrodinger equation for the electrons in the helium atom. It's the product of two wave functions, each for an electron. The wave function of R1 and R2 is the product of a wave function of R1 times the wave function of R2, and approximately it's going to be the product of two exponential functions, e to the power of negative zeta R1, e to the power of negative zeta R2. We consider two extreme cases in which the electron 2 is moved into the nucleus versus moving to the moon. So R2 can be 0, R2 can be infinity. In that case, we get zeta for electron 1. Alright, for case 1, zeta is 1. For case 2, zeta is 2. Therefore, in the real world, I think zeta is between 1 and 2. And again, zeta is the effective nuclear charge. We'll just use the experimental data for the first and second ionization energy of helium to determine the value of zeta. The total energy of the two electrons is simply the sum of the ionization energy of electron 1, the sum of and the ionization of ionization energy of removing the second electron. So it's negative 2.9 atomic unit. So what does this mean? It takes this much energy, 2.9 atomic unit, to remove both the electrons from the nucleus. And we use that state, separated electrons and nucleus as the zero reference. Alright, and then if we have a helium atom, it has a energy of negative 2.9 atomic unit. And now we're going to calculate the effective nuclear charge. The energy for this, if you have a Y electron system with a effective nuclear charge of zeta, the energy is negative zeta squared over 2. Now we have 2 of such electrons, so 2 times this energy is equal to negative 2.9. Alright, we solve this equation, we get zeta equals 1.7. So this value matches with the value we got from here, this table. The effective nuclear charge of helium is indeed roughly 1.7. So we're good, and the wave function of the two electrons can be written as e to the power of negative 1.7 R1 times e to the power of negative 1.7 R2. Alright, so again, this is just one of the approximations. Alright, and this wave function looks reasonable. Well, at least when you look at this wave function, you can see zeta is 1.7, and when zeta is 1.7, the energy is negative zeta squared over 2, right? And then we have 2 such electrons. The total energy is 2 times negative zeta squared over 2, and we do the calculation. It's roughly negative 2.9. And also we know it takes 2.9 atomic unit of energy to remove these 2 electrons. That means the total energy of these 2 electrons is indeed negative 2.9 in the helium atom, and everything seems to match. However, this wave function violates quantum mechanical postulate 6. In postulate 6, we have this: the wave functions of electrons must change sign under the exchange of 2 electrons. So if you exchange any 2 electrons, the sign of the wave function must change. So we have this mathematical form: the sign of R2 R1 should be negative sign of R1 R2. Alright, now let's look at this equation. So if we have this kind of equation, this equation is not antisymmetric. When we exchange R1 and R2, so that means when we exchange this 2, alright, we get this wave function, but this wave function is exactly the same as the original wave function. That means when we take this form for the wave function of the 2 electrons in the helium atom, it's a violation to the quantum mechanical postulate 6, because after we exchange R1 and R2, we get the same wave function. Supposedly the sign should change, but we didn't see any sign change of this wave function. And again, because after we exchange R1 and R2, we actually get the original wave function. We say this wave function is symmetric under the exchange of 2 electrons. Again, it's a violation of postulate 6. Postulate 6 says, well, the wave function must be anti-symmetric. That means the sign must change under the exchange of 2 electrons. So now, how do we kind of solve this problem? Well, we have to consider electron spin in the wave function of the helium atom to resolve this issue. Chapter 20. Many electron atoms. Section 20.2. Electron spin and Pauli exclusion principle. Every electron has an intrinsic angular momentum that originates from its constant spinning about the x, y, and z axis that cross the center of the electron. A spinning electron can be viewed as an electric current loop, which produces a magnetic moment. The shorthand notation for the 3-dimensional electron spin operator is lowercase s, topped by a caret symbol. The z component of s is denoted by s sub z. The z component of the spin of an alpha electron is positive by definition. The z component of the spin of a beta electron is negative by definition. The magnitude of the angular momentum of the electron spin is the square root of 0.75 times h bar. This is because the spin quantum number s is 1/2 for both alpha and beta electrons. And when s squared operator is applied to alpha and beta, the eigenvalues are the same. They're both h bar squared times s plus 1. So when we apply s squared to alpha, we get 0.75 h bar squared alpha. When we apply s squared to beta, we get 0.75 h bar squared beta. Again, it's just 0.5 times 1.5 is 0.75. So we have this spin angular momentum squared equal to 0.75 h bar squared. We can take the square root for both sides. The magnitude of the 3-dimensional angular momentum is thus the square root of 3/2 times h bar, or it's approximately 0.866 h bar. The z component of the angular momentum of the electron spin is m sub s h bar. M sub s is the z component of the electron spin. M sub s can be negative 1/2 or positive 1/2. And therefore, we can apply this s sub z operator to alpha and to beta. We get two different eigenvalues, positive 1/2 h bar, negative 1/2 h bar. Alpha and beta denote the two spin functions of the electrons. They are always normalized. That means the integral of alpha star times alpha d sigma is 1. The integral of beta star beta d sigma is also 1. Here, alpha star is the complex conjugate of alpha, beta star is the complex conjugate of beta. And sigma is the spin coordinates of the electron. Alpha and beta are orthogonal to each other. So the integral of alpha star beta is 0. The integral of beta star alpha is also 0. Sigma, again, is the spin coordinates of the electron. You may imagine this sigma contains also three variables, a radius, a value of theta, a value of phi for the electron spin. The electron often has two different rotational motions. One is about the nucleus, and then you have r, theta, and phi as the coordinates. But there's also a spin about its own axis, and then you need another set of polar spherical coordinates to describe the electron spin. Intuitively, we proposed this e to the power of negative zeta r1 times e to the power of negative zeta r2 for the wave function of the helium atom, but we learned that that's a violation of postulate 6, because in postulate 6 we know the wave function of two electrons must be anti-symmetric under the exchange of these two electrons. So now, what if we add some spin function? Intuitively, we just add the spin function this way. We add alpha 1 here to specify the spin of electron 1, beta 2 here to specify the spin of electron 2. We're assuming electron 1 has a alpha spin, electron 2 has a beta spin. But unfortunately, this wave function is neither symmetric nor antisymmetric, because if we exchange the two electrons 1 and 2, well, we can see this is what we got. These two are different, and these two are also different. So it's neither symmetric nor anti-symmetric. So we must modify this wave function to comply with postulate 6 by ensuring that the wave function change sign under the exchange of two electrons. So we have to have this. One of the linear combinations of these two functions is antisymmetric under the exchange of the two electrons, and thus complies with postulate 6. So you can see over here, this is e to the power of negative zeta r1 alpha 1, e to the power of negative zeta r2 beta 2, and here we have e to the power of negative zeta r2 alpha 2, and e to the power of negative zeta r1 beta 1. So look here, this somehow indicates electron 1 is alpha, electron 2 is beta. Now this is kind of just reversed. Electron 1 is beta, electron 2 is alpha. So we can somehow do a linear combination of these two. One of the linear combinations is this. We just simply take the difference between these two. So the first term, electron 1 is alpha. The second term, electron 1 is beta. The first term, electron 2 is beta. The second term, electron 2 is alpha. Now, since the exponential function is the common factor, we can take this common factor out. We have the product of two exponential functions, e to the power of negative zeta r1, e to the power of negative zeta r2. We know this is symmetric under the exchange of two electrons. And then we look at the spin part. The spin part is alpha 1 beta 2 minus alpha 2 beta 1. Somehow this is anti-symmetric, because if you exchange 1 2, it becomes alpha 2 beta 1 minus alpha 1 beta 2, which is the opposite to this original spin part. Therefore, under the exchange of two electrons, this spatial part that depends on the spatial coordinates remains unchanged. So this two exponential functions together is symmetric. But the spin part is anti-symmetric, which changes sign when we exchange the two electrons. So overall, this wave function becomes anti-symmetric under the exchange of two electrons. And therefore, this wave function complies with the quantum mechanical postulate 6. We can easily verify if we exchange 1 and 2. We have psi of R2 and R1. And then I need to replace R1 with R2, R2 with R1, 1 with 2, 2 with 1, 2 with 1, and I replace this 1 with 2. Now let's compare this wave function and this wave function after the exchange. The exponential function here, this 2, are the same as this 2. But now look at the spin part. Negative alpha 2 beta 1 becomes positive alpha 2 beta 1. Positive alpha 1 beta 2 becomes negative alpha 1 beta 2. Now we changed the sign. What if the two electrons in the 1s orbital of the helium atom were forced to have the same spin? For example, both are alpha spin. Then the wave function of this will have to become this. We need to change beta to alpha, and then we get the wave function equals 0. And that means two electrons in the 1s orbital of helium must have different spins. If they have the same spin, even this wave function doesn't work. You get a value of 0. The probability is 0. Now, more generally, Pauli exclusion principle states that two electrons in the same spatial orbital must have different spins, because otherwise the wave function would be 0. Exactly 0. The probability of finding two electrons with the same spatial quantum number and the same spin quantum number is just 0. And when the wave function is 0, the squared modulus of the function is 0, the probability density is 0, and then the probability is 0. So in the end, no two electrons in the same spatial orbital can have the same spin. Well, also you can say two electrons with the same spin cannot occupy the same spatial orbital. Pauli exclusion principle states that two electrons in the same spatial orbital must have different spins, because otherwise the wave function would be 0. For the same reason, two electrons with the same spin cannot occupy the same spatial orbital. And more generally, it's less likely to have electrons appear close to another if they have the same spin than if they have opposite spins. And this phenomena is called exchange hole, depicted in this graph. So if you have a alpha electron over here at this position, it's unlikely to have another alpha electron getting close to this alpha electron, because two alpha electrons can never have the same spatial quantum numbers, and that means they can never occupy the same spatial orbital. And because of this, the density of the second electron may drop significantly when it's close to the first electron with the same spin. And this results in a smaller electron-electron repulsion. So two alpha electrons can better stay away from each other because of this Pauli exclusion principle. And therefore, we have a lower energy between two alpha electrons than the energy between one alpha and one beta, due to the smaller electron-electron repulsion. And this energy decrease is called exchange energy. And here's one example. If we excite one of the electrons in the helium to the 2s orbital, the triplet electronic state has lower energy than the singlet electronic state, because in the triplet electronic state we can have the two electrons with the same spin. In the singlet state, the two electrons have opposite spins. Now let's look at the excited helium atom in detail. When an electron is excited to the 2s orbital, there are 4 different arrangements that include a triplet electronic state with a degeneracy of 3 and a singlet electronic state. The triplet electronic state of this 1s1, 2s1 electron configuration has lower energy because in the triplet state, the two electrons may have opposite spins. We have three functions over here. They are degenerate. So we can see all these three wave functions are a product of the spatial part and the spin part. The spatial part is the same. It's f1 of r1 times f2 of r2 minus f2 of r1 times f1 of r2. f1 and f2 denote the spatial functions of 1s and 2s orbitals. And you can see 1, 2, 3, these three are exactly the same. Now let's look at the spin part. It can be alpha 1, alpha 2. Both electrons are alpha electrons. Beta 1, beta 2. Both electrons are beta electrons. Well, over here, this is kind of a little strange. This is alpha 1, beta 2 plus alpha 2, beta 1. This is due to the quantum effect. Electrons must be indistinguishable. So this wave function must be written in a way that it's anti-symmetric. And over here, the spatial part is anti-symmetric. The spin part must be symmetric. So over here, we have to write alpha 1, beta 2 plus alpha 2, beta 1 to make sure that this wave function remains unchanged when we exchange two electrons. So if you replace 1 with 2, 2 with 1, 2 with 1, 1 with 2, you get the same spin part. Same here. If you exchange 2 and 1, it remains unchanged. If you exchange 1, 2, this spin part remains unchanged. But the spatial part is anti-symmetric. Alright, so we have a product of the spatial part and the spin part. Alright, so if the spatial part is anti-symmetric, the spin part must be symmetric. So now we have the anti-symmetric spatial part and the symmetric spin part. And overall, the wave function is anti-symmetric. Now let's look at the spin part. Alpha 1, alpha 2. Beta 1, beta 2. And finally, alpha 1, beta 2, and alpha 2, beta 1. They all share the same spin quantum number. S is 1. So S is 1 for the 3, alright? And when S is 1, we have a degeneracy of 3 because the Z component can be from negative 1 to 1. So the Z component of the electron spin is over here, this is 1, this is negative 1, and over here, this is 0. So all three share the same spin quantum number, S is 1. But now M sub S can be negative 1, 0, and positive 1. Finally, let's look at the singlet, in which S is 0, M sub is 0. We have a degeneracy of 1. Let's look at the wave function of the 1s1, 2s1 electron configuration here. Now this time, the spatial part is symmetric. The spin part is anti-symmetric. Overall, the product is anti-symmetric in compliance with postulate 6. So it's possible to calculate the average electron repulsion using postulate 4. In postulate 4, what we need to do is we need to have two integrals on the top and the bottom of a fraction. On the bottom, it's the integral of psi star times psi. And on top, it's the integral of psi star multiplied by the repulsion operator applied to the wave function. So we can compare this wave function and this wave function, alright, or just any one of the three, and evaluate their average repulsion energy. You will see when we use this singlet wave function, we have a larger repulsion than the triplet. And again, that's the so-called exchange energy. The electron repulsion is smaller in the triplet electronic state here than the corresponding singlet state over here. Chapter 20. Many electron atoms. Section 20.3. The wave functions of the electrons in an atom. There is a systematic way of constructing an anti-symmetric wave function of two or more electrons. That is to use a determinant. Because when we switch two rows or two columns of a determinant, the sign of its value changes. Here's an example. We can use this wave function to describe a two-electron system. The wave function of two electrons, 1, 2, can be expressed as 1 over the square root of 2 factorial times a determinant. In this determinant, electron 1 occupies the first row, electron 2 occupies the second row, and we have phi 1 in the first column, phi 2 in the second column. Phi 1 and phi 2 must be different. We can expand this determinant. We get phi 1 of 1, phi 2 of 2 minus phi 1 of 2 times phi 2 of 1. And this is anti-symmetric, because if we switch 1 and 2, we will switch the sign of the determinant. Phi 1 and phi 2 must be different. They are normalized, they are orthogonal to each other. So here, this is what it means to be normalized. The integral of phi 1 squared d tau is always 1. The integral of phi 2 d tau is always 1. Phi 1 and phi 2 are orthogonal to each other. That means the integral of psi 1 star times phi 2 is 0. The integral of phi 2 star times phi 1 equals 0. Over here we have 1 over the square root of 2 factorial. This is just to normalize this wave function. We have a 3 by 3 determinant. We need to have 1 over the square root of 3 factorial in the front of the determinant to normalize the wave function. For the helium atom, we may propose phi 1 to be the normalization factor n times an exponential function e to the power of negative zeta r times alpha. Phi 2 is the same as phi 1, except the spin is beta. Again, this uppercase N is to normalize phi 1 and phi 2. The physical meaning of the 2 by 2 determinant is this. The two 1s electrons, electron 1 and electron 2, we know they have alpha spin and beta spin, but we cannot tell which electron is alpha, which is beta. Both electrons are both alpha and beta. And when one electron is determined to be alpha, then the other must be beta. If one electron is determined to be beta, the other is alpha. But before that, we have to say we know both electrons are both alpha and beta. Again, a systematic way of constructing an anti-symmetric wave function of two electrons in the helium atom is to use a determinant. We have a 2 by 2 determinant. We have 1 over the square root of 2 factorial as the normalization factor. Inside, we have electron 1 in the first row, electron 2 in the second row. Wave function phi 1 in the first column, wave function phi 2 in the second column. And then we can expand this 2 by 2 determinant. We get 1 over the square root of 2 and squared, and then there's two exponential functions, and this part is the spatial part of the wave function. The spatial part is symmetric. Now we have the spin part, which comes from alpha 1 times beta 2 minus beta 1 times alpha 2, and this spin part is anti-symmetric. We can easily prove this entire wave function is anti-symmetric under the exchange of the two electrons. We simply look at psi of 2 and 1 versus psi of 1 and 2. So over here, we need to replace every 1 with 2, every 2 with 1 from this equation. So R1 becomes R2, R2 becomes R1. Alpha 1 becomes alpha 2, beta 2 becomes beta 1, etc. Now we can see this part remains unchanged. The spin part, well, changes sign. So we proved that this wave function is anti-symmetric. In general, the wave function of a many electron system is often expressed as the product of a spatial function and a spin function. Or we can say the spatial part or the spin part of the wave function. When the spatial part is symmetric, the spin part must be antisymmetric. When the spatial part is antisymmetric, the spin part must be symmetric. This is to ensure the total wave function as a product of the spin part and spatial part is antisymmetric. And in the end, we need to apply with quantum mechanical postulate 6. The wave function of the electrons must change sign under the exchange of any two electrons. Again, one systematic way of building an antisymmetric wave function is to use a determinant. And this is because when we switch two rows of the determinant, the sign of the determinant will change. Again, why do we choose the determinantal form when constructing the wave function of a many electron system? The reason is simple. Mathematically, the value of a determinant changes sign under the exchange of any two columns or any two rows. So if you look at this determinant and this determinant, I simply exchanged this row with this row. I switched two rows, and therefore the sign changes. And psi 1, 2 is negative psi 2, 1. When we have a 3 electron system, again we use a 3 by 3 determinant. Well, over here we have electron 1, electron 2, electron 3. In the 3 rows, we have phi 1, phi 2, and phi 3 in the 3 columns. Make sure phi 1, phi 2, and phi 3 are different from each other. Phi 1, phi 2, phi 3 should all be normalized. And also phi 1, phi 2, phi 3 are orthogonal to each other. And then we have a legitimate wave function for a 3 electron system. 1 over the square root of 3 factorial is the normalization factor. Just because if you expand this, we get 3 factorial terms. And then we need to ensure the squared modulus of psi has a integral value of 1. So that's why we need to have 1 over the square root of 3 factorial here. What if we have 100 electrons in an atom? Well, in that case, we need to write out a 100 by 100 determinant. We have 100 electrons labeled 1, 2, 3 all the way to 100, represented by 100 rows, and then we need 100 1 electron wave functions, phi 1, phi 2, phi 3, etc., all the way to phi 100. And then we write them out, phi 1, phi 2, phi 3, etc., to phi of 100. So that's why we have 100 rows for 100 electrons, 100 columns for 100 wave functions. And then you have a huge determinant, 100 by 100 determinant. When you expand it, you have 100 factorial terms. And that's why the normalization factor would become 1 over the square root of 100 factorial. So this is one reason why quantum mechanical calculations for even just one atom can be tedious and slow. Again, we have this many terms when we expand a 100 by 100 determinants. The Pauli exclusion principle results from the antisymmetric property of the wave function of electrons. No two electrons can have the same set of quantum numbers. In the helium atom, the two electrons in the 1s orbital have the same values of n, l, m sub l. They also have the same value of s, but they have different spin quantum numbers m sub s plus minus 1/2. So the physical meaning of this is actually the z component of the electron spin. That can be plus 1/2 h bar or negative 1/2 h bar. If two electrons were allowed to occupy the same spatial orbital and have the same spin, then the wave function of these two electrons would be identical. Phi 1 will be equal to phi 2, and then we can just use phi to represent phi 1 and phi 2. Now if we write out the wave function for the two electrons, it becomes this. You have phi 1 in the first row, phi 2 in the second row. And you can see the first column is exactly the same as the second column. Now I'm going to switch these two columns, and I need to switch the sign. So after I switch the two columns, it's actually the same. So the determinant is equal to negative this determinant. So what happens here is psi 1, 2 turns out is equal to negative psi 1, 2. How can we solve this equation? Well, this has to be 0. Only 0 is equal to negative 0. That means the wave function must be 0, the probability density must be 0, the probability of finding two electrons with the same spatial and spin quantum numbers, well, is exactly 0. There's no way to have two electrons in the same atom with the same spatial quantum numbers and also the same spin quantum numbers. And therefore, in the helium atom, you must have one alpha electron and one beta electron. Alright, remember for all electrons, the value of S, this is for the three-dimensional spin, it's always 1/2. But the Z component can be 1/2 or negative 1/2. So if you are looking at two electrons with the same spatial quantum number, that means if they have the same n, L, m sub L, well, they have to have different m sub s. One is half, the other electron is negative 1/2. And this is why each atomic orbital may accommodate up to 2 electrons, not 3 electrons. When you have 3 electrons in the same atomic orbital, inevitably you will have either 2 alpha electrons or 2 beta electrons. That will make this wave function 0. And that means the probability of finding 3 electrons in the same atomic orbital is 0. 2 electrons in different atoms may have the same set of quantum numbers just because their spatial orbitals have different centers. For example, if you have a diatomic molecule, let's say chlorine 2, well, it's possible to have a 1s alpha electron in the left chlorine and also 1s alpha electron in the right chlorine atom. That's possible. Chapter 20, Many Electron Atoms, Section 20.4, The Variational Method. Here we propose a antisymmetric wave function for the 2 electrons in helium. Psi of electron 1 and electron 2 is equal to 1 over square root of 2 times n squared times the exponential function of negative zeta R1, another exponential function of negative zeta R2, times the spin part of the wave function, which is alpha 1 beta 2 minus alpha 2 beta 1. Here n is the normalization function for the 1 electron function. Zeta is the effective nuclear charge. R1 and R2 specify the distance between the 2 electrons and the nucleus. The expression of this wave function indicates that these 2 electrons together have an alpha and beta spin by looking at this. The z component of the spin angular momentum of the 2 electrons together is 0. So we know there's plus 1/2 h bar and minus 1/2 h bar. So together it's 0. Now let's determine the value of zeta. One way, of course, is to do the experiment. We just need to measure the amount of energy to remove both electrons from the helium atom. And that amount is 2.9 atomic unit of energy. And then we can divide this 2.9 between these two electrons. So each electron has a negative 2.9 over 2, that amount of energy. And we can just approximately state that the energy of each electron is negative zeta squared over 2, assuming it's a hydrogenic electron. And then we set up negative zeta squared over 2 is equal to negative 2.9 over 2. Zeta is determined to be 1.7. So that's how we experimentally determine the value of zeta. How can we determine zeta without doing any experiments? Well, we resort to the variational theorem. It states that whatever trial wave function is used to estimate the expectation value of the energy of the system, the trial energy is always greater than the exact energy of the system. The trial energy comes from the postulate 4 over here when we use the trial wave function. So this is the expression of quantum mechanical postulate 4. On the bottom, we have the integral of the complex conjugate of the trial function times the trial function. On top, we have another integral, which is similar, but over here, instead of the wave function, we use h, the Hamiltonian, applied to that wave function instead. So if we have a trial function, we can determine the trial energy. And the variational theorem states that the trial energy is always greater than the exact energy. The lower the trial energy, the closer the trial function is to the exact wave function. So how can we solve for the exact wave function? Well, one way is to propose a trial function with parameters, and then we can simply minimize this trial energy by varying those parameters so that this trial function is minimized. And when this trial function is truly minimized, it's equal to the exact energy. Now the problem of solving the Schrodinger equation for this multi-electron system becomes minimizing the trial energy in terms of trial function. For the helium atom, we can minimize the trial energy by solving this equation. The first derivative of the trial energy for the helium atom with respect to zeta, which is a parameter, should be 0. So really we're trying to find the value of zeta that minimizes the trial energy. So we propose this trial function for the helium atom. We have normalization factors, exponential functions of zeta times r. Here and here for the two electrons, we have the spin part. Now we evaluate the trial energy. We use postulate 4 here. We plug in the trial function. You may ask, what happened to the spin part? Well, fortunately, you see the integral of the spin part on top and also on the bottom. And fortunately, this Hamiltonian does not change the spin function. So we have the same spin integral on top and on the bottom, they cancel. So again, this Hamiltonian does not make any change to the spin part. Therefore, the spin integrals on top and the spin integrals on the bottom are exactly same. They cancel. The normalization factors also cancel. So for the helium atom, we have the trial energy like this. Let's compare this to integrals on the bottom. It's mostly the wave function squared. On top, it's the wave function multiplied by, well, the Hamiltonian applied to the wave function. So this is the trial energy. We have one parameter, theta, in the expression of the trial energy. How do we minimize the trial energy? Well, at the minimum, the derivative with respect to theta should be 0. So we just need to solve this equation. We take the first derivative of the trial energy with respect to theta. We set the derivative to 0. We just need to solve this. Well, solving this is non-trivial because, well, these two integrals cannot be easily solved, especially the top one. If you look at this Hamiltonian, perhaps the kinetic energy part, the attraction part are fairly easy to solve or relatively easier to solve. But over here you have 1 over R12. In this R12, the coordinates of electron 1 and the coordinates of electron 2 are highly correlated. We cannot separate those variables. So we can solve the top integral numerically, I believe. The bottom integral, I think, is relatively easy because we just have exponential functions. And this d tau is dr1, d theta 1, d phi 1 multiplied by r1 squared sine theta 1. And also we have electron 2. So we have r2 squared sine theta 2, dr2, d theta 2, d phi 2. But still, it's solvable. The top is more difficult, especially when we evaluate the integral that involves 1 over the distance between the two electrons. But still, numerically, I think it's possible to express this in terms of theta and then evaluate the first derivative of the trial energy with respect to theta. We set it to 0, and theoretically we can solve that equation and get theta equals 1.7. Practically, it takes, I think, a very long time to do this calculations. You need to either write a program or maybe you can use a Excel spreadsheet to estimate those integral values. The effective nuclear charge of each 1s electron then fills 1.7 effective nuclear charge in the helium atom based on this calculation. And similarly, we can propose a trial function in the determinantal form for the neon atom, but with more parameters. You need, for example, effective nuclear charge for the 1s electron, for the 2s electron, and also for the 2p electrons. But still, in principle, we can just set this to 0. The first derivative of the trial energy with respect to parameter 1, parameter 2, parameter 3, they should all be set to 0. And then we can solve for the values of zeta 1, zeta 2, zeta 3, etc. for the neon atom. For any other atoms, we can use the same strategy. It's just we might have many more parameters to be optimized. The variational theorem states that whatever trial function you propose to estimate the expectation value of the energy of the system, the trial energy is always greater than or equal to the exact energy of the system. This equal sign holds only if your trial function is exactly the exact wave function. Alright, over here, this is the expression of the trial energy given the trial function. On the bottom, it's the integral of the complex conjugate of the trial function times the trial function. On top, it's the integral of the complex conjugate of the trial function multiplied by the Hamiltonian operator applied to trial function. We can verify this theorem by looking at one specific example. The particle in the box example. We know the exact energy of the particle in the box problem. It should be n squared times h squared over 8ma squared. When n is 1, we get 1 squared h squared over 8 ma squared. Alright, but now let's propose a trial function like this. The reason we propose this kind of trial function is because when x is 0, the trial wave function is 0. When x is equal to a, the trial wave function is also 0. So at least when we propose ax minus x squared, this wave function becomes 0 at the two boundaries, when x is 0 or when x equals a, this value is 0. The square root of 30 over a to the power of 5 is the normalization factor. We introduce this normalization factor to ensure the integral of the squared modulus of the trial function is 1. So now let's use this trial wave function to get the trial energy. Again, this is normalized already. So the bottom integral is just 1. The top integral over here, we have the wave function here. And then this is the kinetic energy operator applied to the wave function. Because the potential energy is 0, so we do not have to write that part. It's just the kinetic energy here. And we can, take the second derivative of this function, which is just -2. So I put -2 here. The wave function copied here. Also, we have the normalization factor squared. I put it here, and then we have negative h bar squared over 2m over here. We just need to integrate this part. This part is pretty easy. We just need to somehow integrate ax and x squared separately. They go here and here. What happens to the -2 here is this: we have -1/2. -1/2 times -2 is just 1, so that's why -2 disappears, -1/2 disappears. So we get this equation. We plug in the lower limit and upper limit, we get something here, and then we clean it up. We get this value. This value is h squared over ma squared multiplied by a number, 5 over 4 pi squared. And 5 over 4 pi squared is 0.12665. Well, it's greater than 0.125, and 0.125 is 1 over 8, which happens to be the exact energy of the particle when its quantum number is 1. So we proposed a trial function. We get the trial energy, and the trial energy is indeed greater than the exact energy over here. So this is just a numerical example that shows that the trial energy is always higher than the exact energy. So one strategy of solving the Schrodinger equation is this: we first propose a trial function that contains one or more parameters, and then using this trial function we can determine the trial energy that contains one or more parameters, and then we need to minimize the trial energy with respect to those parameters. That means if we have, for example, 3 parameters, Z1, Z2, and Z3, we just need to set the first derivative of the trial energy with respect to Z1 to 0, with respect to Z2 equals 0, with respect to Z3 equals 0. We solve all those equations to obtain the optimal values for those parameters. Now over here, there's also an example. We propose a trial function. In the end, we see this trial function has a trial energy higher than the exact energy. Chapter 20. Many electron atoms. Section 20.5. The Hartree-Fock self-consistent field method. For many electron atom, the Schrodinger equation can be solved iteratively and approximately using the self-consistent field method proposed by Hartree and Fock. For example, the Schrodinger equation of the helium atom is this: H psi equals E psi. H consists of kinetic energy operators for electron 1 and electron 2, the attraction felt by electron 1 and electron 2, and the repulsion between the two electrons. We neglect the kinetic energy of the nucleus because it's much smaller than the kinetic energy of the electrons. And also, later we will see it's possible to recover the kinetic energy of all nuclei in a system in a different way. This is the Laplacian for electron 1, Laplacian for electron 2 in polar spherical coordinates. R12 is the distance between electron 1 and electron 2. It's the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. And this term is really difficult to deal with. There's no easy way to separate the coordinates from electron 1 of electron 1 from the coordinates of electron 2 in this expression, 1 over the distance between electron 1 and electron 2. Therefore, we have to make approximations to simplify this Schrodinger equation for the helium atom. And the essence of the Hartree-Fock self-consistent field method is to break the Schrodinger equation of two electrons into two simpler Schrodinger equations, each containing only one electron. So we're about to just solve one electron Schrodinger equations. What if we have many electrons? Well, we will just break the Schrodinger equation of many electrons into many one electron equations and solve those one electron equations first, and then finally come up with a solution to the Schrodinger equation of many electrons approximately. This is just because it's much easier to solve one electron Schrodinger equations than to solve a Schrodinger equation of many electrons. The Schrodinger equation for the helium atom is this: H psi equals E psi. H is the Hamiltonian. The Hamiltonian consists of the kinetic energy operators for both the electrons, the attraction felt by both the electrons, and the repulsion between the two electrons. This can be simplified to two Schrodinger equations. There's two. In the first Schrodinger equation, it contains only electron 1. In the second Schrodinger equation, it contains only electron 2. Therefore, these two equations are one electron Schrodinger equations. In principle, we can always solve those one electron Schrodinger equations. But what is this? Well, V sub 1 effective. This is the effective potential energy felt by electron 1. And this is the effective potential energy felt by electron 2. So in these two equations, somehow we have to propose the effective potential energy for electron 1 here and for electron 2 in the second equation. Phi 1 is the wave function for electron 1. Phi 2 is the wave function for electron 2. Epsilon 1 is the energy of electron 1. Epsilon 2 is the energy of electron 2. And also we call epsilon 1 and epsilon 2 as atomic orbital energies. Phi 1 and Phi 2 are called one electron atomic orbitals because Phi 1 contains the coordinates only of electron 1. Phi 2 contains only the coordinates of electron 2. Now really, these two, the effective potential energy operator, they are both one electron operators that contain the coordinates of only one electron. So V1 effective contains the coordinates of only electron 1. V2 contains only coordinates of electron 2. But then first, how can we make the effective potential energy operator of electron 1 not contain the coordinates of electron 2 and vice versa. So that's question 1. And 2, well, how to determine the expressions of the effective potential energy operator for this 2. We will resort to quantum mechanical postulate 4. So in postulate 4, we learned how to get the expectation value of a physical property. But this time, we're not going to get a value. We're not going to get a expectation value. We will get a expectation potential energy operator. We'll get the effective potential energy operator. So over here, the effective potential energy is the sum of the attraction and repulsion, and given the total wave function psi of 1 and 2, we can somehow evaluate the repulsion operator of the 2 electron repulsion. Here, this is our approximation. We can just integrate the total wave function. This means complex conjugate. So this is the complex conjugate of the total wave function of the 2 electrons. And over here, we apply the repulsion energy operator to the side, the total wave function. And d tau is the volume element. But look, before we used to have d tau to be the volume element of both electrons. But here, we're going to have this d tau be the volume element of a single electron. Here's the idea. For electron 1, the 1 electron effective potential energy operator may be expressed as this. Alright, this is effective potential energy, and over here we have attraction. This is simple, but then what about electron-electron repulsion? Doesn't that include the coordinates of electron 2? Yes. However, we can integrate this psi star and then repulsion operator applied to psi, and then d tau 2. Over here, d tau 2 is the volume element of electron 2. And if we integrate over the coordinates of electron 2, we will be able to effectively remove the coordinates of electron 2 using this integral. Alright, for example, let me give you an example. If we integrate xy with respect to dx, and x is from 1 to 2, the final result will not contain any x, right? So if you integrate x times y with respect to dx, x is from 1 to 2, I think you will get 1/2 x squared times y, and x is from 1 to 2, and then you will get something like 1.5y as the result of that integral. So by integrating this 2 electron function with respect to the coordinates of electron 2, you remove the coordinates of electron 2 in the final result. The final result will still contain the coordinates of electron 1. So that's the idea. For electron 2, we do similar things. The effective potential energy of electron 2 is the attraction it feels from the nucleus, plus over here we integrate psi star, repulsion operator applied to psi. Now with respect to d tau 1, d tau 1 is the volume element of electron 1. So now we have 2 effective potential energy operators for electron 1 and for electron 2. And over here, it contains only electron 1. This operator contains only electron 2. And by the way, this psi should be the total wave function of the 2 electron system. The total wave function can be built up in a format of determinant. In this case, it's 1 over the square root of 2 factorial, the normalization factor over here, and a 2 by 2 determinant. You have electron 1 in the first row, electron 2 in the second row. Phi 1 in the first column, phi 2 in the second column. It's a 2 by 2 determinant to ensure that this wave function is anti-symmetric under the exchange of 2 electrons. But here's another problem. So I was assuming that we know this psi 1 2 to derive the expressions for the effective potential energy operators. We do need to know psi 1 2 here, 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 and here to somehow express the effective potential energy operator for electron 1 and that for electron 2. And we know how to build this total wave function of 2 electrons. Alright, it's just this determinant with this normalization factor. And phi 1 and phi 2 are normalized wave functions. Phi 1 and phi 2 should be orthogonal to each other. So we know all that. But what are the expressions of phi 1 and phi 2? Shouldn't we solve the one electron Schrodinger equation for electron 1 to get phi 1, and then solve the one electron Schrodinger equation for electron 2 to get phi 2? Well, somehow we cannot do that because we do not even know what are the effective potential energy operator for electron 1 or for electron 2. Now we're stuck. Unless we know there exists some kind of iterative algorithms designed to solve this kind of problems. So here is this iterative algorithm. In general, you can use similar algorithms to solve many mathematical problems. Over here, we're going to just use this mechanism to solve the Schrodinger equation. Step number 1. Make an educated guess of phi 1 and phi 2 to construct the total wave function, psi 1 2. So over here, this is going to be just a pure guess based on some understanding of the 2 electrons. So it's not really a pure guess, it's educated guess. For the helium atom, I think I would guess phi 1 to be e to the power of negative 2r multiplied by alpha. Phi 2 would be e to the power of negative 2r multiplied by beta. So it's some kind of guess based on the nuclear charge. Because the nuclear charge is 2, I'm just guessing it's a exponential function e to the power of negative 2r. And we know one electron should be alpha, the other wave function, the other one electron wave function should be beta, something like that. So that's going to be my guess. And based on the educated guess of phi 1 and phi 2, I can build psi 1 2. Once we have psi 1 2, we'll use quantum mechanical postulate 4 to obtain the effective potential energy operators of V1 effective and V2 effective. So we just use this postulate 4 and we integrate psi star. So this is psi star, and then the repulsion operator applied to psi. But when we integrate this integral, make sure for the effective potential energy for electron 1, you integrate that integral with respect to electron 2 only. And to get this, you integrate with respect to electron 1 only. That way, V1 effective and V2 effective are not going to be some numerical values. V1 effective will be a function of R1. V2 effective will be a function of R2. And now we can use V1 effective and the kinetic energy operator for electron 1 to construct a one electron Schrodinger equation to obtain phi 1. We'll use V2 effective to build a one electron Schrodinger equation for phi 2, and we'll solve for phi 2. And now we get phi 1 and phi 2. The phi 1 and phi 2 here are different from our initial guess of phi 1 and phi 2. And then we simply use the new phi 1 and phi 2 to get a new total wave function psi 1 2. And after we get a new psi 1 2, we get a new V1 effective, a new V2 effective. And then we use the updated V1 and V2 effective to obtain another updated set of phi 1 and phi 2. From the latest phi 1 phi 2, we build another psi 1 2. We keep repeating steps 2, 3, 4 until the convergence of the effective potential energy operator for electron 1 and that for electron 2. And that's called self-consistent field. This is how we solve the Schrödinger equation for the helium atom that contains 2 electrons using the self-consistent field method proposed by Hartree and Fock. For the lithium atom with 3 electrons, for the 118 electron atom with this many electrons, or even a very large protein molecule that contains 500,000 electrons, we use a similar iterative algorithm. Alright, if you have 118 electrons, you can write a single Schrödinger equation that contains 118 electrons. But then we need to break this huge Schrödinger equation into 1 electron Schrödinger equations. How many of those? 118 of those. In each 1 electron Schrödinger equation, you need a Y electron effective potential energy operator, and you can solve that 1 electron Schrödinger equation. Then you get phi 1, phi 2, phi 3, all the way to phi sub 118. And using all those phi's, you can build a determinant to get the total wave function of 118 electrons. And using that total wave function, you get the new set of effective potential energy operators. So we repeat those steps from step 2 to step 4 to keep updating phi 1 and phi 2, to keep updating psi of all electrons, and to keep updating the effective potential energy operators until the convergence is reached. So that's the idea of the self-consistent field method proposed by Hartree and Fock. Chapter 20, Many Electron Atoms, Section 20.6, Periodic Trends. The periodic trends of the atomic radius, ionization energy, electron affinity, and metallic character are illustrated here in this periodic table. So first, we just need to identify one element, francium, over here. Francium has the largest principal quantum number n, the smallest effective nuclear charge. Therefore, francium has the largest atomic radius, the smallest ionization energy, the smallest electron affinity, and the most metallic character. By identifying this francium as a reference, we can easily find the trends of the atomic radius, ionization energy, electron affinity, and also metallic character. Over here on this corner, helium has the highest ionization energy. Helium has the smallest atomic radius. However, regarding electron affinity, actually fluorine and chlorine have the largest electron affinity. Now let's look at the definitions of ionization energy and electron affinity. Ionization energy is the amount of energy required to remove an electron from an atom. So the ionization energy is the energy of the cation of X minus the energy of atom X. And usually when we say ionization energy, we're referring to the first ionization energy, unless it's specified otherwise. Electron affinity. It's the amount of energy released when an atom gets one additional electron. So electron affinity is the energy of the atom minus the energy of the anion of the same atom after it gets an electron. Electron negativity, chi, is the ability of attracting shared electrons. Elements with larger ionization energy and larger electron affinity have higher electron negativity values. There are various models to compute or define electron negativity, but all of them lead to essentially the same result or same value for electron negativity. So Molechem proposed this equation to get the value of electron negativity. They sum up the ionization energy and electron affinity and then divide it by 1 electron volt. Whatever the result is, multiplied by a parameter here and then plus another parameter, we get the electron negativity. So you can see, based on this equation, if we have a larger ionization energy, larger electron affinity, we have a larger chi. So actually that's why fluorine has the largest electron negativity, and francium with the smallest ionization energy, the smallest electron affinity. Francium has also the smallest electron negativity. Pauling used the dissociation energy of diatomic molecules to determine the difference in electron negativity. So he used this equation. It's just because when the electron negativity of A differs significantly from B, there's more ionic character in the bond is stronger. Usually ionic bond strength is stronger than covalent bond strength. So he used that to propose this kind of equation. Over here, this is just the AB bonding energy. This is AA bonding energy, BB bonding energy. So he took the average of AA and BB bond energies, compare that with the AB bond energy, and then divide by 1 electron volt. And somehow he took the square root of it to get the electron negativity difference between A and B. So in both formulas, so if you use Mollechem's formula or Pauling's formula, anyway, the electron negativity of fluorine is 4.0. And I think francium is 0.7. Francium has the smallest electron negativity. Fluorine has the largest electron negativity. Now here's a table of the values of electron negativity. As I mentioned, fluorine has the largest electron negativity, 4.0. Fluorine 0.7, the smallest. And it's fairly easy to memorize the electron negativity of the second row, because if you see it's 1.0, 1.5, 2, 2.5, 3, 3.5, and then 4, there's a trend. So the difference between two neighboring elements is 0.5 in this row. We do not have electron negativity for helium, neon, or argon because I don't think they share electrons with other elements. This is the Mollechem's formula. Again, based on this formula, you can see if we have, for example, the francium atom. The francium atom has the smallest ionization energy and the smallest electron affinity, and therefore it has the smallest electron negativity. Chapter 20, Many Electron Atoms, Section 20.7, Microstates and Atomic Terms. Even a single carbon atom with the 1s2, 2s2, 2p2 electron configuration may have many energy levels. From the NIST website, we can see the first few energy levels are 0, 16, 43, 10,000, 21,000 wave numbers. Each wave number is 1 centimeter to the power of -1. So if you multiply this value by the Planck constant and the speed of light, you can get all those relative energies in Joule. But why so many energy levels? Well, this is just because a carbon atom has a partially filled 2p orbital. The 2p orbitals can accommodate up to 6 electrons. But over here we have only 2 electrons. When you put 2 electrons into the 3 2p orbitals, there are 15 ways of arrangements. They are called microstates. These 15 microstates may be grouped into 3 atomic terms. The lowest energy atomic term further splits into 3 energy levels, with 1 or 3 or 5 microstates. They correspond to the relative energy of 0, 16, and 43 wave numbers. And then there are 2 other atomic terms. They correspond to 10,000 wave numbers and 21,000 wave numbers. But now again, why 15 microstates? Well, let's imagine putting 1 electron into the 2p orbitals. Because there are 3 2p orbitals, and the electron can be alpha spin or beta spin, there are 6 ways of arrangements, also known as 6 microstates. The m sub L value, this is the z component of the angular momentum of the electron. It can be -1, 0, or 1. Because when you have p orbital, L is 1, the m sub L can be -1, 0, or 1. The ms value of the electron can be -half or +half. So we can take just any one of the 6 combinations. 3 options here, 2 options here, then in total we have 6 options for the first electron. Now, after we put the first electron into the 3p orbitals, let's place a second electron in these 2p orbitals. Now there are only 5 options left, because no 2 electrons in the same atom may have the same set of quantum numbers. This is why the first electron has 6 options, but the second electron has only 5 options. So now we have 6 times 5, 30 possible arrangements. 6 for the first electron, 5 for the second electron. Only if the electrons are distinguishable. However, we know electrons are indistinguishable. So any permutation of the 2 electrons correspond to the same physical state. Therefore, there are only 30 over 2 factorial, which is 15 possible arrangements when we place 2 electrons in the 3 2p orbitals. What if we have 3 electrons in the 2p atomic orbitals? Well, the first electron has 6 options, the second electron 5 options, the third electron 4 options. So overall we have 6 times 5 times 4. But also we have 3 factorial different permutations. And then we need to use 6 times 5 times 4 divided by 3 factorial. We get a total of 20 microstates. When we have 4 electrons in the 2p orbitals, again we use the same formula, we get 15 microstates. 5 electrons, we get 6 microstates. Well, you might have noticed that if we have 2 electrons versus 4 electrons, in both cases we have 15 possible arrangements or 50 microstates. That's not a coincidence. It's just because over here when we have 2 electrons, we simply arrange the 2 electrons, in the 2p orbitals. Here, when we have 4 electrons, we imagine arranging 2 holes, the opposite of putting electrons, holes into the p orbitals. Alright, so whether you are arranging 2 electrons or 2 holes in the 2p orbitals, you get 15 possible arrangements. Now let's look at the 15 microstates of the subshell of the carbon atom. So we have m sub L to be -1, 0, or 1. And we have m sub S for the electrons that can be -half or +half. So in the first row, we're looking at 2 electrons with the same value of m sub L. And one is alpha, the other is beta. In row 2, we put the 2 electrons into this column with m sub L equals 0. One alpha electron, one beta electron here. Same here, one alpha, one beta. But this is in the third column in which m sub L is plus 1. So these 3 rows correspond to a pair of electrons with the same value of m sub L. Now let's allow the 2 electrons to have different m sub L values. Then we can have the 2 electrons in this column, in the first and second column. So it can be alpha and alpha here, and also it can be alpha and beta here. And then alpha, 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 beta. Now we have beta, alpha, beta, beta. And then beta, alpha, beta, beta. And now over here again, we just list all possible arrangements. Alpha, 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 beta, beta, alpha, beta, beta. So no matter how you arrange these 2 electrons, you will end up with a total of 15 arrangements. That corresponds to the 15 microstates of the carbon atom or a silicon atom. If you are talking about silicon atom, well, it also has a partially filled p orbital. But for carbon, it's 2 p orbitals. For silicon, 3 p orbitals. Now, we are looking at a group of electrons, not just one electron. We're looking at a group of electrons, a group of 2 electrons. So we will use this method to determine the atomic terms. We sum up the m sub s value, we sum up the m sub L value. So physically, we are looking at the z components of the angular momentum and the z components of the spin. And we sum up the z components. We just study the z components for a group of electrons. Alright, let's sum it up. We have beta and alpha. So the sum is 0. Beta alpha, the sum is 0. Beta alpha, the sum is 0. Alpha alpha, the sum is 1. Alpha beta, the sum is 0. Now let's look at another example. This is beta beta, so the sum is -1. So we're going to sum up the m sub s. Over here we sum up m sub L. 2 electrons in the first column, so -1 -1 is -2. 2 electrons in the m sub L equals 0 column, so it's 0. 2 electrons in the +1 column, so it's going to be 2. Now over here, 2 electrons, one with -1, the other 0. The sum is -1. Same here, -1. Over here, you have -1 in the first column, +1 in the third column, so the sum is 0. So we just keep doing this. We get all those sums. Why do we do this? Because we now somehow will have information about the z component of the angular momentum of a group of electrons and the z component of the spin of a group electrons. When I say a group of electrons over here for carbon, it's just 2 electrons. But later you can see if we put 5 electrons in the d orbitals, and then that group of electrons, well, are equal to 5 electrons. So for a single electron in an atom, we know m sub L is from -L to L, m sub S is from -S to S. Alright, and because S, the lowercase s, can only be 1/2, so m sub S can only be -1/2 or +1/2. Now, when we look at atomic terms, for a group of electrons, we have the same rule, but different notation. For a group of electrons in an atom, we use uppercase m sub L. We use uppercase L. We use uppercase m sub S and uppercase S. Alright, so when L, the uppercase L, is 0, 1, 2, 3, 4, the corresponding symbols are uppercase SPD, FG. The 5 rows highlighted in yellow correspond to the 1D term, with L equals 2, S equals 0. I'm going to get back to the previous page to show you the 5 rows, in which L is 2, S is 0. So 1, 2, 3, 4, 5, 5 rows. L is 2. So M sub L can be -2, -1, 0, 1, and 2. Alright? And also we have information about this. When S is 0, M sub S can only be 0. Alright? 0, 0, 0, 0, 0. Alright, again we need to look at M sub S and M sub L at the same time. M sub S is just 0, 0, 0, 0, 0. Therefore S is 0. M sub L is a series of numbers from -2, -1, 0 to 1 and 2. So we have a combination of S is 0, L is 2. S is 0, L is 2. And over here we write 1D. D is the symbol for L equals 2. That's the atomic term for the 5 rows highlighted in yellow. And now you may ask about this superscript. This superscript over here is equal to 2s plus 1. So 2 times 0 plus 1 over here, it's just 1. The atomic term is 1D, and we have 5 microstates. The number of microstates is the multiplicity or degeneracy regarding L, and the multiplicity or degeneracy regarding S. When L is 2, we have 5 different values for M sub L. When S is 0, we have only 1 possible value for M sub S. And now we have over here 5 options times 1 option. We have 5 microstates. Alright, again, this superscript 1 is 2s plus 1. It's the so-called spin multiplicity. Alright, this is the spin multiplicity, and then the symbol that corresponds to L equals 2. We have also 9 rows not highlighted in any color. They correspond to the 3p term. When you see this p, that means L equals 1. When you see this superscript 3, that means S equals 1. Alright, so you just look up the symbol here, SPDF, correspond to L equals 0, 1, 2, 3. When L is 1, it's P. When it's P, L is 1. Over here, 3 is 2s plus 1, so that means S equals 1. We have a spin multiplicity of 3, because when S is 1, M sub S can be -1, 0, or 1. Now let's look at the 9 rows not highlighted. Alright, so you have 1 here, 1 here, and 1 here. Alright, in this 3 rows, you have MS equals 1, 1, and 1. Now M sub L, -1, 0, and +1. Alright, M sub S can also be 0. So let's find 3 zeros. 0, 0, 0. M sub L again can be -1, it can be 0, and it can be +1. Now M sub S can be -1, -1, -1, -1. M sub L can be -1 here, so correspond to this, and 0, and +1. So why 9 rows? Okay, it's just because M sub S can be -1, 0, or 1. M sub L can be -1, 0, or 1. So we have 3 options for M sub S, 3 options for M sub L. In total, we have 3 times 3. That means 9 options. And those 9 options are 9 microstates. They correspond to the 3p term. The angular momentum multiplicity is 3. The spin multiplicity is 3. So 3 times 3, we get 9. Finally, there's one last row, because we have 50 microstates minus 5 minus 9. We have one last row highlighted in green. That corresponds to the 1s term. When you see S, that means L equals 0. When you see 1 here, S is 0. Unfortunately, we use the same English letter S for the symbol that corresponds to the angular momentum, and the same letter S for the spin quantum number. So that's a little confusing and very unfortunate, using the same letter for different meanings over here. But again, let's just look at the previous page. Let's look at this. 0 as 0. M sub S can only be 0. M sub L can only be 0. That means S is 0 from here, and L is 0 from here. So the idea is very simple. We're gonna just make some rectangles. The rows and columns are possible values of M sub S and M sub L. First, the yellow rows, they form a 1 by 5 rectangle. 1, that means M sub S can only be 0. 5, that means M sub L can be 5 different values. And then we can make a 3 by 3, well, you can say square, but also it's just a specific form of rectangle, because M sub S can have 3 options from -1, 0 to 1, and then M sub L can be from -1, 0 to 1, so you have a second rectangle. The third rectangle is 1 by 1 rectangle. M sub S can only be 0, M sub L can only be 0. So really, you just try to group the 50 microstates into a number of rectangles. The rows and columns of the rectangles are the possible values of M sub S and M sub L. In this case, we can make 3 rectangles, therefore 3 atomic terms. And now we have the 3 atomic terms, and we can sum up the number of microstates: 5 for this 1D term, 9 for the 3P term, 1 for the 1S term. We sum it up, we get 50. Among the 3 atomic terms, 1D, 3P, and 1S, 3P has the lowest energy based on the following rules. There are 2 rules to determine which atomic term has the lowest energy. The lowest energy term has the greatest spin multiplicity, so you look for the largest 2s plus 1. Over here, this is 3, and then this is 1, this is 1. Obviously, 3p has the largest spin multiplicity, therefore the lowest energy. But if you have 2 or more terms with the same largest spin multiplicity, the one with the largest angular momentum quantum number L has the lowest energy. Alright, so sometimes you see 2 terms, both with the largest spin multiplicity, and then the second rule is gonna break the tie. You look for the largest L. Now, what is the physical meaning of the atomic terms? Well, an atomic term describes the angular momentum and electron spin of a group of electrons in the same atom. Remember, in general chemistry, we use the lowercase l and the lowercase s to describe the angular momentum and electron spin of a single electron that's not interacting with any other electrons. But when you have a group of electrons, such as in carbon, you have 2 electrons in the 3 2p orbitals, there's some interaction. And we need to take care of the interaction. And this is why we need to look at the total angular momentum, total spin of the group of electrons. But why don't we look at this L vector and S vector directly? Why did we look at M sub S and M sub L? Well, it's hard to sum up vectors. When you sum up vectors, you need to consider its z, x, and y components. You need to sum up all those 3 components separately. But if you just look at the z component of those vectors, the z component is just a scalar. So we can directly sum up the z components as if they are just numbers. And therefore, we like to just sum up M sub L for a group of electrons. We sum up M sub S for a group of electrons. It's just easier that way. And then after we sum up this m sub l, we get the z component of the group of electrons. Here we get the z component of the spin for a group of electrons. And we do know this kind of rule. M sub l has to be between negative L and L. For a group of electrons, we have the same rule. This m sub l can be from negative L to L. And if this uppercase L is 1, m sub l can be negative 1, 0, or 1. When L is 2, m sub l can be from negative 2 to 2, with a degeneracy of 5. The lowercase m sub s can only be negative half or positive half. But when you have a group of electrons, and then you look at the z component, well, the z component can be from negative n over 2 to positive n over 2, where n is the number of electrons in that subshell. So sometimes s can be even 1, then m sub s can be negative 1, 0, or 1. So we did look at the carbon atom as example, and we saw this kind of case. Carbon has a 3p atomic term, and 3p, that means 2s plus 1 is 3, s is equal to 1. The z component can be negative 1, 0, or 1, because we are looking at a group of 2 electrons. Also, s can be even more than 1. It can be 1.5. Then the z component can be negative 1.5, negative 0.5, 0.5, or 1.5. It's called a spin quartet, because we have 4 possible values for m sub s. Now let's look at the experimental data for carbon again. The first 5 energy levels of the carbon atom are 0, 1643, 10,000, 21,000 wave numbers. One wave number, well, you can just multiply this by h and c, the Planck constant, and speed of light to get joule. It's this much. It's about 2 times 10 to the power of negative 23 joule, or 12 joule per mole, or 0.012 kilojoule per mole. So it gives you a kind of idea about how much those relative energy values are. You just multiply all those by 12 joule per mole, or 0.012 kilojoule per mole. Alright, we can assign those relative energy levels, the first 3 to 3p, and then 1d and 1s. You can see 1d and 1s have higher energy than 3p. 3p has the lowest energy among all, because 3p has the greatest spin multiplicity. Alright, and now, why does this 3p atomic term have 3 energy levels, 0, 16, and 43? Alright, very small energy spacing. You can see you need to multiply this 16 by this. It's roughly going to be 0.2 kilojoule per mole. 43 times this, it's only 0.5 kilojoule per mole. Really small energy spacing. Well, it's just because over here within this 3p atomic term, you have angular momentum, you have electron spin. Alright, angular momentum, that's the group of electrons rotating about the nucleus, right? And the spin, that's the rotation of the electrons about its own axis. So 2 different circular motions. And we learned that when we have a circular motion of a charged particle, such as an electron, we create a current loop, an electric current loop, and that creates a magnetic moment. Alright, that creates a magnetic moment. And when you have angular momentum and spin, well, there are 2 different magnetic moments, and they can interact with each other. Okay, they can be aligned in parallel or anti-parallel, and they can be aligned in a way that they are perpendicular to each other. So between these 2 magnetic moments, there can be attraction, repulsion, or no interaction overall. So that's why this 3p atomic term splits into 3 energy levels. The lowest one, well, this is when the 2 magnetic moments attract each other. Over here, when there's no interaction, and over here, of course, when the two magnetic moments have repulsion between each other, then you have slightly higher energy. So now we have to create another quantum number J. J is from L minus S all the way to L plus S. So J is 0, 1, or 2 for the carbon 3p atomic term. Because when you see 3p, P means L is 1. When you see this 2s plus 1 is 3, S is 1. So when L is 1, S is 1, well, L minus S is 0, L plus S is 2. So we have three possible values for J. J can be 0 or 1 or 2. They correspond to these three different energy levels. Over here, J is just 0. Over here, J is 1. Over here, J is 2. Now, the coupling of the orbital motion and the spin motion of the electrons is denoted by the quantum number J. The orbital motion creates a magnetic moment. The spin motion also creates a magnetic moment, and these two magnetic moments may attract or repel each other, or there's no interaction. Three different options for the 3p atomic term of carbon. Now this J can be from the difference between L and S to the sum of L and S. For the 3p atomic term, J can be 0, 1, or 2. The energy levels now becomes this. L is the angular momentum. 2s plus 1 is the spin multiplicity. And J denotes the coupling between the orbital motion and the spin motion. And again, J has a range from the difference between L and S to the sum of L and S. When the subshell of interest is less than half filled, for example carbon, the energy level written this way, with a lower J value has lower energy. The level with a higher J value has a higher energy. So for carbon, it's less than half filled, so 3p sub 0 is the lowest energy level. And again, the relative energy levels of 3p0, 3p1, and 3p2 are 0, 16, and 43 wave numbers. Now let's look at oxygen. The atomic terms of the oxygen atom are the same as those of the carbon atom, because in the oxygen atom we have 4 electrons occupying the 3 2p orbitals, which is equivalent to having 2 holes or 2 vacancies occupying the 2p orbitals. And the arrangements of 2 holes correspond to the arrangements of 2 electrons. So for oxygen, we also have the 3 atomic terms. The lowest energy atomic term is 3p, followed by 1d and 1s. But there's a difference between the oxygen and carbon atoms. Well, for oxygen, the 3p2 has the lowest energy. For the carbon atom, 3p sub 0 has the lowest energy. Well, if the subshell of interest is more than half filled, then this energy level with a lower J has a higher energy. The level with a higher J has a lower energy. The main reason is when we are looking at the atomic terms of oxygen, we are looking at not the 2 electrons. We are arranging 2 holes or 2 vacancies in the 2p orbitals. So that's just the opposite to arranging 2 electrons in the 2p orbitals. So that's why regarding the J value for oxygen and for carbon, we have 2 different rules. When the subshell is less than half filled, then lower J value means lower energy. When the subshell is more than half filled, well, A lower J value means higher energy. So what if it's exactly half filled? When it's exactly half filled, well, you'll see the value of L is going to be 0. And when that's the case, when L is just 0, J can only be one value. J is equal to S, the spin quantum number. So in that case, we do not have to rank the energy levels with respect to J, because J can only adopt one value when the subshell is exactly half filled. So for example, if you have p orbitals, if it's exactly half filled, it's going to be m sub L will be minus 1, 0, and 1. So the sum is going to be just 0. Now let's look at the quantum number of the Z component of J. So what is J? J is the coupling of the orbit motion and the spin motion of a group of electrons. Now let's look at its Z component. Its Z component can be from negative J all the way to J. So also there's a multiplicity. The values of m sub J can be different. There are this many possible values, 2J plus 1 possible values, from negative J to positive J. When you place such an atom in an external magnetic field, each energy level with a J value will further split into 2J plus 1 microstates. So all those electrons will be kind of aligned in a way that interact with the external magnetic field. And this m sub J can be like from negative J to positive J. So all different kind of ways in alignment with the external magnetic field. So when m sub J is 0, that means, well, the Z component is just 0. There's no interaction with the external magnetic field. And then you can have minus J or plus J. So you can have like repulsion or attraction caused by the external magnetic field. So now in that case, with an external magnetic field, each energy level may split into 2J plus 1 microstates. For example, 3p0 split into just one state, 3p1 splits into 3 states, 3p2, this J is equal to 2, splits into 5 states in a magnetic field. In total, we have 1 plus 3 plus 5, that's 9 microstates, correspond to the 9 microstates in the 3p term. The number of states for an atomic term can be calculated in two different ways. One way is we sum up all those 2J plus 1. So J is 0, 1, and 2. So 2J plus 1 is 3, well, 1, 3, and 5. Sum it up, we get 9. Another way is to look at the value of L and S. When you look at 3p, L is 1, S is 1. So basically you just do 3 times 3. It's also 9. Here's a example problem 20.7.1. Calculate the number of microstates included in the 4F term. In the 4F term, L is 3, S is 1.5. So L minus S is 1.5, L plus S is 4.5. So J value can be from 1.5 to 4.5. Here they are 1.5, 2.5, 3.5, 4.5. Now we're going to sum up the 2J plus 1. So 1.5 has a 2J plus 1 of 4, and this corresponds to 6, this corresponds to 8, and this corresponds to 10. So we can sum up the values of 2J plus 1, which is 4 plus 6 plus 8 plus 10, that's 28. Also, we can just look at the term symbol. 4, we plug in 4 here, that's the spin multiplicity. And F, that means L is equal to 3, 2L plus 1, that's 7, 7 times 4, we get 28. So using these two equations, we should get the same number. Now let's look at a table of the number of microstates and the atomic terms for various subshells with the lowest energy atomic term in bold font. So what if you have only one electron in the p orbital? Well, we have 6 options, right? So 6 microstates correspond to the 2p atomic term. Okay, when you see p, that means L is 1. When you see 2s plus 1 is 2, s is 1/2. Alright, s is 1/2, L is 1. The number of microstates is just 2 times 3, that's 6. P2, P4. Well, we have 2 examples, carbon and oxygen. 15 microstates. The 3 atomic terms are 1s, 1d, and 3p, with the lowest atomic term in the bold found. Now 3 electrons, 20 microstates. Well, it's just 6 times 5 times 4 divided by 3 factorial. We get 20. And we can group all these 20 microstates into 3 atomic terms. Over here, this one has the greatest spin multiplicity and therefore lowest energy. 4s has the lowest energy. And now let's count the number of microstates. Over here, the number of microstates is just 4. So 4 times 1 is just 4. Here it's 2 times 5, it's 10. 2 times 3, that's 6. 6 plus 10 plus 4, that's indeed 20. What if you have only one d electron, 10 options? It's 2d atomic term. The multiplicity for this d term is 5. The spin multiplicity is 2, so 2 times 5, that's 10. For d2, we have 45 microstates because the first electron, 10 options. The second electron, 9 options. 10 times 9, 90. 90 divided by 2 factorial, 45. Again, it's just because electrons are indistinguishable. When we have 2 electrons, we have 2 factorial different permutations. We need to divide that, so we get 45. And now we have we can group this 45 microstates into 5 atomic terms: 1s, 1d, 1g, 3p, 3f. So there are 2 rules to determine which term has the lowest energy. First, look for the largest spin multiplicity, so 3. We have a tie here, so how do we break the tie? Now look at the largest L. So for the F term, L is 3. For the P term, L is 1. I'm going to go with 3F, with the lowest energy atomic term. Alright, so if we have 3 or 4 or 5 d electrons, it gets just more complicated. It's doable, it's really tedious if we have 5 electrons occupying d orbitals. The number of microstates is 10 times 9 times 8 times 7 times 6 over 5 factorial. We have 252 microstates. And then we can make 8 atomic terms. Each atomic term corresponds to a rectangle with rows and columns that are the values of m sub s and m sub l. And among these 8 atomic terms, we can easily identify the lowest energy term, 6s, with the largest spin multiplicity. Chapter 20. Many electron atoms. Section 20.8. Atomic term symbols for the D2 electron configuration. The total number of microstates is 10 times 9 over 2 factorial, which is 45 for the D2 electron configuration. This is because when we place the first electron in the 5 different d orbitals, there are 10 options. The second electron has 9 options. 10 times 9 is 90. But there are 2 identical permutations for the 2 electrons. Therefore, we have 90 over 2, 45 microstates. Now in this table, we will just look at the sum of the m sub l values of the 2 d electrons. When we have a d electron, the lowercase m sub l can be from -2, -1, 0 to 1 and 2. So we have these 5 values for the first electron, these 5 values for the second electron, and we will sum up the m sub l values for the 2 electrons. Let's look at this cell. -2, -2. So together it's -4. And because these 2 electrons both have a value of m sub l being -2, -2, they must have different spin quantum number. Therefore, they have to be 1 alpha and 1 beta. Only 1 microstate here. So you can see just -4 over here with just a single occurrence. This means, well, the total m sub L is -4, and we can only have one microstate with such a value. Now look at this cell. You see -3, -3, -3, -3. Why is that? Well, over here we see m sub L for one electron is -2. For the other electron it's -1. So look, this m sub L values are different. What does that mean? That means, well, their spin numbers can be the same. They can also be different. Now we have 4 different situations. We can have alpha alpha, beta beta. We can have alpha beta plus beta alpha. We can have alpha beta minus beta alpha. So this is the singlet state. And these 3 together is a triplet state. A total of 4 arrangements or 4 microstates. Since we have 4 different microstates, each with a sum of m sub L being -3. So I'm writing -3 4 times. Now let's look at this cell. -1, -1. Same m sub L. Therefore, the spin must be different. We have only one possible microstate over here, which is just 1 alpha, 1 beta, both occupying this m sub L orbital. So again, you see the trend. If the value of m sub L of one electron is different from m sub L value of another electron, we have 4 options or 4 microstates. All right, like those cells in the lower triangle. What if the m sub L of one electron is the same as m sub L of the other electron? Then you have to have 2 different spin numbers. That means the 2 electrons must be paired with 1 alpha and 1 beta. Therefore, there's only 1 microstate in the diagonal cells. All right, again, if m sub L is 2 for one electron and also 2 for the other electron, well, these 2 electrons must have different spins, alpha and beta. Now we have actually a total of 45 numbers entered. So 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, that's 40. And then 1, 2, 3, 4, 5, 45. 45 microstates have been specified in this table. Now we're going to group those 45 microstates into atomic terms. First, let's look at all those numbers in red. If you look at those numbers in red, they correspond to, well, m sub s equals 0. So it's just alpha beta minus beta alpha, the singlet. Singlet spin, okay? They are all singlet spin. The spin multiplicity is just 1. And now let's look at m sub L, the sum of the individual values of lowercase m sub L of both electrons. It can be -4, -3, -2, -1, 0, 1, 2, 3, 4. So now we have a series. This m sub L can be from -4 to 4. What does that mean? That means L is 4. Now let's look at m sub s. In all cases, m sub s is 0. It's the singlet state. And then the atomic term is 1g. G means L is equal to 4. And the 1 here, that means a spin singlet. 2s plus 1 is 1, so s is 0, and it does make sense over here. M sub s is just 0. It has to be the singlet state. Okay, we assigned a total of 9 microstates to the 1g atomic term. Now we have 45 minus 9, 36 microstates left in the table. So we have 36 numbers in this table. We will further group those microstates. Now let's look at the numbers in yellow. We have 21 numbers in yellow. You can see over here we have 3 identical values, -3, -3, -3. So that means we have a triplet here. The spin quantum number can be -1, 0, and 1. What about m sub L? Well, it can be -3, -2, -1, 0, 1, 2, 3. So we have a series numbers for m sub L from -3 to 3. How about ms? from -1 to 0 to 1. We have a spin multiplicity of 3. You see 3 numbers in each cell. And we have a angular momentum multiplicity of 7 because, well, L is 3. So M sub L can be -3, -2, -1, 0, 1, 2, 3. 7 times 3, we have 21 microstates. They correspond to the 21 numbers highlighted in yellow. And they belong to the 3F atomic term. So when L is 3, the symbol is F. And over here we can see M sub S can adopt 3 different values. So the spin multiplicity is 3. And then we further remove those microstates assigned to the 3F atomic term. Now we have 15 microstates left. This 15. And by looking at this 15, well, actually, if you are familiar with the P2 microstates, 15 microstates in P2, so they can be just assigned similarly. It's just 1S, 1D, and 3P. But still, let's work on it. First, let's look at those green numbers. -2, -1, 0, 1, and 2. Alright, and those are the singlets. Alright, so M sub L is from -2, -0, -1, 0, 1, 2. And M sub S can only be 0 for the singlet spin. And we have this 1D atomic term done. And after we remove these 5 green numbers, we will have a total of 10 microstates left. We have only 10 microstates left in this table. Now let's look at the 9 numbers in blue. So 1, 2, 3, 1, 2, 3, 1, 2, 3. That means we have a spin quantum number of -1, 0, and 1 over here. M sub L can be -1 in this cell, 0 in this cell, and 1 in this cell. We have a series M sub L values from -1, 0 to 1. And also M sub S is -1, 0 to 1. So this is a triplet spin. Alright, so that's why we have 9 microstates assigned to the 3P atomic term. We look at the 3P, L is 1, S is 1. When L is 1, M sub L can be -1, 0, and 1. When S is 1, M sub S can be -1, 0, and 1. So we assign this 9 microstates to the 3P atomic term. Finally, there's a 1 number left, which is in purple. So if you look at this number, M sub L is 0 plus 0, which is 0. And we see only 1 0 here, 1 occurrence of 0 here. That means we have a singlet spin. S has to be 0. And then we have the final atomic term, which is just 1S. So when you see this 1S, this S means L is 0, M sub L can only be 0. When you see this 1, that means 2 times the spin quantum number S plus 1 is 1, S is 0, M sub S can only be 0. There's only one option for the spin. Again, you know, this 0 corresponds to the 1S atomic term. The 9 numbers in blue belong to the 3P atomic term. So now we group all 45 microstates into the 5 atomic terms. The red ones, there are 9 numbers in red. It's just 1G. 21 numbers in yellow. That's 3F. We have 5 numbers in green, 1D. 9 numbers in blue, 3P. 1 number at last in purple, that's just 1S. Again, we can just use this table to derive the atomic term symbols for the D2 electron configuration. Let's review this. We have 45 numbers in this table that correspond to 45 microstates. And over here, if you look at this cell, that means the 2 electrons both have a M sub L equals -2, -2. So the sum is -4. And because these 2 electrons have the same value of M sub L, they must have a different spin. So it's going to be a singlet. and that's why I have this -4 appearing only once in this cell, a singlet. What if the m sub l values for the two electrons are different? And then we can have 4 different spin scenarios: alpha alpha, alpha beta plus beta alpha, beta beta, alpha beta minus beta alpha. 4 options. The first 3 are the triplet spin. The last one is a singlet spin. So we have 4 numbers here, 4 numbers here in the lower triangle. In the lower triangle, the 2 values of m sub l are different. In the diagonal, the m sub l values are the same. So you have only one possible spin state, which is a singlet. And in the lower triangle, you have a triplet plus a singlet. So 4 options regarding the spin. So you have this -3 appearing 4 times, -2 appearing 4 times, 4 times. This number also 4 times. Okay, and in total you can count. We have 45 numbers in this table, and then we group this 9 red numbers to 1G, 21 numbers in yellow to 3F, 5 green numbers in 1D, and 9 numbers in blue to 3P. Finally, this number left in 1S. Similarly, if you are looking at the F2 electron configuration, it's actually fairly easy. You can just imagine we need to have a bigger table than this. This is 5 by 5 table. For this F2 electron configuration, well, we need a 7 by 7 table. We need to have this m sub l from -3, -2, -1, 0 to 1, 2, 3. And over here, we need to have values from -3 to +3. So we need a 7 by 7 table. And we also will have like diagonal cells and lower triangle cells. And we fill them up and then group them into the atomic terms. And you will see we just need to have 2 additional atomic terms. So remember, for this D2 we have 1G, right? So we have 1G, 3F, 1D, 3P1s. It's just beyond 1G. You need a letter H. H is after G. You need a H, and then you need a spin multiplicity of 3. And then after H it's I, so you need 1I. So you just need to write out 2 more atomic terms. After G it's H and I. And then you can see the trend over here. It's 1, 3, 1, 3, 1, 3, 1. So really you just need to imagine we just need to have 2 more columns, 2 more rows. They also have similar numbers like this. It's just, you know, if you have F2 electron configuration, it starts with -3 and -3. So you will have at most -6 in the diagonal. -6, -2, -6, -4, -2, 0, 2, 4, 6 in the diagonal. And then you have off diagonal triangle. So just because of that, you will get additional atomic terms such as 3H and 1I. And also we can easily determine G2. We just need 2 more atomic terms, 3K and 1L. Know that we know it's HI, J, K, L, but J is skipped just because there's no corresponding letter J in the Greek alphabet. So usually we just look at the letters in alphabetic order after SPDF. So first SPDF, and then alphabetic order. That means we have G, H, I, and then skip J, and then K and L. And then if you look at the spin multiplicity, it's going to be 1, 3, 1, 3, 1, 3, 1, 3, 1. Alternately, due to the arrangement of this kind of table. Chapter 21, Molecular Orbital Theory, Section 21.1, the Schrodinger equations of molecules. The wave function of a molecule that consists of m nuclei and n electrons can be written as a function of the coordinates of all these electrons and the coordinates of all nuclei. We use lowercase r1, r2 vectors to specify the positions of the electrons. We use uppercase R1, R2 vectors to specify the positions of the nuclei. So those vectors are three-dimensional vectors. And also, in this lowercase r1, r2, all the way to rn, we should also include the spin coordinates for the electrons. Now, the wave function of all electrons and all nuclei can be too complicated to solve. Therefore, for convenience, Born and Oppenheimer proposed an approximation to separate the motions of the electrons from the motions of the nuclei. Mathematically, it's this. The wave function of a molecule can be written as the product of a wave function of electrons and a wave function of nuclei. In the wave function of electrons and the so-called Born-Oppenheimer wave function of electrons, the coordinates of the nuclei are fixed. The Born-Oppenheimer approximation is reasonable because electrons move much faster than the nuclei. When the nuclei change their positions, it takes no time for the electrons to move accordingly. Therefore, the very slow motions of the nuclei can be separated from the motions of the electrons. In the Born-Oppenheimer approximation, the coordinates of the much heavier nuclei are considered fixed, while the coordinates of the much lighter electrons are dynamic. The Born-Oppenheimer approximation separates the motions of the electrons from the motions of the nuclei. Mathematically, the wave function of a molecule is the product of the wave function of all electrons times a wave function of all nuclei. And then the total energy of the molecule is the sum of the energy of the electrons and the energy of the nuclei. When the electronic energy is calculated, the nuclei's positions are held constant for convenience. The nucleus electrostatic repulsion is calculated assuming the nuclei are particles instead of waves. They are particles with fixed positions, and therefore the repulsion between nucleus A and nucleus B is simply Za times Zb over Rab. Za and Zb are the nuclear charges. Rab is the distance between these two nuclei, both at specific positions. When calculating the kinetic energy of the nuclei, the electrons are assumed to move with the nuclei instantaneously, so that the very slow motions of the nuclei have no impact on the electronic energy. The kinetic energy of the nuclei is approximately the sum of the translational, rotational, and vibrational energies of the molecule. At a specific temperature, we can estimate the total translational, rotational, and vibrational energies of all molecules, assuming the Boltzmann distribution. So the equation is this: the kinetic energy of the nuclei is the sum of the translational energy plus the rotational energy plus the vibrational energy. And over here, this E denotes the kinetic energy of the nuclei. The kinetic energy of the nuclei being excluded from the Bornheimer wave function of a molecule. The total energy operator is approximately just the Born-Oppenheimer Hamiltonian. So H is approximately H sub B hyphen O, Born-Oppenheimer. We have the kinetic energy operator of all electrons. We have the attraction felt by all electrons. We have electron-electron repulsion, and also we have the nucleus repulsion. So over here, we can see this I is from 1 to N, A is from 1 to M. So this way we can enumerate all electrons and all nuclei. Here we also need to look at all electron repulsion terms. But you can see this I is from 1 to n, but J is from a number greater than I to n. Why do we need to do this? Well, if we write J is also from 1 to n, that means we will have to include a term. That's 1 over R11 and 1 over R22. That does not make sense because electrons do not repel themselves. So you cannot include 1 over R11 in this Hamiltonian. And also, if we just write J is different from I, there's another issue. If J is just different from I, we will have to include a term which is 1 over R12 and then 1 over R21. That way we count the repulsion between electron 1 and electron 2 two times. So to avoid the double counting, we have to say J must be greater than I. So when I is 1, J is from 2 to n. When I is 2, J is from 3 to n. And again, this is to avoid the erroneous inclusion of self-repulsion and to avoid double counting the repulsion between two electrons. For the same reason, when we look at the repulsion between the nuclei, A is from 1 to m, but B has to be greater than A. And this way, we avoid double counting. We avoid the repulsion between a nucleus and itself. For a molecule with fixed nuclear positions, this is simply a constant. We can just get the positions of all nuclei and compute this really easily. This does not involve any quantum behavior. So we can separate this from the electronic energy. The electronic energy is equal to the Born-Oppenheimer energy minus the nucleus repulsion. So the electronic Hamiltonian is simply the kinetic energy operators for the electrons, the attraction operators for the electrons, and the electron repulsion operators. The operator of the electronic energy includes the nucleus repulsion. Again, over here we have kinetic energy operators, we have attraction operators, we have repulsion between electrons. However, in many other textbooks, the electronic Hamiltonian also includes the nucleus repulsion for historical reasons. But precisely, we want to say the Hamiltonian of electron should not include the nucleus repulsion. After the nucleus energy being separated, the Schrödinger equation of electrons become this. We apply the electronic Hamiltonian to the wave function for electrons. We get electronic energy times the wave function of the electrons. And now, given the nucleus positions, we get the Born-Oppenheimer energy, which is the sum of the electronic energy and the nucleus repulsion. What about the total energy of the molecule? And then we need the electronic energy, the nucleus repulsion, and also the kinetic energy of the nuclei. The kinetic energy of the nuclei can be calculated separately by summing up the total vibrational, rotational, and translational energies of the molecule. And therefore, the total energy of the molecule can be expressed in this mathematical equation. The total energy of a molecule is the electronic energy plus the nucleus repulsion, and then plus the kinetic energy of the nuclei, which includes the vibrational, rotational, and translational motions of the molecule. Here, this electronic energy is the sum of the kinetic energy and potential energy of all electrons. Chapter 21, Molecular Orbital Theory. Section 21.2. the H2 plus molecule. To solve the shorting equation for the electrons in a molecule, we may construct a trial wave function using the LCAO-MO method and then minimize the trial energy. The essence of the LCAO-MO method is that the molecular orbitals are the linear combinations of the atomic orbitals. MO denotes molecular orbitals, LCAO denotes the linear combinations of the atomic orbitals. For example, the MOs in the H2 plus or H2 molecules can be expressed as this: a linear combination of, well, over here this is just 1s orbital of hydrogen A, this is 1s orbital of hydrogen B, when we have two nuclei A and B. In H2 plus we have only one electron. We can use this diagram to describe this H2 plus molecule. Two nuclei, one electron. The distance between the electron and nucleus A is Ra. The distance between the electron and nucleus B is Rb. The distance between A and B is Rab. Now, what are this C sub A and C sub B? Those are molecular orbital coefficients. Those are just numbers. They put a weight on those atomic orbitals. This 1s A orbital is 1 over square root of pi times e to the power of negative Ra in atomic units. And phi for 1s B is 1 over square root of pi times e to the power of negative Rb. Again, these two equations are in the atomic units. And remember, the fundamental atomic units are this: the charge of electron is 1, the mass of electron is 1, h bar is 1 over 4 pi epsilon 0. This is electric force constant, has a value also of 1 in atomic units. And again, H2 plus contains 1 electron and 2 nuclei. The shorter equation is this: H psi equals E psi. H consists of the kinetic energy operator for the electron and the attraction this electron feels from nucleus A, the attraction the electron feels from nucleus B, and over here this is uppercase R sub AB. This is the repulsion between the two nuclei. We did neglect the kinetic energy of the nuclei because the kinetic energy of the nuclei is much smaller than the kinetic energy of the electron. Now let's look at the shorter equation for H2 plus. So we have H psi equals E psi. H is the kinetic energy of the electron and the potential energy of the electron plus the nucleus repulsion. We apply that to the wave function, we get the energy times the wave function, after we neglect the kinetic energy of the nuclei. Since the distance between the two nuclei is held constant in the Born-Oppenheimer approximation, we have a simpler shorting equation that focuses on the electronic energy. Over here we have the electronic Hamiltonian applied to psi. H psi equals E psi. This E is the electronic energy. The electronic energy is the Born-Oppenheimer energy minus the nucleus attraction. We simply removed this nucleus attraction from the shorting equation. Now let's look at the LCAO method, linear combination of atomic orbitals. So we express the wave function of the molecular orbitals of this H2 plus molecule to be a coefficient times the wave function of 1s A, and then a coefficient times the wave function of 1s B. So in this equation, well, 1s A is e to the power of negative Ra, 1s B is e to the power of negative Rb. R sub A and R sub B are the distances between the electron and the two nuclei, nucleus A and nucleus B. So R sub A is the square root, over here the sum of 3 squares. This is x minus the x of nucleus A, y minus the y of nucleus A, z minus the z of nucleus A. And also we have a similar expression for R sub B. So now we have two nuclei. We cannot by default put the both nuclei at the center. None of these two appear at the center now. So usually we treat over here just the midpoint between the two nuclei as the center of the system. Alright, so that's why we have R sub A, R sub B, in this kind of format. Again, the uppercase X, Y, Z are the Cartesian coordinates of the nuclei. The lowercase X, Y, and Z are the Cartesian coordinates of the electron. So over here we also have the expression of the uppercase R, which is the distance between the two nuclei, the square root of the sum of these three squares. Again, when we try to solve the Schrodinger equation for the system, usually we'll just assume this A and B have fixed positions. So this uppercase X, Y, and Z for nuclei A and B are just fixed values. Again, the Schrodinger equation for the electron in the H2 plus molecule is this. We have the electronic Hamiltonian, the kinetic energy of the electron, and also the potential energy felt by the electron. We apply this H to psi, we get E psi. This E is the electronic energy. The wave function of the electron is a linear combination of two atomic orbitals, e to the power of negative Ra, e to the power of negative Rb. Don't worry about the normalization factor. And over here you can see if we move this nucleus B all the way to the moon, and then we have just a hydrogen atom plus another nucleus on the moon. And over here this wave function is just 1sa, e to the power of negative Ra. Now if we move this nucleus A to the moon, then we have a simple hydrogen atom plus another electron on the moon, and the wave function is e to the power of negative Rb. So we're making two different cases, extreme scenarios, to get the over here the basis for the linear combination. So now the molecular orbital is a linear combination of these two atomic orbitals, e to the power of negative Ra, e to the power of negative Rb. And again, C sub A and C sub B are molecular orbital coefficients. And because of the symmetry of this molecule, we know the squared modulus of psi should comprise equal weights of 1sa and 1sb. And therefore, Ca squared is equal to Cb squared. So Ca is plus minus Cb. When Ca is equal to Cb, well, these two 1s atomic orbitals are in phase. The formed MO is a constructive interference of the two AOs. And this MO is symmetric with respect to the center of the molecule. And it's the so-called sigma G bonding orbital. G is the first letter for gerade or G symmetry. Gerade, I think, is a German word. That means symmetry or even function. Now we have Ca that can be Cb or minus Cb. When Ca is equal to negative Cb, the two 1s atomic orbitals are out of phase. The formed MO is a destructive interference of these two atomic orbitals. And this MO is antisymmetric with respect to the center of the molecule. And we say this is a sigma U star antibonding orbital. U is the first letter of ungerade in German. Ungerade means odd function, anti-symmetric function. Sometimes we just use U to denote ungerade. This star actually means antibonding. So remember, we in the past we used star to denote the complex conjugate, but here, well, this star has a different meaning. So when you see sigma U star, it means this is anti-bonding sigma orbital with a U symmetry or Ungerade symmetry. Oh, I forgot to show you the shapes of sigma G and sigma U star. Over here we have constructive interference between the two atomic orbitals. And over here we have destructive interference between the two atomic orbitals that are out of phase. So in the middle we have a nodal surface. To normalize the sigma g bonding orbital with this kind of form, we just need to integrate its squared modulus. We expand the squared modulus. We have this 1sa squared, we have 1sb squared, and also we have cross terms. Since this is normalized, so we have 1 and 1 here. Together we have 2, and over here we have another integral, so we just combine this 2 and put it here, and we have integral here. We copy that here. And now we define the overlap integral S sub AB between the two atomic orbitals. S sub AB is defined to be the integral of 1s A orbital times 1s B orbital. And therefore, the normalization factor for the sigma G bonding orbital becomes 1 over the square root of 2 plus 2 times SAB. So over here, this is 2 times SAB, and therefore this CG squared is 1 over 2 plus 2 times SAB, and therefore CG is 1 over the square root of 2 plus 2 SAB. And then the molecular orbital becomes this. Now this is normalized. It's 1 over the square root of 2 plus 2 SAB, and then over here we have the constructive interference between these two atomic orbitals, and you can see this MO with a constructive interference in the middle. This is in the middle. We have a overlap between the two atomic orbitals, and this integral S sub AB is called the overlap integral. This integral is always positive. Just because this 1sa function is always positive, this 1sb function is always positive. To normalize the sigma u antibonding molecular orbital, which is a coefficient, times the difference between the two atomic orbitals, again we just need to integrate the squared modulus of this antibonding molecular orbital and set it to 1. Now we expand this wave function squared. We have 1, 2, 3 terms. This integral is just 1. This integral is just 1 because the 1sa wave function is normalized. The 1sb wave function is also normalized. But also we have a cross term over here. Therefore, cu squared times 2 minus this integral of 2 times 1sa times 2 1sb is equal to 1. And we defined S sub AB as the integral of the 1sa orbital times 1sb orbital. And therefore, this cu squared times 2 minus 2 times the overlap integral S sub AB is just 1. Therefore, the coefficient in front of this linear combination in the antibonding orbital is 1 over the square root of 2 minus 2 SAB. And then we have the MO for this antibonding orbital. It's 1 over the square root of 2 minus 2 SAB, and then times the 1sa wave function minus the 1sb wave function. Again, the overlap integral S sub AB, this integral of 1sa and 1sb is always positive. It's just because you can see 1sa is the exponential function, which is positive. 1sb is also a positive exponential function. Therefore, we integrate a exponential function, and over here d tau is the volume element. Now, if we set r sub a equals r sub b, this wave function becomes 0. Because when r sub a is equal to r sub b, we have these two wave functions with the same value, so they cancel, and this side is 0 in the middle. The nodal plane of this antibonding orbital is defined this way. When this is 0, we have a nodal plane, and the nodal plane is right here in the middle between the two nuclei, right in the middle. The normalized sigma G bonding orbital and the normalized sigma U anti-bonding orbital MOs are this too. Sigma G or psi of G as the wave function is 1 over the square root of 2 plus 2 times the overlap integral, and then times the sum of 1sa and 1sb. The antibonding orbital is 1 over the square root of 2 minus 2SAB, the overlap integral over here, times the difference between the two atomic orbitals. We can use these two trial wave functions to calculate the trial molecular orbital energy. So first, let's look at the trial energy of the bonding orbital. with the G symmetry or Gerarder symmetry. And it's pretty simple. We just use partially 4. It's the integral of, over here we have the wave function. Actually, this should be the complex conjugate of the wave function, but since these two wave functions are real functions, so the complex conjugate of this psi of g is itself. And over here we apply the Hamiltonian to the function, and then we can determine this simplified expression for the trial energy. We take this part and this part out. We have 1 over 2 plus 2 times the overlap integral, and then in the middle we have this equation. We can simplify this equation by using shorthand notations. We can do 1sa times h over 1sa applied to 1sa, that's HAA, and then we have this 1sa orbital times the Hamiltonian applied to 1sb, that's HAB, and then we have HBA, which is this times this, and also we have HBB, which is this times the Hamiltonian applied to 1sb. So we have 1, 2, 3, 4 terms over here. HAA is the integral of 1sa and then Hamiltonian applied to 1sa. So really, this is just the energy of the 1s electron in the hydrogen atom. It's negative 1/2. HBB is also negative 1/2. Just imagine you have a hydrogen atom B that includes the nucleus B plus electron. The energy is negative 1/2. Now HAB and HBA, all right, they are just the integral of 1sa, and then over here Hamiltonian applied to 1sb, and here we have 1sb and then Hamiltonian applied to 1sa. So we got 2 integrals as the cross terms. These two are the same because of the symmetry of this molecule, and these two values will be between 0 and negative 1/2. And because of the symmetry in this H2 plus molecule, we have HAA equals HBB, HAB equals HBA. Also, the physical meaning of HAA is just the energy of the electron in the hydrogen atom A. HBB is the energy of the electron in the hydrogen atom B. So these two are both equal to negative 1/2 atomic units. The trial energy of the sigma G or psi G bonding orbital is this. We have 1 over 2 plus 2 SAB, and then these 4 terms we have negative 1/2 here, negative 1/2 here, and then 2 cross terms. So since HAA equals HBB, we can just write it this way. HAB equals HBA, we can write it this way. So overall, this trial energy for the sigma G bonding orbital is HAA plus HAB over 1 plus SAB. Similarly, the trial energy for the sigma U NT bonding orbital is this: HAA minus HAB. On the bottom, we have 1 minus SAB. So we can compare the trial energy for the sigma G orbital and the trial energy for sigma U NT bonding orbital. So we just need to change this plus sign to minus sign, this plus sign to minus sign. This trial energy for sigma G bonding orbital is more negative than the energy of the electron in the hydrogen atom. So it's more negative than negative 1/2, and that's the reason when H and H plus approach each other from a infinite distance, the energy of the electron keeps decreasing at a rate faster than the increasing of the ion repulsion. So overall, the energy of the entire system decreases, and that's why you can form a bond between the hydrogen atom and a H plus ion. A bond is formed when these two approach each other. Now let's look at this trial energy for the antibonding orbital. It's less negative than the energy of the electron in the hydrogen atom. So it's less negative than negative 1/2. That means if you put the electron in the antibonding orbital, well, it's unfavored energetically. We can define the energy shifts of the two molecular orbitals from the AOs. Alright, so it's delta E sub G, delta E sub U. So now let's look at the molecular orbital diagram for H2 plus. So we have on the left hand side the hydrogen atom with negative 1/2 atomic unit energy. Over here we have H plus, no electron. All right, and then let's allow this to interact. We form two MOs. One is bonding orbital, one is anti-bonding MO. The bonding orbital has a G symmetry or Garrotter symmetry, and this sigma U is the anti-bonding orbital with U symmetry or one Garrotter symmetry. This star means anti-bonding. In this sigma G orbital, we have overlap between these two atomic orbitals in the middle. Over here, when we look at the anti-bonding orbital, we have a nodal surface right in the middle between the two nuclei. Now you can see, well, this sigma G has lower energy than the atomic orbital energy. Sigma U has an energy higher than the atomic orbital energy in the hydrogen. So we have a shift here. This delta E sub G is a downshift. This delta E sub U is an upshift. So we can express this delta E sub G and delta E sub U. Delta E sub G is E sub G, the child energy of the bonding orbital minus HAA, which is just the atomic orbital energy. So we plug in the expression of E sub G over here, and then minus the atomic orbital energy. So really it's just negative one half atomic unit for the hydrogen atom. But for just generality, we'll just keep this H sub AA here. So we take the difference between these two. Over here, this energy is this E sub G. This energy is the atomic orbital energy. So we take the difference from here to here. It's just algebra. We have HAB minus HAA times SAB on top, 1 plus SAB on the bottom. This is less than 0, and that's why actually this E sub G is lower than the atomic orbital energy. And now let's look at delta E sub U, which is defined to be E sub U minus HAA, which is the energy of the anti-bonding orbital minus the atomic orbital energy. So this is positive, and we have this expression as E sub U minus HAA. We kind of just combine this two, some simple algebra. We get HAA times SAB minus HAB over 1 minus SAB. This is greater than 0. So in this fraction, the denominator is greater than 0. SAB is between 0 and 1. So on the bottom, you have a positive value, and on top, you also have a positive value. That's why delta E sub U is greater than 0. So again, delta E sub G is less than 0. So the bonding MO has lower energy than the atomic orbital. And over here, this delta E sub U is positive. So the energy of the anti-bonding orbital is higher than the atomic orbital. So we have this statement over here. Delta E sub G is negative, delta E sub U is positive. We can easily prove the magnitude of delta E sub G is less than the magnitude of delta E sub U. So in this MO diagram, I intentionally draw this arrow longer than this down arrow for a reason. It's just because SAB is always positive. The overlap integral SAB is usually between 0 and 1, and it's positive. And then we can prove this inequality. Delta E sub G is less than delta E sub U in their magnitudes, because so first we can write this easily. 1 over 1 plus SAB is less than 1 over 1 minus SAB, because this SAB, the overlap integral, is between 0 and 1. And now I multiply both sides by a positive number, which is HAB minus HAA times SAB. So we have this less than this. Alright, and you can see this is the magnitude of delta E sub G over here. It's the magnitude of this. And now if you look at this expression is the magnitude of delta E sub U. So therefore we just proved that the magnitude of delta E sub G is less than delta E sub U. So over here, this shift, downshift, is less than the upshift. So now if you imagine, what if we have 4 electrons? Then we put 2 electrons here, 2 electrons here. And in that case, well, the upshift of the energy is greater than the downshift of the energy. So if you somehow occupy those MOs with 4 electrons, well, it's not going to be favored energetically. That's why we have never observed H2 with 2 minus charges in the real world because H2 with 2 minus charges is less stable than 2 separate H minus anions. Chapter 21, Molecular Orbital Theory, Section 21.3, the H2 molecule. The shown equation of H2 in the atomic unit is H psi equals E psi. Psi is a function of 2 electrons, labeled 1 and 2. H consists of the kinetic energy operators for both electrons, the attraction felt by these 2 electrons from the 2 different nuclei. We have electron-electron repulsion and also nucleus-nucleus repulsion. Again, kinetic energy operators of the 2 electrons, attraction between the electrons and the nuclei, electron-electron repulsion, and over here, nucleus-nucleus repulsion. In general, when a system contains n-charged particles, the number of electrostatic potential energy terms is n times n minus 1 over 2. So again, for each of the n-charged particles, it feels either attraction or repulsion from the other n minus 1 charged particles. Therefore, in total, we have n times n minus 1 terms for potential energy. Why divided by 2? Because if we count the number of potential energy terms in the previous way, we double counted actually every single electrostatic term 2 times. So that's why we need to divide everything by 2. In hydrogen 2, there are 4 charged particles. So 4 charged particles each feels either attraction or repulsion from the other 3. So 4 times 3, we have 12 potential energy terms. But to remove the double counting, we need to divide this 12 by 2. We get 6 potential energy terms. Among these 6 potential energy terms, 4 are negative attraction terms, 1, 2, 3, 4, and 2 are positive repulsion terms between the 2 electrons and between the 2 nuclei. So in this diagram, we can see the repulsion between nucleus A and nucleus B, the repulsion between electron 1 and electron 2, and then finally the attraction between the 2 electrons and the 2 nuclei. Now let's look at the molecular orbital diagram of H2. It's very similar to the molecular orbital diagram for H2+. We just have one more electron in H2. The bond order of H2 is 1. The bond order of H2+ is 1/2. How do we compute the bond order? Well, it's equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So over here, when we form these 2 MOs, the 2 electrons occupy the sigma g bonding orbital. The bond order is therefore 2 minus 0 over here, and then divided by 2. We have a bond order of 1. In H2+, we have only 1 electron in the bonding orbital. Therefore, the bond order is only 1/2. What about H2-? That means we have 1 additional electron. We can only put this additional electron in here, the sigma u star anti-bonding orbital, and therefore we have 2 bonding electrons and 1 anti-bonding electron in H2-. In that case, the bond order is also 1/2. It's 2 minus 1 over 2. That's 1/2. So both H2+ and H2- have a bond order of 1/2 for different reasons. In H2+, there's only 1 bonding electron. In H2-, we have 2 bonding electrons, but also 1 anti-bonding electron. Now let's look at H2-. That means we need to put 2 electrons in the sigma u star anti-bonding orbital. It's very unstable. That's why in the real world we cannot see this H2-, with a bond order of 0. Again, the bond order should be the number of bonding electrons minus the number of anti-bonding electrons divided by 2. To weaken a bond, we can either reduce its bonding electrons or increase the number of anti-bonding electrons. The MO diagram of H2 is very similar to the MO diagram of H2+. The wave function for the 2 electrons in the H2 molecule must be anti-symmetric under the exchange of the 2 electrons. So that's the biggest difference between H2 and H2+. In H2 plus, we have only one electron. We do not even have to worry about quantum mechanical postulate 6, which states that the total wave function must be anti-symmetric under the exchange of two electrons. In H2 plus, we don't even have two electrons. But in H2, we have to worry about this postulate 6. We write out the total wave function of the two electrons in H2. It's the normalization factor n times sigma g of electron 1, sigma g of electron 2, and then followed by a spin function alpha 1 beta 2 minus alpha 2 beta 1. You can see this sigma g1, sigma g2, this is symmetric. If I switch electron 1 with electron 2, I get the same expression. However, if you look at the spin part over here, alpha 1 beta 2 minus alpha 2 beta 1, well, the sign of this will change if I swap electrons 1 and 2. Again, under the exchange of the two electrons, we get psi of electron 2 and electron 1. Now we have sigma g2 times sigma g1, and then alpha 2 beta 1 minus alpha 1 beta 2. I just replaced every single 1 with 2, every single 2 with 1. Now let's compare this wave function and this wave function. N is the normalization factor. Sigma g2 goes here, sigma g1 goes here. No change in this part versus this part. But if you look at the spin part, alpha 1 beta 2 now becomes negative alpha 1 beta 2. Negative alpha 2 beta 1 now becomes positive alpha 2 beta 1. Therefore, psi of 2 1 is equal to negative psi of 1 2. The wave function is indeed anti-symmetric under the exchange of the two electrons. In this wave function, we noticed the spatial part is symmetric while the spin part is anti-symmetric. Now let's look at the spin of this function. When we look at this function, we can apply the s squared operator to this wave function, we get 0. We can also apply the z component spin operator to this wave function, we also get 0. And more generally, if we have a MO occupied by two electrons, or you can say this MO is completely occupied, the net spin is just 0. In this case, the alpha and beta completely cancel. We do not have a net spin in this case. But what if we promote one of the two electrons in the H2 molecule to one of the anti-bonding orbital, and then there are 4 possible microstates? We can write them out. We can have one electron in the sigma g orbital, the other electron in the sigma u star orbital. Now we can have alpha alpha, alpha beta, beta alpha, and beta beta. Well, this is just because now we have two electrons in the two different spatial orbitals. They have different spatial quantum numbers. Therefore, it's okay for them to have the same spin quantum numbers. So it's okay for them to be alpha alpha or beta beta. And also, we can have alpha beta or beta alpha. We can apply this s squared operator to alpha alpha. We will get the h bar squared times s plus 1 as the eigenvalue. The result is 2h bar squared times alpha alpha. This s is equal to 1 because when you have alpha alpha, the s is actually 1. Instead of 1/2, you have 2 electrons here. What about beta beta? Same thing. We get 2h bar squared times beta beta. So really it tells you, well, the spin angular momentum is the square root of 2h bar squared. The z component of alpha alpha is h bar. The z component of beta beta is negative h bar. So the z components of alpha alpha is simply just a positive half h bar of 1 alpha, and then another positive 1/2 h bar for the other alpha. That's why we get h bar. And over here, when we look at the z component beta beta, it's just negative 1/2 h bar plus another negative 1/2 h bar. It's negative h bar in total. That's the z component. So now you can see we have alpha alpha and beta beta. They have the same magnitude of the 3-dimensional spin angular momentum, which is the square root of 2 times h bar, but they differ in the z component. One is h bar, the other is negative h bar. Neither alpha beta or beta alpha is an eigenfunction of the S squared operator. But if we do a linear combination, either alpha beta plus beta alpha or alpha beta minus beta alpha, they both are an eigenfunction of this S squared operator. We can apply this S squared operator to alpha beta plus beta alpha. We get eigenvalue 2h bar squared. So if you look at this eigenvalue 2h bar squared, 2h bar squared, 2h bar squared, they are exactly the same. Now if we apply the same S squared operator to alpha beta minus beta alpha, oh well, this two actually cancel. You're gonna get 0. The z components of the angular momentum of alpha beta plus minus beta alpha, they are both 0. And over here we see a diagram of alpha beta plus minus beta alpha. Well, this is alpha beta, this is beta alpha. So really we need to mix this two. MO diagram, we have this diagram plus minus this diagram. We get alpha beta plus minus beta alpha. And this is just because of the quantum effect of electrons. Electrons are indistinguishable. When we write this alpha beta plus minus beta alpha, we cannot tell which electron is alpha, which electron is beta. When one of the two electrons in the H2 molecule is excited to the sigma U star anti-bonding orbital, there are 4 possible microstates. Alpha alpha, alpha beta, beta alpha, beta beta. We can regroup them and attribute all those 4 microstates or their linear combinations to S1 and T1 excited states. S1 means the first singlet excited state. T1 is the first triplet excited state. When we see this T1, that means we have a degeneracy of 3. When we see S1, that means we have a degeneracy of 1. And this is wave function to the S1 electronic state. Over here we have sigma G and sigma U star. So if you look at this, we have electron 1 in sigma G, electron 2 in sigma U star. Over here we have electron 2 in sigma G, electron 1 in sigma U star. We have a linear combination here. And over here the spin part is also a linear combination, alpha 1 beta 2 minus alpha 2 beta 1. So now let's analyze the spatial part of the S1 wave function. This is symmetric. If we swap 1 and 2, there's no sign change. We're gonna get the same expression. However, over here, if we switch 1 and 2, the sign will change. So we have a symmetric spatial part and a anti-symmetric spin part in the S1 excited state. Well, the T1 triplet excited state, over here we have a degeneracy of 3. That means these 3 have the same energy. Now let's look at the spatial part. They share the same spatial part. It's sigma G1, sigma U star 2 minus sigma G2 times sigma star U star 1. Over here we can see if we exchange electrons 1 and 2, the sign of the spatial part will change. We have an anti-symmetric spatial part. Therefore, the spin part must be symmetric. Over here, alpha 1 beta 2 plus alpha 2 beta 1. This is symmetric under the exchange of the 2 electrons. Also, we can exchange 1 and 2. We will still get alpha 1, alpha 2. We can exchange 1 and 2 here. Again, beta 2 times beta 1 is equal to beta 1 times beta 2. So in the T1 excited state, we have a anti-symmetric spatial part and we have a symmetric spin part. In the S1 state, we have a symmetric spatial part and a anti-symmetric spin part. Now again, we will review what is this? What is alpha beta minus beta alpha? What is alpha beta plus beta alpha? Okay, it's just like this. Let's just assume this one is electron 1, and then we have this alpha electron 1. This is beta for electron 2. But over here, this is beta for electron 1. This is alpha for electron 2. Neither this or this is a eigenfunction of the S squared operator. So we'll have to think of a way to get S squared value. We just need to simply do a linear combination of these 2 different MO diagrams, either plus or minus. Both plus or minus, both linear combinations are denoted by alpha beta plus minus beta alpha, and this expression is indeed a eigenfunction of the s squared operator. So in the previous page, we get the eigenvalues for alpha beta plus beta alpha. Well, the corresponding eigenvalue of s squared is 2 times h bar squared. What about alpha beta minus beta alpha? Well, the eigenvalue of s squared is simply 0. Now let's look at the z components of alpha beta plus minus beta alpha. They are both 0. So if we look at this 4 wave functions again, in the S1 state, we have a anti-symmetric spin part. Over here, s squared is 0, s sub z is 0. Now let's look at this 3 spin functions. The s squared value for this 3 different spin functions are exactly the same, 2 times h bar squared. What about the z component? Well, they are different. The z component for alpha 1, alpha 2 is positive h bar. The z component for beta 1, beta 2 is negative h bar. The z component for alpha 1, beta 2 plus alpha 2, beta 1 is 0. Chapter 21, Molecular Orbital Theory, Section 21.4, Homonuclear Diatomic Molecules. The molecular orbital diagram of helium-2 shows that the bond order of this helium dimer is 0. Therefore, the helium-2 molecule is very unstable. It dissociates into helium atoms spontaneously. This is the MO diagram of helium-2. We have 2 electrons in the 1s orbital on the left, 2 electrons in the 1s orbital on the right. They form sigma G bonding orbital, sigma U star anti-bonding orbital. And then we have 2 bonding electrons, 2 anti-bonding electrons. The bond order is therefore 2 minus 2 over 2. That's just 0. And also because the energy shift of this sigma U star is greater than the energy shift of this sigma G star. So actually helium-2 dimer has a higher energy than 2 separate helium atoms. Therefore, the helium dimer dissociates spontaneously into helium atoms. What if we remove an electron from the helium-2 dimer? Now we have helium-2 plus. We have 2 electrons in the bonding orbital and only 1 electron in the anti-bonding orbital. Now we have a bond order. The bond order is 1/2. It's 2 minus 1 divided by 2. Therefore, the helium-2 plus is energetically stable. It has lower energy than the sum of 1 helium atom and a helium plus. This helium-2 plus does not dissociate spontaneously. We need to break a bond between these 2 helium nuclei. Although the bond order is only 1/2, there is a bond. Now let's look at the molecular orbital diagram of lithium-2. So over here we see lithium-2. First, the 1s electrons, they form sigma G and sigma star. Over here, the bond order is exactly 0. Now, the 2s orbitals, they form 2 sigma G, 2 sigma U star. And we put these 2 electrons into this lower energy, 2 sigma G bonding orbital. And over here, this is empty. So the bond order is 1. 2 bonding electrons minus 0 anti-bonding electrons divided by 2. We don't have to worry about those core electrons or core orbitals. They always cancel. And also, the core electrons are really close to the nucleus. They are attracted to the nucleus. They do not take part in any chemical reactions. We can also write out the electron configuration for a molecule, such as lithium-2. So we have 2 electrons in the 1 sigma G orbital, so over here, 2 electrons in the 1 sigma U star orbital here, 2 electrons in the 2 sigma G orbital over here, and 0 electrons in the 2 sigma U star anti-bonding orbital. Or simply we can drop the last term because we do not have any electrons in this anti-bonding orbital. And again, the bond order of lithium-2 is 1. What if we remove an electron from lithium-2? Well, that means we remove 1 bonding electron. The bond order will decrease to 1/2. Now what if we add 1 electron to the lithium dimer? Well, we can only add the electron here in the anti-bonding orbital. The bond order is also 1/2 because now we have 2 bonding electrons and 1 anti-bonding electron. We take the difference divided by 2. The bond order for lithium-2 minus is also 1/2. For convenience, after lithium-2, so we're going to talk about beryllium-2, boron-2, carbon-2, etc. We will not draw those core electrons or core orbitals for those diatomic molecules, because core electrons and core orbitals are of very little interest to chemists. They do not take part in chemical reactions. Now let's look at beryllium-2. So the electron configuration of beryllium-2 is this: 1 sigma G2, 1 sigma U star 2, 2 sigma G2, 2 sigma U star 2. Remember, for lithium, we have only 6 electrons, so we stop right here. For beryllium-2, we have 2 more electrons. Now we have this 2 electrons in this 2 sigma U star orbital. So here's the situation for beryllium-2. We have 2 electrons from the 2s orbital on the left, 2 electrons from the 2s orbital on the right. Alright, and these 2s atomic orbitals form molecular orbitals, sigma G and sigma U star. We have a total of 4 electrons to allocate. Therefore, 2 electrons in this 2 sigma G orbital, 2 electrons in this 2 sigma U star antibonding orbital. What's the bond order? 0. Because we have 2 bonding electrons minus 2 antibonding electrons. It's just 0. But now, what if we remove an electron from beryllium-2? Well, look at this picture. If we remove an electron, we have beryllium-2 plus with 2 bonding electrons and only 1 antibonding electron. The bond order becomes 1/2. What if we add an electron to the beryllium dimer? Well, that means we have to put an electron on here. So over here we have this so-called 1pi U orbital. This is formed by the interaction between a 2p orbital on the left and a 2p orbital on the right. So now we have 3 bonding electrons and 2 anti-bonding electrons. So in beryllium-2 minus, we also have a bond order of 1/2, because again, now we have 3 bonding electrons more than the number of anti-bonding electrons too. And how do we form those orbitals, those sigma and pi orbitals between 2p orbitals? Now let's look at this diagram. Between s orbital and s orbital, it's straightforward, it's a sigma bond. Between a s orbital and a p orbital, if it's head-to-head interaction, we also form a sigma bond. Between 2 p orbitals, well, we can form sigma bonds or pi bonds. This is head-to-head interaction. It's called a sigma bond. Now we are looking at pi shoulder-to-shoulder interaction between these 2 p orbitals. It's called a pi bond. And also a p orbital and the d orbital may have shoulder-to-shoulder interaction as well. It's also a pi bond over there. So you can see these 2 lobes are in phase. These 2 lobes are also in phase. Between 2 d orbitals, if you align these 2 orbitals into planes parallel to each other, you can form a delta bond. But over here, you're seeing just a simple pi bond. There's interaction between these 2 lobes and interaction between these 2 lobes. I was talking about, having 2 d orbitals in 2 different planes that are parallel to each other, and then you can have these 4 lobes overlapping with these 4 lobes. When that's the case, you have a delta bond. All right, that's more complex than this. Usually you observe delta bond in like transition metal complexes that involve 2 transition metal centers. So for now, we don't have to worry about delta bond. We don't even have to worry about those d orbitals. We just focus on this. When 2 p orbitals interact with each other via a head-to-head interaction, it's sigma bond. Shoulder-to-shoulder interaction, that's a pi bond. So now we can form a 2 degenerate pi bonds, and over here this is a sigma bonding orbital, and then we can also form 2 pi type anti-bonding orbitals and 1 sigma U star anti-bonding orbital. Now let's look at the symmetry over here. This is 2 sigma G, 2 sigma U star. But now this pi bonding orbital has a U symmetry. And why is that? Now look at this. G and U stands for symmetric and anti-symmetric with respect to the center. So we have the center here. And how do we know it's symmetric or anti-symmetric? with respect to the center. We just need to draw an arrow that passes through the center. So I'm going to draw an arrow here from this to this. Now you look at the two ends of the arrow. They have different colors. That means this is anti-symmetric. Alright, draw an arrow that passes through the center of this diatomic molecule. And I'm going from gray to white. Therefore, it's anti-symmetric. We can draw an arrow this way, from gray to white, or from white to gray. The color changes. It's anti-symmetric. Therefore, this bonding orbital is pi sub u. Now let's look at this head-to-head interaction. Again, there's a center here. You draw an arrow. It's going to be from gray to gray, same color. Therefore, this is symmetric with respect to the center of this diatomic molecule. Therefore, this symmetry is G. Again, the 2p interactions result in 6 molecular orbitals because we have 6 2p orbitals from the 2 atoms. In total, 6 atomic orbitals can be used to make 6 MOs. Now, among the 6 MOs, 3 are bonding molecular orbitals, 3 are anti-bonding molecular orbitals. The head-to-head interaction results in sigma bonding orbital or sigma star anti-bonding orbital. The shoulder-to-shoulder interaction results in either pi or pi star orbitals. So now let's look at this kind of diagram. We have 2p orbitals. They can interact in 2 different ways. Head-to-head, you get sigma bonding orbital and sigma star anti-bonding orbital. Shoulder-to-shoulder, you get pi sub u bonding orbital and pi sub g anti-bonding orbital. So now let's look at those graphs. First, head-to-head interaction. So this two head-to-head interaction, it's constructive because in the middle you have white and white overlap. It's sigma. Now over here, all right, this is still head-to-head interaction, so it's sigma bond. But look at the colors. This is white, and this is this is, let's say, blue. So when you have white and blue, this is actually sigma star. This is sigma star. There's a nodal surface in the middle. There is some error in the color over here. This part should be green color. This part should be white color. Sorry about this. I kind of got the picture from Wikipedia, but there's error with the colors in this lobe and in this lobe. This is sigma star. Now let's look at pi bond. When you look at pi bond, it's definitely shoulder-to-shoulder interaction, and it's constructive interference. Blue to blue, white to white. It's constructive. Over here, pi star. Still, it's shoulder-to-shoulder interaction. Therefore, this is pi type orbital, and this is anti-bonding because we have on top we have blue and white, on the bottom we have white and blue, different colors because they're out of phase. When they're out of phase, well, there's gotta be a nodal surface in the middle, and this is a anti-bonding orbital due to the destructive interference between these two p orbitals. Now let's look at this boron 2. In boron 2, we have 2 more electrons in beryllium 2. So in a boron atom, we have 2 electrons in the 2s orbital and 1 electron in the 2p orbital. And now let's look at the 2s orbitals. They can form sigma g, sigma u star. You put 2 electrons here, 2 electrons here. We have 2 bonding electrons, 2 anti-bonding electrons. They cancel. So this part, although it's not core electrons, not core orbitals, but this part is also a little boring over here because, again, the number of bonding electrons cancel the number of anti-bonding electrons. We have a bond order of 0. Now let's look at the interactions between 2p and 2p. So we have 3 2p orbitals on the left, 3 2p orbitals on the right. We have a total of 6 atomic orbitals to start with. We need to make 6 MOs. Which 6 MOs? We will see some pi orbitals, some sigma orbitals. When we have shoulder-to-shoulder interaction, pi orbitals. When we have head-to-head interaction, sigma orbitals. And also we have pi-type bonding orbitals versus pi star anti-bonding orbitals. Why is that? We can have constructive interference. That means overlap. Or destructive interference. That means there's a node in the middle. Now let's look at those situations. First, shoulder-to-shoulder interaction, constructive interaction. We have 2 degenerate pi orbitals. pi sub u with u symmetry. Now we can put these 2 electrons in here because we need to put 2 electrons in 2 degenerate orbitals. We have to separate these 2 electrons because they repel each other, and because of the Hund's rule, we need to have maximized the spin. So we have spin up and spin up over here, and this is boron 2, the boron dimer molecule. This is the MO diagram for this boron dimer. What's the bond order? 2 bonding electrons down there, 0 antibonding electrons. Therefore, the bond between the 2 boron atoms is a single bond. This is a single bond. It's really weird. The bond order is 1, it's a single bond. But in this single bond, you actually see 2 1/2 pi bonds. So you have 1/2 pi bond over here, another 1/2 pi bond over here. So let's say, well, if we put these 2 boron atoms on the z-axis, so we have a pi bond formed between the 2px orbitals, and another pi bond between the 2py orbitals. And also the bond order of the pi bond from the 2px orbitals is 1/2, and the bond order of another pi bond is also 1/2. So although we say it's a single bond, it's actually made of 2 1/2 bonds. It's kind of really strange. Now let's look at the electron configuration of boron 2. 1 sigma G2, 1 sigma U star 2, those are core electrons, core orbitals. And now we have 2 sigma G2 over here and 2 sigma U star 2 over here. Finally, 2 electrons that can make bonds. They occupy the 2 degenerate pi U orbitals. One here and one here. And what about boron 2 plus? We have boron 2 plus. We need to remove an electron, then the bond order is just 1/2. What about boron 2 minus? That means we add an electron. So how do we add an electron? We add an electron here or here. And then we have 3 bonding electrons. The bond order is 1.5. What about boron 2 minus? When you have boron 2 minus, we put an electron here, another electron here. Now we have a bond order of 2. We have 2 whole pi bonds. Alright, so that's the situation over here. And also in the ground electronic state of boron 2, we have 2 unpaired electrons. So these 2 are unpaired. They have parallel spin. Each electron is going to generate a magnetic moment due to the electron spin, and the electron spin of these 2 electrons do not cancel, because based on Hund's rule, we need to maximize the spin. It's either alpha alpha or beta beta. Either way, you have a net electron spin. That means you have a net non-zero magnetic moment. And boron 2 may be weakly attracted to the poles of a strong magnet. And we say boron 2 is paramagnetic. It's paramagnetic. Each boron 2 molecule may be considered as a very small, very weak magnet due to its non-zero net electron spin. So again, the spin of this electron does not cancel the spin of the other electron. We have a net electron spin. We have a net magnetic moment. And finally, I want to just quickly mention the number in front. So for the core electrons, we have 1 sigma G, 1 sigma U star. I didn't draw those, but now we have 2 sigma G, 2 sigma U star, and then 3 sigma G, 3 sigma U star. So we just label those sigma G and sigma U star with those numbers. And right here, this is the first time we see pi orbitals, therefore it's 1 pi U. And over here, this is the first time we see any pi G orbital, so this is 1 pi G star. So going above, you might see 2 pi U and 2 pi G stars. Now let's look at carbon 2. Carbon 2 has 2 more electrons than boron 2. So we simply fill up these 2 degenerate pi U orbitals. And the bond order is 2 for carbon 2. Well, we have a pi bond here, another pi bond here. These 2 pi bonds are perpendicular to each other. Again, let's align this molecule in the z-axis. So we have a pi sub x orbital and a pi sub y orbital. Both are doubly occupied, so we have a total bond order of 2. What if we have C2 plus? Then we need to remove an electron. The bond order becomes 1.5. What if we have C2 minus? Then we need to add electron now in the sigma G bonding orbital. Now we have 5 bonding electrons in C2 minus. Therefore, the bond order becomes 2.5. What if we have C2 2 minus? while C2 minus has the same number of electrons as nitrogen 2. We need to put 2 more electrons here in the 3 sigma G orbital. That means we have 6 bonding electrons, 0 anti-bonding electrons. The bond order is therefore 3. And now let's look at the ground electronic state of carbon 2. We do not have any unpaired electrons. So that means we do not have any net electron spin. We do not have any magnetic moment. The net electron spin is 0. C2 is diamagnetic. In organic chemistry, we learned the bond order of C2H6, C2H4, C2H2 is 1, 2, 3. Intuitively, we would guess that when the number of hydrogen atoms decreases, we would have higher and higher bond order. But now in quantum chemistry, we learned that the bond order of C2H0 is not 4; it's actually only 2, and we have actually 2 bonds, 1 pi x bond, 1 pi sub y bond, so only 2 pi bonds. Well, the bond order of carbon 2 may become 4 if somehow you can promote a 2 sigma U star electron to a bonding orbital. So if somehow, let's say we have 4 electrons over here, then we can somehow there are 4 bonding electrons here already, and somehow if you can promote one of these 2 electrons, any one of these 2 anti-bonding electrons, to here, all right, it takes a lot of energy to go from here to here. But let's say you have the energy, you can promote this 2 sigma U star electron to here. Now we have 2 bonding electrons, 1 anti-bonding electron, and then 5 bonding electrons here. So in total we have 2 plus 5, that's 7. We have 7, 1, 2, 3, 4, 5, 6, 7. And then we have 7 bonding electrons and 1 anti-bonding electron, and then we have a bond order of 3. So how can we have a bond order of 4? You need to promote both electrons here to here, and then we have in total 8 bonding electrons and 0 anti-bonding electrons. Again, we need external energy to promote these 2 electrons in the 2 sigma U star anti-bonding orbital to here, 3 sigma G bonding orbital, and then we will be able to have a bond order of 4 in the carbon 2 dimer. Now let's look at the electron configuration of nitrogen 2. Nitrogen 2 has 2 more electrons than carbon 2. So we're going to put these 2 electrons in the 3 sigma G orbital. We have bond order of 3. What about nitrogen 2 plus? We have a bond order of 2.5 because we need to remove a bonding electron. What about nitrogen 2 minus, the anionic molecule? The bond order is also only 2.5 because, well, if we put 1 additional electron in this diagram, you have to put that electron in the 1 pi G star anti-bonding orbital. And then we have 6 bonding electrons and 1 anti-bonding electron. The bond order becomes 2.5. Over here we have just 2 bonding and 2 anti-bonding. The ground electronic state of nitrogen 2 contains 0 unpaired electrons. You can see all electrons are paired. Therefore, nitrogen 2, just like carbon 2, nitrogen 2 is diamagnetic. So it tends to be magnetized in the opposite direction of an external magnetic field, causing a repulsive force. So nitrogen 2 has all electrons paired, therefore it's diamagnetic. So is carbon 2. Now let's look at oxygen 2. O2 is very interesting. O2 has 2 more electrons than nitrogen 2. So we have to put the 2 electrons in the 1 pi G star anti-bonding orbitals here and here. The bond order is 2 in O2, so we draw a double bond between these 2 oxygen atoms. The reason is simple. We have 6 bonding electrons, 2 anti-bonding electrons. We take the difference, that's 4 over 2, that's 2. So the bond order is just 2. What about O2 plus? Well, when we have O2 plus, we need to remove an electron, and actually we can remove an anti-bonding electron. Now the bond order is 2.5. We can also add an electron to the MO. We need to add the electron over here, and then we have 5 bonding electrons and 3 we have 6 bonding electrons in total and 3 anti-bonding electrons. 6 minus 3 divided by 2, that's 1.5. So if we add one more electron to O2, we form O2 minus with a weaker bond, with a bond order of only 1.5. So the oxygen 2 molecule contains 2 unpaired electrons. Based on the Hans rule, these 2 electrons have the same spin. We want to maximize the spin, therefore the net electron spin is non-zero. We have a non-zero net magnetic moment over here, and that means each O2 is a small magnet, and O2 can be attracted by a magnetic pole. So now let's look at this video. In this video, I think the instructor pour first liquid nitrogen through this 2 poles, and there's no effect, but then the instructor poured liquid oxygen. You will see liquid oxygen can be attracted by the magnetic poles. So this is the video. I'm gonna fast forward to here. So I think it's pouring. I'm gonna go back to here so that we can see more clearly. This is liquid nitrogen. Liquid nitrogen just go through. Okay, there's no attraction at all. This is liquid nitrogen. Liquid nitrogen. All electrons are paired. This is liquid oxygen with unpaired electrons. Okay, liquid oxygen is being attracted. Between these 2 magnetic poles, you see liquid oxygen is being attracted. Alright, so this MO diagram can be used to explain why O2 has a small magnetic moment. Now if we just imagine F2, we just put 2 more electrons here and here. We have 2 more antibonding electrons in F2 than O2. That means in F2 we have just a single bond. We learned that in general chemistry, between 2 fluorine atoms, there's only a single bond. And over here, using this MO diagram, we learned that in F2 we have 6 bonding electrons here, 4 anti-bonding electrons here, and then for F2, okay, for F2, and then 6 minus 4 over 2. That's just the bond order is just 1. All right. So what if you have F2 plus? Well, when you have F2 plus, you just put 1 more electron in here. The bond order is 1.5. What if you have F2 minus? Well, F2 minus, that means you put 2 electrons here and here, and then you put another electron in this sigma U star orbital, and then the bond order is only 0.5 in F2 minus. F2 minus has a very weak bond with a bond order of only 0.5. Alright, F2 minus has the same MO diagram as neon 2 plus. So neon 2 plus actually has a non-zero bond order. Neon 2 plus has a bond order of 1/2, the same as fluorine 2 minus, because neon 2 plus and the fluorine 2 minus have the same number of valence electrons. Finally, let's talk about spin this sp mixing and how does that change the order of MOs. So we'll compare the MO diagram of nitrogen 2 N2 and oxygen 2 O2 side by side. So in nitrogen 2 we have a total of 6 valence electrons. In O2 we have a total of 8 valence electrons. And on top they are the same. You have 1 pi g star, 1 pi g star, and then 3 sigma u star, 3 sigma u star. But if you look at this part and this part, compare this two, you'll see some difference. In nitrogen 2, the 1 pi u orbitals have lower energy than 3 sigma g. In O2, the 3 sigma g orbital has lower energy than 1 pi u. Alright, so what's the reason? This is actually the normal MO diagram. Why? Because usually pi-pi interaction is weaker than the sigma interaction. So supposedly the interaction between 2 orbitals to form this pi bonds or anti-bonding orbital, pi anti-bonding orbital, those kind of interaction should be weaker. That means this 1 pi u and this 1 pi g star should be closer to the center or the atomic energy level. So this is the atomic energy level, and the 1 pi u and 1 pi g star should be close to the center, and 3 sigma g, 3 sigma u star should be far away from the center over here. So this is the normal picture. But over here, why is this 3 sigma G kind of closer to the center? It's even above the 1 pi u. Okay, let's talk about the sp mixing. So sp mixing occurs when you have, for example, MO orbitals with the same symmetry. So you can see this is 3 sigma G, right? You have 3 sigma G. Below 3 sigma G, there's a 2 sigma G. There is a 2 sigma G. I didn't draw it. There's a 2 sigma G molecular orbital, right? The 2 sigma G molecular orbital is formed by the interaction between the 2s atomic orbitals in the nitrogen molecule or in the oxygen molecule. So 2s orbital, they can form 2 sigma G orbital. Now this 2 sigma G molecular orbital is a bonding orbital. 3 sigma G also is a bonding orbital, alright? And 2 sigma G and 3 sigma G, they have the same symmetry. They are both G symmetry, that means symmetric with respect to the center. They also have a same symmetry. It's called a sigma symmetry. So actually sigma and pi indicates the symmetry of the MOs as well. So, but you do need to learn more about point groups, about group theory, to understand that sigma and pi are symbols to denote the symmetry of MOs as well. So anyway, if you just look at 2 sigma G, 3 sigma G, they share the same sigma, Greek letter sigma. They share the same English letter G. That means they are both symmetric with respect to the center, and they both have the same sigma symmetry around the molecular axis. That means they can interact. The interaction between 2 sigma G and the 3 sigma G will bump the 3 sigma G up and will shift the 2 sigma G down. So when two orbitals with the same symmetry interact, you will bump up the higher energy orbital even higher, lower MO even lower. So you will see this 2 sigma G in this nitrogen 2 is even lower, and 3 sigma G is bumped up. And it's bumped up so significantly, this 3 sigma G lies above this 1 pi u. So this is a normal picture, but then in nitrogen 2 we have sp mixing. We bump this 3 sigma G up even higher than 1 pi u. So that's the story about this sp mixing. You need molecular orbitals with the same symmetry to interact. When they interact, the lower MO orbital will become even lower. The higher molecular orbital will become even higher. That's why the sp mixing bumps up the 3 sigma G orbital in the nitrogen 2. But why didn't this kind of sp mixing bump up this 3 sigma G in O2? Well, it's simply because in O2, yes, this 3 sigma G is also bumped up because of the interaction between 3 sigma G and 2 sigma G. But because in O2 and also in F2, the energy gap between 2 sigma G and 3 sigma G is so large, the interaction is very, very small. So although this 3 sigma G is bumped up, but only by a little bit, not enough for this 3 sigma G to overcome, to get over this 1 pi u. So in O2 and F2, although there is also sp mixing, there's also energy shift of both 2 sigma G and 3 sigma G. Although 2 sigma G is shifted down and 3 sigma G is shifted up, but that shift is not enough for this 3 sigma G to have higher energy than 1 pi u. So that's that. For nitrogen 2 and for carbon 2, boron 2, so you have this kind of MO. For O2 and F2, you have this kind of MO. All of this is due to the so-called sp mixing. Chapter 21, Molecular Orbital Theory, Section 21.5, Heteronuclear Diatomic Molecules. The MO diagram of lithium hydride is similar to the MO diagram of H2. The lithium 2s atomic orbital interacts with the hydrogen 1s atomic orbital and form a 2 sigma bonding orbital and a 3 sigma star anti-bonding orbital. There's no G or U symmetry in this heteronuclear diatomic molecule, because this molecule does not have any center of symmetry. the lithium 1s orbital has significantly lower energy than the hydrogen 1s orbital, and therefore there's no interaction between this 1s orbital and this 1s orbital. The bond order of lithium hydride is 1. So we have this 2 bonding electrons, 0 anti-bonding electrons. The difference is 2. 2 divided by 2, that's 1. Over here, although it's written as 1 sigma, however, it's not really a bonding orbital. This 1 sigma is awfully similar to this just 1s orbital, because again, the interaction between the lithium 1s orbital and hydrogen 1s orbital is negligible. The ionization energy of lithium is 0.2 atomic unit. The ionization energy of hydrogen is 0.5. Therefore, the lithium 2s atomic orbital lies above the hydrogen 1s orbital. This atomic orbital energy is negative 0.2. This atomic orbital energy is negative 0.5. So the ionization energy is simply the amount of energy to promote this electron from negative 0.2 to 0. The difference is 0.2. The ionization energy for hydrogen is the amount of energy required to promote this electron from negative 0.5 atomic unit to 0. Therefore, the ionization energy of hydrogen is 0.5. So now we place the lithium 2s orbital above the hydrogen 1s orbital. And this two may form 2 sigma and 3 sigma star, bonding orbital, anti-bonding orbital. There is no GOU symmetry. And over here, because this sigma is the bonding orbital, and this 1s orbital has lower energy than the 2s orbital, this 2 sigma is closer to the hydrogen 1s orbital than to the lithium 2s orbital. And that means in this 2 sigma, it contains more than 50% of hydrogen 1s, less than 50% lithium 2s. However, if you look at this 3 sigma star antibonding orbital, it contains more than 50% of the lithium 2s, less than 50% of hydrogen 1s. Note that the ionization energy is the absolute value of the energy of the highest occupied atomic orbital, HOAO. So when you see this atomic orbital energy over here, well, the ionization energy is positive 0.5. When you see this energy of HOAO of lithium is negative 0.2, then the ionization energy is positive 0.2 AU. The energy of the highest occupied atomic orbital of a neutral atom is always negative, such as negative 0.5 for hydrogen 1s, negative 0.2 for lithium 2s. The ionization energy of a neutral atom is always positive. It always takes some energy to promote an electron from the highest occupied atomic orbital in an atom to an energy of 0. The MO diagram of hydrogen fluoride shows that the fluorine 2pz atomic orbital interacts with the hydrogen 1s atomic orbital and form a 3 sigma bonding orbital and 4 sigma star anti-bonding orbital here and here. The other 2 p orbitals do not interact with the hydrogen atomic orbital. So we just shift this to here at the same energy level. However, for just naming purposes, we now call them 1pi orbitals and 1pi electrons, but really those are just the 2px and 2py electrons in 2px, 2py orbitals. It's just in the MO diagram we have a different name for these electrons. Now let's look at the bond order. We have 2 bonding electrons in the 3 sigma bonding orbital, 0 anti-bonding electron here. So 2 minus 0 over 2, that's 1. The bond order of hydrogen fluoride is 1. What about these 4 electrons? Again, although they are labeled as 1pi electrons, they are neither bonding electrons nor anti-bonding electrons. These 4 electrons are still the 2px and 2py electrons on fluorine. What about the 2s orbital of fluorine? Well, the 2s orbital lies far below the hydrogen 1s orbital. So even if there's some interaction between the fluorine 2s orbital and hydrogen 1s orbital, the interaction is negligible. So we just have this 2 sigma here with the same level as this 2s, and these 2 electrons are not considered bonding electrons, because these 2 electrons essentially are just the 2s electrons of fluorine. The highest occupied atomic orbital energy for fluorine is negative 0.64. So I drew this 3 lines lower than the hydrogen 1s orbital, negative 0.5. Now when this and this form a 3 sigma MO, this MO, because this energy level is closer to this one, this 3 sigma contains more 2pz orbital of fluorine than this hydrogen 1s orbital. Now if we look at this 4 sigma star, it contains more than 50% of hydrogen 1s and less than 50% of fluorine 2pz. So again, because this 3 sigma contains more than half from this fluorine 2pz, you can see these 2 shared electrons are closer to the fluorine atom, because there is more than 50% probability of viewing these 2 electrons in the 2pz orbital of fluorine. And that is something we have learned in general chemistry. When you form a hydrogen fluorine bond, the electrons are closer, the shared electrons are closer to the fluorine atom than to the hydrogen atom. Chapter 21, Molecular Orbital Theory. Section 21.6, VS-EPR Theory. VS-EPR stands for valence shell electron pair repulsion. The VS-EPR theory states that each atom in a molecule prefers to adopt a geometry that minimizes the repulsion between the electron groups in the valence shell. When there are 2, 3, 4, 5, or 6 electron groups surrounding one atom, the hybrid orbitals centered on the atom are typically sp, sp2, sp3, sp3d, or sp3d2 orbitals, such as in C2H2, C2H4, C2H6, SF4, and SF6. The elements in the third row or below can often accommodate more than 8 electrons, because they can use d orbitals to hold electrons as well. Now let's look at this table. When we have 2 electron groups, the shape is linear. We often have sp hybrid orbitals. One example is C2H2. On each carbon, we have sp hybridization. When there are 3 electron groups, the shape is trigonal planar. The hybridization is often sp2. The examples: C2H4 ethylene with a double bond between the 2 carbon atoms, and also BH3. In BH3, the hybridization on boron is sp2. When there are 4 electron groups, the shape is tetrahedral. The hybridization is sp3. One example is methane. 2 other examples: ammonia, water. When there are 5 electron groups, the shape is trigonal bipyramidal. The hybridization is often sp3d. Now we'll have to use a d orbital to hold the electrons. A couple examples: sulfur tetrafluoride, and then PF5, phosphorus pentafluoride. When there are 6 electron groups, the shape is octahedral. The hybridization is sp3d2. We have to use 2 d orbitals. 2 examples here: sulfur hexafluoride and bromine pentafluoride. In this bromine pentafluoride, this bromine is surrounded by 6 electron groups, 1 lone pair plus 5 single bonds. Over here we have another table that summarizes the VS-EPR theory. So when we have 2 electron groups, such as 2 chemical bonds, it's linear. 3 electron groups, trigonal planar. Over here we have 3 bonds. Over here E stands for lone pair electrons, so we have 1 lone pair and 2 bonds. The molecular geometry is bent. 4 electron groups, we have a tetrahedral shape. In this example, we don't have any lone pair electrons. Over here we have 1 lone pair, therefore the 3 bonds are trigonal pyramidal. Over here we have 2 lone pairs, and then the molecular structure is bent. So we can view this as methane CH4, ammonia NH3, and water H2O. 5 electron groups, we have a electron geometry of trigonal bipyramidal electron geometry. In this case, we do not have any lone pair electrons, just 5 bonds. So the molecular geometry is also trigonal bipyramidal. But if you do have a lone pair, the molecular geometry is called seesaw. One example is SF4, sulfur tetrafluoride. On sulfur, you have a lone pair and then 4 bonds. Also, we may have T-shaped molecular geometry when we have 5 electron groups that include 2 lone pairs and 3 bonds. We can have linear as well if we have 3 lone pairs and 2 chemical bonds. When we have 6 electron groups, well, it's octahedral electron geometry. When there's no lone pair electrons, all 6 are bonds, and then the molecular geometry is also octahedral. What if there is 1 lone pair and 5 bonds? Well, in this case, the molecular geometry is called square pyramidal. So we just look at this part, ignoring this lone pair. What if we have 2 lone pairs and 4 bonds? Well, the molecular geometry is square planar. So in short, if we do not have any lone pair electrons, the electron geometry is the same as the molecular geometry. The molecular geometry is the same as the electron geometry. So when we have 2, 3, 4, 5, 6 chemical bonds, both the electron geometry and the molecular geometry are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Now, what if we have at least 1 lone pair? Well, then the molecular geometry is different from the electron geometry. In the electron geometry, you need to consider every single electron group. In the molecular geometry, you need to ignore the lone pair electrons. So, for example, if we erase this part, the lone pair electrons, the molecular geometry would be bent, and if we erase this, the molecular geometry would be trigonal pyramidal. What if we erase a lone pair electron here from the trigonal bipyramidal electron geometry? Well, just pretend you don't see this E, and then the remaining structure is called seesaw. Same here, the molecular geometry is different from the electron geometry. If you just look at this top part, it's square pyramidal. And over here, one good example is water. When you look at water, there are 4 electron groups surrounding the oxygen, but there are 2 lone pairs. So the electron geometry is tetrahedral, but the molecular geometry is bent. Chapter 21, Molecular Orbital Theory, Section 21.7, Localized molecular orbital theory. Localized molecular orbitals are MOs concentrated or localized on a single chemical bond or one electron lone pair. For example, each of the two beryllium hydrogen bonds in beryllium hydride can be described by a localized MO formed between the 1s orbital of one hydrogen atom and a sp orbital of the beryllium atom. Over here we have a hybrid orbital with this kind of shape. The normalized wave function of the two sp hybrid orbitals of beryllium are 1 over the square root of 2. This is the normalization factor times psi of beryllium 2s minus psi of beryllium 2pz. This is one of the two sp hybrid orbitals. The other one is 1 over the square root of 2, which is the normalization factor times the beryllium 2s orbital plus the beryllium 2pz orbital. So both sp orbitals are properly normalized. And over here, those are the shapes. So if we have the interaction between 2s orbital and 2pz orbital, we can mix them in two different ways. One way we have a larger lobe pointing to left, the other way we have a larger lobe pointing to the right. The localized MO wave functions of beryllium hydride are linear combinations of the two sp hybrid orbitals of beryllium and the 1s orbitals of the two hydrogen atoms. So now let's look at this beryllium overlapping with hydrogen A, this beryllium overlapping with hydrogen B. So in this case, we have a MO. We put some weight on the coefficients on the hydrogen A. This is 1s orbital of hydrogen A, and over here we have some weight or molecular orbital coefficients d sub A on this sp orbital of beryllium. For hydrogen B, we can have another sp orbital overlapping with this 1s orbital of hydrogen B. So Ca, Cb, Da, Db are simply molecular orbital coefficients. In localized molecular orbital theory, each of the 4 carbon-hydrogen bonds in methane, CH4, are formed between a hydrogen atom and a sp3 hybrid orbital of carbon. So first, let's look at the sp3 hybrid orbitals. Over here, we can use the 2s orbital, 2px orbital, 2py orbital, and 2pz orbital to make 4 sp3 hybrid orbitals. And those are normalized. This 1/2 is the normalization factor. So look, we can do a linear combination of these 4 different orbitals: 2s, 2px, 2py, 2pz. Over here we have plus, 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 and then plus, minus, 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 plus, minus, 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 plus. So these 4 linear combinations will have this kind of shape with 109.5 degrees between any two lobes. It's 109.5, and this is tetrahedral. Mathematically, the 4 localized MO wave functions of methane are this. So we have the 1s orbital from hydrogen A overlapping with this sp3 hybrid orbital, and we can have hydrogen B overlapping with another sp3 hybrid orbital, hydrogen C, hydrogen D. Each overlaps with a sp3 hybrid orbital. Again, we have 4 hybrid orbitals centered on the carbon atom. They are 4 sp3 hybrid orbitals. They can all overlap with one hydrogen atom. So over here you can see overlapping with hydrogen A, hydrogen B, hydrogen C, and hydrogen D. So what are those C sub A, C sub B, C sub C, C sub D, and also D sub A, D sub B, D sub C, D? They are called molecular orbital coefficients. In this case, we're looking at localized MOs, so those are localized molecular orbital coefficients. Chapter 21, Molecular Orbital Theory, Section 21.8, Symmetry Adapted Molecular Orbital Theory. Before studying the symmetry-adapted molecular orbital theory, one must have a solid understanding of molecular symmetry. I taught this topic in inorganic chemistry, and I made a YouTube playlist of my lectures on inorganic chemistry right here. I used Inorganic Chemistry 6th edition by Shriver et al. And 7th edition by Weller et al. In the 6th edition, Molecular Symmetry is Chapter 6. In the 7th edition, Molecular Symmetry is Chapter 3. So in my playlist of the lecture videos on Inorganic Chemistry, the first video is this. You can download my PowerPoint file and click this. You get to the playlist and see the first video on molecular symmetry. This is about point groups. And after the first video, there are 20 more lecture videos on the same topic, molecular symmetry. The last video is this one. I think there's a total of 20 plus videos on molecular symmetry. You do need to invest about 30 hours on molecular symmetry to have a solid understanding, but if you just want to have a basic understanding of point groups and character tables before studying this section, you can watch at least the first 3 videos in this playlist. So the first one is point groups. The second one is to determine the point groups for several molecules. The third one is the character table. Symmetry-adapted molecular orbitals are delocalized over the entire molecule. The symmetry-adapted MOs belong to the irreducible representations of the point group of the molecule. For example, methane CH4 belongs to the T sub D point group tetrahedral, and its symmetry-adapted MOs belong to the A1, A2, E, T1, and T2 irreducible representations in the TD point group. Water belongs to the C2V point group, and therefore the symmetry-adapted MOs of water belongs to the A1, A2, B1, and B2 irreducible representations in the C sub 2V point group. Over here we have the character table for the C2V point group. This is the point group. This 4 are the operations. E is the identity operation, that means doing nothing. C2 is rotation about the z-axis for 180 degrees. Sigma V is symmetry operation, symmetry plan. The XZ plan is the symmetry plan, so we can do a reflection via this XZ symmetry plan. There's also a YZ symmetry plan in water, so we can also do another operation with respect to this symmetry plan. There are 4 irreducible representations: A1, A2, B1, and B2. So A1 irreducible representation, that means when you do this identity operation, rotation, sigma V with respect to XZ plan, or sigma V with respect to the YZ plan, the molecular orbital will be symmetric. There's no change in sign. What if you have a MO that belongs to A2 irreducible representation? Of course, when you do identity operation, that means doing nothing, no change. When you do C2, no change. But over here, when you do reflection with respect to XZ or YZ plan, the sign of the MO will change. When you do B1, you can see -1 here, -1 here. That means when you do C2 rotation or reflection with respect to YZ plan, the MO will change sign. For B2, when you do these 2 operations, the MO will change sign. So mostly we need to focus on the negative ones. All right, here, 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 and here, here. So these 6 are negative ones. That means the sign of the MO will change when you do corresponding operations. We can also assign those irreducible representations to some like simple functions like x, y, and z. For example, z function, it's A1 symmetry, x function B1 symmetry, y function B2 symmetry. Because if you just imagine a vector along the y-axis, when you do a C2 rotation about the z-axis, the sign of this, or the direction of the vector, in the y-axis will have to change the direction. So that means changing sign. Or if you do a reflection with respect to xz plane, well, the vector that's in the y-axis will have to change sign. Alright, so that's why you see -1, -1 here. So x, y, z correspond to b1, b2, and a1. We also have x2, x squared, y squared, z squared. They're all a1 because a1. So if you look at x, b1, all right, and then x squared is b1 times b1, b1 times b1. So mostly just have this times itself, this times itself, this times itself, this times itself. You get 1, 1, 1, 1. That's a1 symmetry. Y squared, same thing. You need to square all those four numbers individually. You get 1, 1, 1, 1. That's a1 symmetry. What about x, y? X times y. So this 2, you get a 1. This 2, you get a 1. This 2, you get -1, -1. So it's going to be a2 symmetry. So x, y is a2 symmetry. What about xz? It's just x, this row times this row. You get the same symmetry as x, etc. R sub z, R sub y, R sub x are rotations. Over here, R sub z is to rotate about the z-axis. So the rotation can be represented by a circular arrow. And when you do identity operation, when you do C2 rotation, the circular arrow does not change its direction. But when you do reflection, the circular arrow will change its direction. Therefore, we have -1, -1 here. So similarly, we have the rotations about x and y axis. Again, +1 means symmetric, -1 means anti-symmetric. The character table can be used to determine the symmetry of p orbitals that are proportional to x, y, z. We can also determine the symmetry of the d orbitals. The d orbitals are proportional to x, y, y, z, z, x, x squared minus y squared, and 2z squared minus x squared minus y squared. So we can use this character table to determine the symmetry of atomic orbitals. And also we can use the character table to determine the symmetry of dipoles, because dipoles are proportional to x, y, and z. So you can see the three dipoles in the three different directions, x, y, and z directions, are b1 symmetry, b2 symmetry, a1 symmetry. Also, we can determine the symmetry for the polarizabilities. So if you have a matrix of polarizability, you see a bunch of elements such as x, y, y, z, z, x, x squared, y squared, z squared. You can determine the symmetry of those as well. The character table can be used to determine the symmetry of rotations. Over here, I think I mentioned this. When you see, for example, two -1s, that means this rotation operation will change sign. All right. Now let's look at the symmetry adapted MOs of water. They should belong to the A1, A2, B1, B2 irreducible representations in the C2V point group. So we're going to look at a few MOs. Over here, we have 1, 2, 3, 4, 5, 6. A total of 6 molecular orbitals for water. But now let's look at the left side, the right side. What are they? Over here, those are just atomic orbitals of the oxygen atom, all right, centered at the oxygen. This is just the 2s orbital of oxygen, 2pz orbital of oxygen, 2py orbital of oxygen, and 2px of oxygen. And you can see I assigned those symbols of irreducible representations for those atomic orbitals. 2s always symmetric, no matter what you do, it's A1. 2pz, it happens to be symmetric with respect to all four different operations. Which for identity operation, right? That's number one. The second operation is rotation about the z-axis for 180 degrees, so that's not going to change sign. The third operation is to have reflection with respect to, for example, this symmetry plane. No sign change. Another symmetry plane is perpendicular to the screen, and again, no change in the sign of the MO. So this is also A1. This is B2. This is B2 because first, when you do rotation, the sign will change. The gray will go here, the white will go here if you rotate this atomic orbital 180 degrees. And also, this is B2 because if you draw a symmetry plane here, right in the middle, cutting through the screen, and you do a reflection about this plane, and then the sign will change. So that's why it's B2. This is B1 because first, when you rotate this, the sign will change. And also, if you do a reflection with respect to the plane of the screen, the sign will change. So it's B1. And also, we are looking at atomic orbitals of the hydrogen atoms. There are two hydrogen atoms, one here, one here. They can have the same phase, all right? And then this is A1 symmetry. This is symmetric with respect to all four different operations. One identity operation, that means doing nothing, a rotation, and also two reflections because we have two symmetry planes. One symmetry plane is the screen, just right here. The surface of the screen is one symmetry plane. Another one is perpendicular to the screen, cutting through this middle point, all right? So that's why it's A1. This is B2 because when you do a rotation, just like this, when you do a rotation, the sign will change. And when you do a reflection with respect to a plane perpendicular to the screen, so this plane, I'm just cutting through this, the sign will change. And you do a reflection, the sign will change, just like this. And now, how do the atomic orbitals on oxygen and the atomic orbitals on the hydrogen atoms interact? You have to make sure that you use atomic orbitals with the same symmetry. So over here, A1 will interact with this A1 and this A1. This B2 will interact with this B2. Nothing will interact with this B1, so this B1 is just going to be non-bonding. All right, this B1 is going to be non-bonding. I'm going to just draw B1 right here. So it's from B1, right? B1. Okay, these three actually are degenerate energy levels. Px, Py, Pz have the same energy. All right, so just we'll draw a horizontal dash line to here. This is B1 because there's no interaction between this B1 atomic orbital with the hydrogen atoms. Okay, if you look at these two hydrogen atoms, they do not have any B1 here. There's only A1 and B2. Now let's look at B2. So this is B2, and we see a B2 here. So we have a B2 here, a B2 here. All right. So when you have two B2, they interact just because they have the same symmetry, and also they have fairly close energy level. So I predict the interaction will be fairly strong. So over here, this one will be lower to here. A new B2, this one will be kind of shifted up to here. So this will contain a bit more atomic orbitals from hydrogen. This one will contain a little bit more character from the oxygen. But again, this is B2, this is B2. They keep the B2 symmetry. Again, if you do a rotation, the sign changes. If you do a reflection about this plane, the sign will change. Same here. If you do a rotation, the sign will change. If you do a reflection with respect to a symmetry plane that's perpendicular to the screen, again, the sign will change. The black will go here, the white will go here. All right, finally, A1, A1, A1. So it's a little complicated. You have A1, A1, A1. How do we kind of draw the interactions? One way is this. If you're familiar with MO theory, you can just do this just right away. You form three A1 molecular orbitals. But for me, I usually do this. I find this A1, and I pick one of these two. All right, which one? I'm going to look at the energy levels of this two. Which one is closer to this A1? I think this looks closer to this A1. That means this two will interact more strongly. So I will allow this blue and this blue to interact first, and then I will shift the lower orbital down and higher orbital up. And now I get this new A1, this also a new A1. So I got two new A1s already in the middle. And then I will allow this A1 to interact with this A1. So we have these two A1s. I will shift this down. All right, because when you have two orbitals interacting with each other, the lower energy orbital will become even lower. The higher energy orbital will become even higher. So when you have this interact with this, that will shift this one down. So this one will go here, and this one should be bumped up a little bit. All right, so this one was maybe here, and then after interacting with this, it's bumped up a little bit. Now we have three A1s, we have two B2s, we have this B1, that means non-bonding orbital right here, non-bonding MO over here. And then we have a complete molecular orbital diagram. Now let's look at this A1. This A1 contains more than 50% of this orbital, less than 50% of this orbital. But if you just look at this, I mean, this is a picture I got from Wikipedia, so it doesn't reflect that. But anyways, they are in phase. That's correct. All three s orbitals are in phase. You have just a bonding MO. Over here, mostly it's in phase. You can see these two are in phase. The oxygen and this hydrogen are in phase. Both are white colors, and these two are black colors. The oxygen and the hydrogen on the right are also in phase. This one also a bonding orbital, but not very strong bonding. You can see a very small black over here, and this is black, black, black. They are in phase. This one is entirely non-bonding. Entirely non-bonding. This is just the 2px orbital from the oxygen. There's no interaction between the oxygen 2px and the hydrogen. Again, the symmetry does not match at all. You have B1 here, but I can't find any B1 on this side. There's no interaction. Another A1, this is a highest energy A1. This is like a sigma star. You have this two out of phase, white and black out of phase. This white and this black also out of phase. So it's anti-bonding MO, and this one is also anti-bonding MO. Again, this is these two are out of phase. These two are out of phase. So if you look at this picture, it seems like we have three bonding orbitals, and then one non-bonding, and then two anti-bonding orbitals. Well, then you may ask, do we really have 1, 2, 3, 4, 5, 6 bonding electrons, and therefore the bond order is 3? Of course not. In water, the bond order is 2 in total. Oxygen form 1 bond to the left hydrogen and 1 bond to the right hydrogen. So what happens here is this one is actually between non-bonding and bonding. Okay, if you look at this lobe, really small. The interaction here, yes, it's a in-phase interaction. It's constructive interference, and over here constructive interference. But this constructive interference is so small, so it's kind of more like non-bonding, a little bit bonding. Okay, over here, let's look at this. Mostly it's bonding because you can see strong constructive interference between these two white lobes, and also very strong constructive interference between the two black lobes. However, if you just cut this p orbital into two halves, all right, the top half does not really take part into the interaction. So the top half is more like non-bonding. So this is also a mixture of non-bonding and bonding. This is a mixture of non-bonding and bonding. So these two together, well, I wouldn't say the combination of this will give you kind of one non-bonding and one bonding. This is almost completely bonding. All right. So although you have 3 bonding orbitals fully occupied by 6 electrons, essentially the bond order in the water molecule is 2. Just because over here we have also non-bonding character from those MOs. These two are just definitely anti-bonding. This is 100% non-bonding. Over here, 100% non-bonding. Alright, let's look at the MO of water again. This time some different pictures. I think I generated all those pictures using computational chemistry software. We have the character table here, and hopefully you understand what those numbers means. +1 means symmetric, -1 means anti-symmetric or changing sign. Alright, this E means identity operation. This is rotation about the z-axis for 360 over 2 degrees, which is 180 degrees. Sigma V is a symmetry plane that contains this principal rotational axis. You have XZ plane, you have YZ plane, that's why, and you have 4 different so-called irreducible representations. Why such a name? Well, it's from actually linear algebra. You might have to take more advanced linear algebra to fully understand group theory. But for now, let's just look at a few MOs. This is definitely bonding MO. You see strong constructive interference. Also here B2, bonding orbital. Constructive interference constructive interference between the oxygen and this hydrogen. Let's just on top just a little bit. You have non-bonding. Actually, over here you have a little bit non-bonding from here too. Now let's look at this. This is also a mixture of bonding and non-bonding. So this part is mostly non-bonding, but on the bottom, well, I think we still see a little bit constructive interference. So a little bit bonding, a lot of non-bonding. This one, this B1, is 100% non-bonding. So none of the orbitals from the hydrogen atom take part in this MO. So this MO is actually just one atomic orbital centered on the oxygen atom. And then antibonding orbitals, we have two of them. You can see destructive interference over here, destructive interference over here. Same here, destructive interference, destructive interference. These two are occupied. Now let's look at methane. Methane is more complicated. Methane belongs to this TD point group, and in this TD point group, we have A1, A2, E, T1, T2 irreducible representations. And the four carbon-hydrogen bonds can be described by, well, this four wave functions. The first one belongs to the A1 symmetry, completely symmetric. And then the last three belong to a so-called T2 irreducible representation. This T means triply degenerate. All right. So now let's look at those wave functions. The first wave function is A1 symmetry. You have carbon 2s, and you have hydrogen A, hydrogen B, hydrogen C, hydrogen D. All contribute to this MO. So what does this mean? This means you have just the 2s orbital of carbon at the center, and then surrounded by four 1s orbitals of the four hydrogen atoms. And all those atomic orbitals are in phase, so it's completely symmetric. Now T2, that means you have, well, some negative signs here and here, here and here, here and here. So I'm going to show you just one picture. One of the T2, all right? So over here, you can see you have 1s orbital at these two corners, white color, and also two 1s orbitals from hydrogen, blue colors, and then a p orbital. This is px, centered on the carbon atom, and you can see constructive interference over here between this px and this 2s, and also you can see constructive interference between this lobe of 2px and this 2s orbital. So this is indeed a bonding orbital, but it's kind of strange. In the middle, there's actually a planar nodal surface that you can use to cut this CH4 into two halves. You know, the left half is constructive, the right half is also constructive interference. And also we pay attention to the delocalization of the MO. This is just one MO delocalized over the entire CH4 molecule. So you can see everywhere you see some lobes, you have contribution from the 2px of carbon. You also have contribution from 1, 2, 3, 4, all four hydrogen atoms. So when you look at symmetry adopted molecular orbital theory, usually those MOs are delocalized over the entire molecule. Remember, when we study the localized MOs are localized or concentrated on just one single bond or one lone pair. But now over here, we're looking at actually four bonds. There's a bond here between these two. There's a bond here between carbon and this hydrogen. There's a bond here between carbon and the third hydrogen, and then between carbon and the fourth hydrogen. Now we're looking at all those MOs. The bottom four are bonding MOs. The top four are anti-bonding MOs. Let's look at the bottom one first. A1 symmetry. You have 2s orbital from carbon and then 1s orbital from each of the four hydrogen atoms. They are all in phase, so it's just completely constructive interference. So this is a bonding orbital. Now these three are degenerate. It's T2 symmetry. You can see it's still constructive interference between this carbon and this two hydrogen atoms, also between this carbon and the other two hydrogen atoms. Same here, you can see constructive interference between this carbon at the center and the two hydrogen atoms on top. Also, it's constructive between the carbon and the two hydrogen atoms on the bottom. Same here, constructive interference. Now, destructive interference. On top, you have red on top of this carbon, but the two hydrogen atoms are blue. Different colors out of phase. Same here, different colors out of phase. Different colors out of phase. And this one is also not anti, it's just anti-bonding MO. It's anti-bonding MO because if you look at carbon, it's 2s orbital with red color. Now let's look at the 4 1s orbitals from the 4 hydrogen atoms, blue color. Out of phase, anti-bonding. Now, just in summary, we have a total of 8 MOs, and 4 are bonding MOs, 4 are anti-bonding MOs, and indeed we have actually 4 bonds. So approximately the bond order of this, and this, well, are just 4 ones. Bond order is 1 1 1 1 approximately. Chapter 21, Molecular Orbital Theory, Section 21.9, the Herkel Method. The Herkel Method can be used to predict the molecular orbital energies and resonance energies of conjugated cyclic and acyclic polyenes. For example, we can use the Herkel Method to calculate the molecular orbital energies for 1,3-butadiene. 1,3-butadiene contains 4 carbon atoms, each contributing a 2p orbital and a 2p electron to form the conjugated system. The Herkel method involves solving this equation for 1,3-butadiene. On the left-hand side, we have a 4x4 determinant because over here we have 4 MOs. Each consists of some contributions from the 4 2p atomic orbitals. And H sub ii are called Coulomb integrals. Hi different from J are called resonance integrals. S sub ij is the so-called overlap integral. For simplicity, we're just assuming S sub ii is 1 and S sub I different from J is just 0. This is the approximation for us to use to solve this determinant. We also set H sub ii to be alpha, Hij to be beta, when I and J are different. Both alpha and beta are negative. For most polyenes, beta is around 10% of alpha, and alpha is simply the 2p atomic orbital energy of carbon. We can look up this value. It's roughly negative 11 electron volts, or negative 1,100 kilojoule per mole. Now let's look at this Herkel method. We can expand this 2x2, 4x4 determinant in this form. So over here we have diagonal terms. We have Hii minus epsilon Sii as alpha minus epsilon. It's just because Hii is alpha, H11 is alpha, H22 is alpha, H33 is alpha, H44 is alpha. And then minus epsilon times S11, epsilon times S22, epsilon times S33, epsilon times S44. And again, S11 is 1, S22, S33, S44, they are all 1. So that's why we have diagonal terms like this. Now beta. When I and J are different, we have a beta here. But why is this 0? Because this carbon is adjacent to this carbon. There's a resonance integral between these two neighboring carbon atoms. However, between carbon 1 and carbon 3, there's no resonance integral. Between carbon 1 and carbon 4, there's no resonance integral. That's why you put 2 zeros here. Now let's look at carbon 2. Over here, this is H22. And on the left-hand side, you have beta. On the right side, you have beta because carbon 2 is bonded to both carbon 1 and carbon 3. That's why you see beta on the left and right-hand side. Now let's look at carbon 3. Okay, this is carbon 3. Alpha minus epsilon, which is H33 minus epsilon times S33. And also, you have a beta on the left, a beta on the right. Because this carbon 3 has carbon 2 on the left, carbon 3 on the right. Therefore, you have 2 resonance integrals in this row, one on the left, one on the right. Finally, carbon 4. When we look at carbon 4, well, there's only one carbon on the left, so therefore we have only one beta in this 4th row. And over here we have a 4x4 determinant. We need to expand this determinant and solve the equation. There's a systematic way to expand determinants, so you can use this term, alpha minus epsilon, multiplied by a 3 by 3 determinant. And then this beta multiplied by also a 3 by 3 determinant. That consists of 1, 2, 3, 3 elements here, 3 elements here, and 3 elements here. And when you look at the second row, you need to change sign. So it's really negative beta times a determinant with the first column as beta 0, 0, second column as beta alpha minus epsilon beta. The third column should be 0 beta times 0 beta and alpha minus epsilon. And then plus 0 times another determinant. Anyway, 0 times the determinant is just 0. This 0 times the determinant is 0. So we can expand this 4 by 4 determinant, and we get this kind of expression. This is the fourth order polynomial function of epsilon. We're going to solve this polynomial equation. Using the Huckel method, again, we can assume Sii is just 1, Sij is just 0, and we set Hii is alpha, Hij is beta, if I and j are adjacent to each other. Again, over here, alpha is simply the 2p atomic orbital energy of carbon, roughly negative 11 electron volts, or negative 1100 kilojoule per mole. Beta is the so-called resonance integral. This beta contributes to the pi bonding energy, and later you'll see also resonance energy. We do have to solve this 4 by 4 determinant. I talked about how to set up this 4 by 4 determinant. In the diagonal term, you just have alpha minus epsilon for the diagonal term, and then you need to examine the situation for every single carbon. So carbon 1 is bonded only to carbon 2, so you just put beta here, and then 0 here, 0 here. Carbon 2 is bonded to both carbon 1 and carbon 3. That's why you have 2 betas on the left and on the right. Carbon 3 also is bonded to 2 carbon atoms, carbon 2 and carbon 4. That's why you have 2 betas here in this row. And carbon 4 is bonded to only carbon 3. That's why you see only 1 beta. We can expand this 4 by 4 determinant, so we get this polynomial equation, and then we can somehow simplify this polynomial function. We get this. Now, how do we solve this? One way is to do variable substitution. If we set x to be alpha minus e squared, we'll simplify this fourth order polynomial equation to just a quadratic function. We'll solve this x. How do we solve x? Well, it's just pretty simple. I think we just need to use negative b plus minus the square root of b squared minus 4ac over 2. That's over 2a. That's just the standard solutions to quadratic equations such as ax squared minus b, plus bx plus c equals 0. So we get this kind of solutions in terms of beta squared. We have 2.6 beta squared. We have 0.38 beta squared. And now alpha minus e is simply the square root of this, or the square root of this. And therefore we solve for alpha minus e to be plus minus 1.6 beta, or plus minus 0.6 beta. Why do we have 4 different solutions? Well, this is a fourth order polynomial equation. That's why we have 4 different roots or solutions. The 4 MO energy levels of butadiene are determined to be epsilon equals alpha plus 1.6 beta, alpha plus 0.6 beta, alpha minus 0.6 beta, alpha minus 1.6 beta. Remember, both alpha and beta are negative. Alpha is negative 11 electron volts. Beta is usually 10% of alpha, so all those are negative. And the 4 pi electrons should occupy the 2 lowest energy levels. So I would say these 2 energy levels with more negative energy. The total energy of this 4 pi electrons is going to be 2 times this energy and 2 times this energy. Altogether, you get 4 alpha plus 4.472 beta. Now let's look at the resonance energy. The resonance energy is the total energy of this 4 pi electrons in resonance over here, minus, well, over here 4 alpha plus 4 beta are the total energy of 2 separated double bonds, and the difference is 0.472 beta, and this is the resonance energy in 1,3-butadiene. Again, 4 alpha plus 4 beta is the energy of the 4 pi electrons of 2 separated pi bonds. How do we compute the bonding energy or molecular orbital energy for ethane? Well, ethane contains only 2 carbon atoms, so we can write a 2 by 2 determinant this way, and we solve this equation. We get epsilon is equal to alpha plus beta, epsilon is alpha minus beta. So for the ethane molecule, the 2 pi electrons should occupy this energy level. The total energy would be 2 alpha plus 2 beta. Now, what if you have a molecule that contains 2 separated double bonds, unconjugated, and then, well, for each double bond you have this much energy, and for the second double bond you have this much energy. Therefore, the total is 4 alpha plus 4 beta. Again, get back to 1,3-butadiene. The total energy of the 4 pi electrons is 4 alpha plus 4.472 beta. So we can take the difference. We get the resonance energy for 1,3-butadiene, which is roughly 0.5 beta. Using the Huckel method, we can also demonstrate that this cyclopropenyl cation C3H3 plus is aromatic. And we can again look at the structure over here. We have carbon 303 forming a ring structure. We have a plus charge on the entire molecule, and this plus charge is delocalized over the entire molecule. Now let's write out a 3 by 3 determinant, because we have only 3 carbon atoms, each contributing 1 2p atomic orbital. So 3 2p orbitals will make 3 MOs. Since we make 3 MOs, we need a 3 by 3 determinant to determine the molecular orbital energies for the 3 MOs. So again, the diagonal term has to be alpha minus epsilon, all 3 diagonal elements, and then off diagonal elements, it's beta beta here, beta beta here, beta beta here. Why 2 betas in the first row? Because carbon 1 is bonded to carbon 2 and also carbon 3. That's why you see 2 betas here. This is a ring structure. This is a ring structure, and that's why each carbon is bonded to 2 carbon atoms, and therefore you need 2 betas in this every single row. Solving this equation, it's doable. I mean, it's just a 3 by 3 determinant, so you can use this term times this term times this term, and then you can use beta times this beta, and then finally beta times this beta. You get 3 positive terms, and you also have 3 negative terms, which is this beta times this. That should be negative, and then beta times this, and should be negative, and also beta times alpha minus epsilon. That's also a negative term. So you combine 3 positive terms, 3 negative terms. You combine everything, you get one single third order polynomial equation. Set it to 0, we solve it, we get 3 roots. It's going to be alpha plus 2 beta, and then alpha minus beta, and alpha minus beta. So this too means we have degenerate molecular orbitals. Alright, 2 molecular orbitals with the same energy. Now if you look at this structure, we are carbon 3H3 plus. That means we have only 2 pi electrons. So these 2 pi electrons will occupy this MO, the lowest energy MO, and the total energy will be this times 2, which is 2 alpha plus 2 beta, 4 beta. So this alpha plus 2 beta multiplied by 2, we get 2 alpha plus 4 beta. Now let's consider just a isolated carbon-carbon bond. What's the molecular orbital energy? It's just 2 alpha plus 2 beta. So compare this and this, you can see over here we have 4 beta, here we have only 2 beta. The difference is 2 beta. We have a lot resonance energy in this structure. It's 2 beta. The value is 2 beta. It's larger than 0.5 beta for 1,3-butadiene, and therefore this ring structure of carbon 3 hydrogen 3 plus is a aromatic structure. Now finally, let's look at benzene. When you look at benzene, there are 6 carbon atoms. Each carbon atom contributes 1 2p atomic orbital, and we have a total of 6 2p atomic orbitals forming 6 MOs. So you're looking at the 6 MOs here, the lowest energy MO, second lowest energy MO with a degeneracy of 2, and then these 3 are kind of just anti-bonding pi orbitals, and these 2 MOs are also degenerate. Finally, we have the highest energy MO over here. Now if you look at the number of nodes that cut through the benzene ring, zero nodes over here. We have a node that cut through this benzene ring, 1 node here, or over here also 1 node. This is just vertical, this is a horizontal node. And over here there are two nodes, 1, 2. There are two nodes. Over here, two nodes, 1, 2. And over here we have three nodes, 1, 2, 3. So as the number of nodes increases, the energy of the molecular orbital also increases. Now let's look at this 6 by 6 determinant. Just because we have 6 MOs formed from 6 conjugated p orbitals, we need to solve this 6 by 6 determinant. We set it to 0. Now the diagonal elements are all alpha minus epsilon. But now this is carbon 1. Carbon 1 is bonded to carbon 2 and also carbon 6. That's why you see two betas in this row. And now carbon 2 is bonded to carbon 1 and carbon 3, etc. Finally, this is carbon 6. Carbon 6 is bonded to carbon 5 over here. It's also bonded to carbon 1. So that's why you also see two betas in the last row as well. So this is a ring structure. That's why each carbon is surrounded. It's bonded to two neighboring carbon atoms. Now we just solve this. How do we decompose a 6 by 6 determinant? Well, it's non-trivial. I'm not going to show you every single step. I would use a program. I would write a simple computer program to solve this, and I'll just tell you what the solutions are. So over here we have energy alpha plus 2 beta, alpha plus beta, alpha plus beta. This is alpha minus beta over here, alpha minus 2 betas. Alright, remember alpha and beta are both negative. For carbon, alpha is roughly negative 1100 kilojoule per mole, and beta is roughly 10% of alpha. That's why these three MOs have lower energy. Alright, and now we occupy those MOs with 6 electrons. And now let's look at the total energy. It's going to be 2 times alpha plus 2 beta, and then 2 times alpha plus beta, and then 2 times alpha plus beta. We get 6 alpha plus 8 beta. 6 alpha plus beta, 8 beta. And now let's consider 3 isolated carbon-carbon double bonds. Well, that would be 6 alpha plus 6 beta. Now we have 6 alpha plus 8 beta. What's the difference? The difference is 2 beta. So 2 beta, again, is the resonance energy of benzene. Benzene is an aromatic compound with significant resonance energy. And now if you look at similar structures for carbon 4 H4, a ring structure with 2 double bonds, you're going to get 4 MOs. You're going to get 4 MOs, but unfortunately in that case, you will not get any resonance energy. So actually carbon 4 H4, the ring structure with 2 double bonds, is so-called anti-aromatic. Chapter 22, Electronic and NMR Spectra of Molecules. Section 22.1, Microstates and Molecular Terms of Diatomic Molecules. In a diatomic molecule, the molecular axis is a z-axis by convention. For example, when we have a H2 molecule, usually we define the z-axis to be the axis that passes through the 2 hydrogen nuclei. And also this z-axis passes through the center of sigma G and sigma U star. The z components of L and S are denoted by m sub L and m sub S. L is the orbital angular momentum, and the S is the spin angular momentum. In a diatomic molecule, the electrons can only rotate about the internuclear axis, which is the z-axis. For example, we can rotate this sigma star U about the z-axis. We can rotate this sigma G about the z-axis. But we cannot rotate this about the x or y-axis. Now let's assume we have a y-axis here. We cannot rotate sigma G about this y-axis, because if we did that, well, the electron wave will be moved away from the nuclei, and this is unphysical. So if we rotate this, the electron wave, the center of these 2 lobes, will be moved away from the center of the nucleus. That's unphysical. Therefore, the rotations of the electrons about the z-axis of the molecule are two-dimensional rotations, not three-dimensional rotations. We have learned this before. For a two-dimensional rotation, well, m sub l can only be negative L or positive L, nothing in between. Only two options for m sub l. We have a degeneracy of 2. The electron spin is about the center of the electron, and therefore it's still a three-dimensional rotation for electron spin. Therefore, m sub s can be from negative s plus 1 all the way to s. So pay attention to the difference over here. M sub l can only be negative L or L, but nothing in between. M sub s can be from negative s to positive s. For electron in the sigma orbital, m sub l is 0. For electron in the pi orbital, L is 1, so m sub l is plus minus 1. And also, we can just use this to explain the lowercase m sub l is plus minus 1 for a p atomic orbital. And the pi orbitals are simply linear combinations of p orbitals. So we have this equation leading to this equation. What about the pz hyphen pz sigma orbital? Well, in this case, m sub l is 0, because for each pz you have m sub l equals 0, and then you have two of them, still the sum is going to be 0. So we learned this. A pz electron does not rotate about the z-axis. The pz hyphen pz sigma electrons do not rotate about the z-axis as well. Now let's look at a few examples of molecular terms. For hydrogen 2 in the ground electronic state, we have 2 electrons in the 1 sigma g bonding orbital. G denotes Gerarder or symmetric. M sub l is simply just 0. We have 2 electrons, each has a value of m sub l of 0. So 0 plus 0 is 0. We have 2 electrons paired, so 1 is alpha, 1 is beta. The sum of m sub s is 0. Because m sub l can only be 0, we have L must be 0. And because m sub s can only be 0, s is also 0. Therefore, we can easily write out the molecular term symbol for H2. The format is this. We have 2s plus 1 in the superscript. S is the spin number. And then we use a Greek letter here to denote the value of L. When this uppercase L is 0, 1, 2, 3, this Greek letter will be sigma, pi, delta, phi. Alright, so L is 0 for H2 in the ground electronic state. That means we just put sigma here. And then the multiplicity is just 1. This is a spin multiplicity because S is 0. 2s plus 1 is 1. You have a singlet spin state. Just remember, when we look at the atomic orbitals in the hydrogen atom, when L is 0, 1, 2, 3, we learned those are atomic orbitals are SPDF. And then we studied the atomic terms for many electron atoms. And then when the uppercase L is 0, 1, 2, 3, we have SPDF atomic terms. Now we're looking at molecular terms. We simply use different notations. We use Greek letters, but sigma, pi, delta, phi, and gamma are just the Greek letters that correspond to SPDFG. So this is how you memorize those molecular terms. Now both electrons in H2 are sigma g, and therefore in total the symmetry is G, because G times G is G. If you have 2 electrons, one is G symmetry, one is U symmetry, then the total is U. If you have both electrons with U symmetry with respect to the center, the total wave function has a G symmetry because U times U is G. Over here you might just imagine G is +1, U is -1. And then you can derive all this all by yourself. -1 times -1 is +1. Now let's get back to the H2 molecule in the ground electronic state. Its molecular term symbol is simply 1 sigma G. This one means it's a singlet spin state. Sigma means the uppercase L is just 0. The electrons do not rotate about the intermolecular axis. And G is just the symmetry with respect to the center of the molecule. Now let's look at another superscript over here, because sigma orbitals are always symmetric with respect to the symmetry planes that contain the internuclear axis. We have 1 sigma G plus for H2 with one additional symbol, the plus sign in the superscript. This plus sign indicates the wave function of the electrons is always symmetric with respect to any plane that contains the internuclear axis. However, if the wave function changes sign with respect to any plane that contain the internuclear axis, then minus arises. Sorry about this typo. This is plane. Any planes. Alright. In summary, the molecular term of this is 1 sigma G plus. Again, the superscript 1 means it's spin singlet. Sigma means L is just 0. G means it's Garrotter symmetry, and plus means the wave function is symmetric with respect to any and all symmetry planes that contain the internuclear axis. Well, what if you have a wave function that's anti-symmetric to one of those planes that contain the internuclear axis? Then you need to replace this plus with minus. Now let's look at a more complicated situation. What if we excite an electron in H2 from the 1 sigma G bonding orbital to 1 sigma U star antibonding orbital? Now we have also molecular terms, and this time we have 1 sigma U plus, 3 sigma U plus. It's just because we can write out 4 microstates. These 3 are the T1 electronic state, three microstates, and this one is S1. So now let's look at the wave functions. If we look at the first 3 wave functions that belong to the T1 electronic state, they share the same spatial function, sigma 1 sigma star 2 minus sigma 2 sigma star 1. So it's just exactly the same. They differ in the spin part, alpha 1 alpha 2 beta 1 beta 2 alpha 1 beta 2 alpha 2 beta 1. In these 3 cases, M sub L is just 0 0 and 0, because those are just sigma orbitals, and we have just zeros. M sub S, when you have 2 alpha it's 1, when you have 2 beta it's -1, when you have this combination it's 0. Now let's look at the singlet. Also, the spin part times the spatial part times the spin part. But over here, the spatial part is symmetric. The spin part is anti-symmetric. Again, we have a degeneracy of 3 here and a degeneracy of only 1 here. But why are they like 1 sigma U plus, 3 sigma U plus? So first, the superscripts over here. 1 is the spin multiplicity. It's 1 for the S1 electronic state. But T1 has a degeneracy of 3 with a spin multiplicity of 3. So that's 3 here. And then why sigma? Because both electrons are still in the sigma orbitals. So as long as you have all electrons in the sigma orbitals, over here it's going to be sigma. L is going to be 0. And now U. Why U symmetry? It's just because 1 electron is in the G orbital, 1 electron is in the U orbital. So G times U is U. That's why you have U here, another U here. Now what about this plus sign in the superscript? It simply means, well, all these wave functions, so they're all plus. They're symmetric with respect to any refraction, with regard to any symmetry plane that contains the internuclear axis. Alright, it's just all symmetric with respect to symmetry planes. And then you have the plus sign. So in summary, the molecular terms of this H2 are 1 sigma U plus, 3 sigma U plus. If we have two electrons, one in the 1 sigma G orbital and the other in the 1 sigma U star orbital. What if we promote both the electrons to the 1 sigma U star orbital? Well, in that case, the molecular term is 1 sigma G plus. So first, when you have both electrons in here, it has to be 1 alpha, 1 beta. Overall, M sub S is 0, S is 0, the spin multiplicity is just 1. Now, why sigma? Again, they both are in the sigma orbitals, so this is going to be sigma with L equals 0. And the symmetry with respect to the center. This orbital has a U symmetry, but you have two electrons. So U times U is G. That's why the molecular term is still 1 sigma G, not U, with two electrons with U symmetry. Again, U times U is G. Finally, a plus. So again, in this case, we can also write out a wave function, which is, I think it's going to be, this part should be replaced with sigma star 1 times sigma star 2, and that's it. In that case, it's still symmetric if we do reflection with respect to any symmetry plane that contains the hydrogen-hydrogen axis. So we get 1 sigma G plus over here. There are guidelines on determining the molecular terms for the second row homonuclear diatomic molecules. If all MOs are completely filled or completely empty, plus applies. The wave function is going to be symmetric upon reflection. This is because when the MO is doubly occupied, its wave function is always symmetric. If we look at this lithium-2 as example, you can see two electrons appeared in the 2 sigma G orbital. Therefore, the molecular term is 1 sigma G plus. 1 means the spin multiplicity is 1. Sigma is symmetry determined by the value of L. In this case, L is just 0. This molecular term has a G symmetry because you have two electrons, both are in the 2 sigma G orbital. G times G is still G. And the wave function is symmetric upon reflection. What if we have partially filled MOs? Well, if we have partially filled MOs with a sigma symmetry, so mostly, you can view this as a sigma bonding orbital, then plus applies. It's just because a sigma orbital is always symmetric upon reflection through any plane that contains the molecular axis. Alright, you can just imagine, this is quite different between a sigma orbital and a pi orbital. So if you have a sigma orbital between two atoms, and no matter how you choose a plane, that contains the two nuclei, the sigma orbital is symmetric with respect to just any symmetry plane that contains the two nuclei. However, if you have a pi orbital, things are different. If you have a pi orbital, for example, in ethylene, and then a reflection with respect to a plane that contains all atoms would be antisymmetric. So that's the difference. Now let's look at lithium-2 minus. Well, when we look at lithium-2 minus, we do have one additional electron in the 2 sigma U star orbital. Alright, let's just look at the electron. We have a spin multiplicity of 2. That electron can be alpha or beta with U symmetry because that single electron occupies the 2 sigma U star orbital. And it's a sigma orbital, so we have sigma here. And the wave function, again, is still symmetric upon reflection. For the ground electronic state of carbon 2, 4 electrons occupy the 2 degenerate pi u orbital. All MOs are completely filled, so plus applies. All electrons are paired, so S is 0, and also L is 0. The symmetry, well, we have 4 electrons. They are all in the pi u orbitals. So U times U times U times U is still G. So in the end, it's still G. So the molecular term for C2 is 1 sigma G plus. What if we remove an electron from the C2 molecule? We get C2 plus. Well, then the molecular term symbol becomes 2 pi u minus. Look how different it is. 2 pi u minus, alright, versus 1 sigma G plus. So first, when you have 3 electrons in the 2 degenerate pi u orbitals, well, you have a spin multiplicity of 2. And you have a pi orbital singly occupied. So in that case, L is 1, M sub L is minus 1 or plus 1. Alright, so that's why you have a pi. Why U symmetry? Well, 3 electrons, right? U times U times U is U. And then minus over here, now a pi orbital is anti-symmetric with respect to plane reflection, and you have a single electron in this pi orbital, therefore it's minus. If you have 2 such electrons in the same pi orbital, then minus times minus, you get plus. Now let's look at the more difficult cases, O2 and B2. They have the same molecular terms. Let's talk about maybe O2 first. For partially filled MOs of pi symmetry, such as in O2, if sigma arises, the triplet is minus, the singlet is plus. The ground state for O2 is 3 sigma G minus. I'm going to explain this a little bit over here. First, if you have O2, you have 2 electrons in the 2 degenerate 1 pi G star orbital. So you can have alpha, alpha, beta, beta, alpha, beta, beta, alpha. Right? And you have a total of 6 different microstates. Well, I forgot to mention that you can have alpha, beta in this one, and alpha, beta in this one. Alright? So let's look at all 6 different microstates. M sub L for electron 1, M sub L for electron 2. They can be plus 1 or minus 1. Okay, they cannot be 0 because we're talking about 2-dimensional rotation here. When you have a diatomic molecule, yes, the electrons can rotate about the nucleus, but it's going to be just 2-dimensional rotation about the z-axis. That's it. Well, the electrons cannot rotate about the x or y axis. So M sub L can be either negative L or positive L. So that's why you have these options. The sum is going to be 2 over here, minus 2, 0, and 0. What about M sub S? Well, although we have a diatomic molecule, you know, the electrons can rotate about the internuclear axis only, but if you're talking about spin, it's still 3-dimensional spin, so about its own axis. So that's why we have this alpha beta, and over here beta beta, beta alpha beta, alpha alpha. So all different kind of combinations, and we have 6 different microstates. The first 2 microstates can be combined into just a 1 delta molecular term. So why it's 1 delta? So first, the 2 electrons are alpha beta. So the spin multiplicity is just 1. Why delta? Delta means L is 2. Delta means L is 2. When L is 2, M sub L should be minus 2 or positive 2 for 2-dimensional rotation. So we do see minus 2 plus 2 here. Alright, we can combine this 2 1s, we get 2. We combine this 2 negative 1s, we get negative 2. So when you see M sub L can be 2 or minus 2, then L is just 2. When L is 2, we use delta. Alright, so when L is 0, 1, 2, 3, we have sigma, pi, delta, and phi, Greek letters. Now this 4 microstates can be grouped into 2 terms. One is 3 sigma g and then 1 sigma g. This is 3 sigma g. S is 1, M sub S can be negative 1, 0, and 1. Over here, S is 0, M sub S is 0. In both cases, we have this sigma here, sigma symmetry here, because L is 0. You can see L is 0, L is 0. Because M sub L is 0, M sub L can only be 0, therefore L is 0. If L is 0, we use this Greek letter sigma. Now, why G symmetry? Well, it's just, these two electrons are in the G orbitals. G times G is G. So both are G, alright? Both are G over here. And then we use this rule. If sigma rises, triplet is plus, the singlet is plus, triplet is minus, singlet is plus. So we get this molecular terms. The deeper reason for this is, again, we need to kind of examine the wave function for the electrons and see if it's symmetric or anti-symmetric upon reflection. But for now, we're going to just use those rules. If sigma rises, the triplet is minus, singlet is plus. And then we get the three molecular terms for O2. 1 delta, 3 sigma g minus, 1 sigma g plus. In B2, we have the same three molecular terms. In B2, we have 2 electrons in the 1 pi u orbitals. Again, 6 microstates. Again, this kind of combinations, I think it's going to be exactly the same 6 microstates, and then same molecular terms. B2 can also be assigned into 1 delta, 3 sigma g minus, and 1 sigma g plus. You do need to pay attention to this U symmetry here, but since we have 2 electrons in these orbitals, U times U is still G. In both O2 and B2, this 3 sigma g minus has the largest spin quantum number and therefore the lowest energy. Alright, 1 delta and 1 sigma g plus, they both have higher energy than 3 sigma g minus, because again, this one has the largest spin multiplicity. Now let's look at a heteronuclear diatomic molecule, OH. It's really a radical, but we're going to just use this as example. We use usually uppercase XAB to denote the ground first and second electronic state with the same spin. So X is the ground electronic state over here, and followed by A and B, uppercase A and B. They share the same spin quantum number, so you can see this 2 as the spin multiplicity, 2, 2, 2. Alright? What if you have other electronic state with a different spin? Well, then you use lowercase a and b. I think you see a lowercase a here, lowercase a for sigma, lowercase b, for pi. So you have a spin multiplicity of 4, a different spin, and then you use lowercase. For the OH radical, the spin multiplicity in the ground electronic state is 2. Alright, again, lowercase ab are the first and second excited state in a different spin state. Alright, over here multiplicity is 4, and this one multiplicity is 2. And when you see a spin multiplicity of 4, that means 2s plus 1 is 4. S is 1.5. You have 3 unpaired electrons. Over here, when the spin multiplicity is 2, S is 0.5, you have only 1 unpaired electron. Electronic transitions between molecular terms with different electron spin multiplicity are strictly spin forbidden, so we don't see that much. Extremely weak intensity. For example, any transition between a doublet spin state and quartet spin state is spin forbidden. It's extremely slow. So from this x to pi to, for example, this A4 sigma, it's going to be extremely slow, extremely rare. The potential energy curve of a diatomic molecule such as OH is shown below. Over here we have this x2 pi electronic state as the ground state. In this ground electronic state, the 1s orbital of hydrogen and 2pz orbital of oxygen form a sigma bonding orbital, sigma star antibonding orbital, and we have 2 electrons fully occupied the sigma bonding orbital. And since this is fully occupied, these 2 electrons do not contribute to the determination of the molecular terms. We just need to look at the unpaired electron in oxygen in this sigma star. It has m sub l equals plus minus 1, m sub s equals plus minus 1/2, which results in the sum is plus minus 1. The sum of spin is plus minus 1/2. So L is just 1, S is 1/2. When L is 1, the grid ladder is pi. When S is 1/2, the spin multiplicity is 2. Therefore, it's 2 pi over here. Right? It's just because there's one unpaired electron in this ground electronic state, and that electron is in one of the p orbitals in oxygen. Now let's look at some other cases. In the first excited electronic state, one electron occupies the sigma orbital, and all other electrons are paired. So we need to focus on this sigma orbital, singular occupied. Therefore, we have a spin multiplicity of 2. And since this is a sigma orbital, we write sigma here, and it's a plus because the wave function is going to be symmetric with respect to any symmetry plane that contains these 2 atoms. We do not write G or U in the subscript, only because in this OH molecule there's no inversion center. Chapter 22: Electronic and NMR Spectra of Molecules. Section 22.2: Electronic Transitions and Selection Rules. Any electronic transition that involves the change of the electron spin state is forbidden with nearly zero intensity because the integral of alpha star beta is 0. The integral of beta star alpha is also 0. Star denotes the complex conjugate, the intensity of a spin allowed transition, such as from alpha to alpha or from beta to beta in an atom or molecule, is proportional to the squared modulus of the transition dipole moment, which is a vector here, mu superscript mn with an arrow, and the intensity is proportional to squared modulus of this vector. We can prove this statement if you like to watch this 23-minute proof here in my YouTube channel. The transition dipole moment can be expressed as the sum of 3 components in the x, y, and z directions. I, j, k are the unit vectors in the x, y, and z directions. And then mu superscript mn sub x is the x component, y component, and z component here. Let's look at the x component of the transition dipole moment. It's the integral of the wave function of the mth electronic state multiplied by this x component of dipole moment multiplied by the wave function of the nth electronic state. So we can evaluate this mu sub x, mu sub y, mu sub z separately. And again, x, y, z are the x, y, z components. Over here, mu x, mu y, mu z are the components of the electric dipole moment expressed here. And with m and n in the superscript, it's the so-called transition dipole moment, which is also a 3-dimensional vector with 3 components in the x, y, and z direction. An electronic transition is allowed only if this transition dipole moment is non-zero. As long as it's non-zero, its squared modulus is positive, and then we have a finite intensity to observe this transition. But if this is 0, then we say the electronic transition is forbidden. But how can we determine if the transition dipole moment is 0 or non-zero? Well, we will have to evaluate three integrals, these three, the x, y, and z components of the transition dipole moment. If all three are 0, then the vector of transition dipole moment is 0. The electronic transition is going to be forbidden. If any one of these three integrals is non-zero, then the transition dipole moment vector is non-zero. We will be able to observe this transition as long as it's also spin allowed. The intensity of a spin-allowed transition in an atom or molecule is proportional to the squared modulus of the transition dipole moment. Here's an example. If we're looking at the electronic transition from 1s alpha to 2s alpha in a hydrogen atom, this is going to be forbidden because its transition dipole moment is 0, the squared modulus is also 0. However, if you have an electronic transition from 1s alpha to 2px alpha, that's actually allowed, both spin allowed and spatial allowed. Now let's look at these two examples in detail. From 1s alpha to 2s alpha, it's spin allowed from alpha to alpha. Now let's look at the spatial intensity, spatial probability. So let's look at this x components. This is mu sub x with MN in the superscript. M and N represent the initial and final electronic state. So now let's plug in all those equations. C is a constant. Now we need to integrate this integral and also a spin integral. The spin integral is just 1 because the integral of alpha star alpha is just 1. Alpha is normalized. Really, we need to focus on this integral and see if this integral is 0 or non-zero. This integral is actually 0 because a 1s function and 2s function are even functions of x, and then in the middle we have an odd function of x. So if we look at the product, this entire product is an odd function of x. What does that mean? If we change the sign of x, we're going to change the sign of this product, and that means the integral is going to be 0. The integral of any odd function from negative infinity to positive infinity is 0 only because if you look at the graph of the integral, the left hand side and the right hand side have the same magnitudes but opposite signs, so overall the integral should be 0. And similarly, we can determine the y component and z component of the transition dipole moment. They are both 0. You just plug in y here. It's going to be an odd function of y. The integral of that product with respect to dy is 0. You can also replace this x with z to get the z component. Again, the integral of the product with respect to dz is going to be 0. So that's why we actually cannot observe the electronic transition from 1s alpha to 2s alpha if it's photon induced. Now let's look at this B. From 1s alpha to 2px alpha, this electronic transition is allowed. This is because now we still look at this integral and multiply by the spin integral. The spin integral is just 1, so we focus on this spatial function. We look at here, we'll plug in all the wave functions over here and here. You can see this 1s wave function is a even function of x. That means when x changes sign, it does nothing to to this wave function. But this 2px is proportional to x. So therefore, 1s times x times 2px is together is a even function of x, and that means this integral is not going to be 0. Again, you can even just use a more specific function for 1s, it's e to the power of negative r, and then 2px is x times e to the power of negative r over 2. If you integrate this from negative infinity to positive infinity, I think you'll get a positive integral value. That means this x component is non-zero, and that means the transition dipole moment is non-zero. When the transition dipole moment is non-zero, its squared modulus is non-zero, and the intensity is proportional to this, and therefore the intensity of observing this 1s alpha to 2px alpha electronic transition is positive. We can observe this. This is an allowed transition. More generally speaking, the selection rule for the electronic transition in the hydrogen atom is delta L is plus minus 1. The angular quantum momentum number must change by 1. The intensity of a spin-allowed transition in an atom or molecule is proportional to the transition dipole moment squared. For example, if we look at an electronic transition in water, the electronic transition from a A1 MO to a B1 MO is allowed, but from B1 to B2, that's forbidden, because we can actually look up the symmetry for X, Y, and Z vectors. Because when you have an electric dipole moment, that's the charge times the x, y, z vector. So somehow we can determine the symmetry of the electronic dipole moment in the x, y, and z directions. Again, x, y, z, let's look it up. X is B1, y is B2, and z is A1. Therefore, x, y, z correspond to B1, B2, A1 irreducible representations. Now, in the x direction, the A1 to B1 electronic transition dipole moment is the integral of a totally symmetric function. So A1 times B1 times B1. All right. This is the initial initial electronic state. This is a final electronic state, and this is the x component of the electric dipole moment. So A1 times B1 is A1 is completely symmetrical, and the integral of a completely symmetrical function is non-zero. So the x component is non-zero. Therefore, the entire vector cannot be zero. The transition is allowed. However, from B1 to B2, it's completely forbidden, because none of the x, y, z vector has a A2 symmetry. We can see if you have B1 and B2 in the integral, this is initial, this is final electronic state. In the middle, we need a A2. We need a A2 so that the product is A1. So that integral of this product is non-zero. However, you can see A2 over here. Neither x or y or z correspond to this A2 symmetry. Therefore, the electronic transition from a B1 molecular orbital to a B2 molecular orbital in water is forbidden. In the x, y, and z direction, the B1 to B2 electronic transition dipole moment is an integral of B2, B1, and A1 function. We can do this here. Again, the transition is from B1 to B2. And then in the middle, we have the symmetry for the x vector, y vector, or z vector. They correspond to the symmetry of the electric dipole moment. And the x is B1, y is B2, and z is A1. So you can see when we do this product, we get B2. So B times B times B is B. All right, B corresponds to kind of just the anti-symmetric with respect to rotation. 1 and 2 are referring to symmetric versus anti-symmetric about reflection. So B, 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 you get a B. B, A, B, you get an A. Because B times B is A. And then, you get A over here. And then let's look at 1, 1, 2. 1 means symmetric, 2 means anti-symmetric. So you can replace 1 with plus 1, 2 with negative 1. So plus 1, negative 1. The product is negative 1. So we put a B here. Plus 1, minus 1, so we put a 1 here. Plus 1, 2 means negative 1, so we have plus 1 times plus 1 times negative 1, we get a negative 1 here. So the result is B2 symmetry, B1 symmetry, A2 symmetry. None of these three is totally symmetric, so the integral of a B2 function is going to be 0. The integral of a B1 function is 0. The integral of A2 function is also 0. That means the x component, y component, and z component, they're all 0. The transition dipole moment factor has to be 0 if its three components are all 0. Therefore, B1 to B2 electronic transition in water is forbidden. And not only in water, just in any molecule with the C2V point group, the B1 to B2 electronic transition is forbidden. Using the character table, we can also determine if a vibrational transition is infrared allowed or Raman allowed. For example, we can look at the symmetry of the vibrational modes. The A1, B1, B2 vibrational modes are infrared allowed in any molecule that belongs to the C2V group. because you can look up the three electric dipole moment in the x, y, and z direction. X is B1, Y is B2, and Z is A1. So you just need A1 vibration mode to be allowed in the Z direction. B1, look up B1. Then this is going to be allowed in the X direction, and also there's a B2. You see B2 here. This vibration will be allowed in the Y direction. Alright, so this is how we determine if a vibrational transition is infrared allowed. Again, this molecule absorbs a photon, and it can be excited or de-excited as long as it's infrared allowed. To determine whether it's infrared allowed, you need to look up the symmetry of X, Y, and Z. They correspond to the symmetry of the electric dipole moment. So if you have B1, B2, or A1 symmetry, it's going to be allowed. All vibrational modes of a molecule in the C2V point group are Raman allowed, because for this to be Raman allowed, you need a vibrational mode with the same symmetry as one of this, either x squared or y squared or z squared or xy, yz, zx. You can see x squared, y squared, z squared. Those are A1, xy is A2, xz is B1, yz is B2. So pretty much no matter what you have, if you have A1, A2, B1, or B2, it's going to be Raman allowed. To check if it's Raman allowed or forbidden, you look for the second order functions such as x squared, y squared, z squared, or xy, xz, yz. You look for them and see if they are allowed or not. When a molecule possesses a inversion center, X, Y, Z are always U symmetry, while the components in the polarizability matrix are always G symmetry. Alright, so when you have an inversion center, X, Y, Z are always anti-symmetric with respect to the center. However, if you're looking at the second order functions, they are symmetric with respect to the inversion center. So what does that mean? Well, as long as you have a molecule with a inversion center, X, Y, Z will always be U symmetry, and all those second order functions will always be G symmetry. What does that mean? That means we can make a prediction. No vibration mode of a molecule with a symmetry center or inversion center can be both infrared and Raman active. If it's infrared active, it's definitely Raman inactive. If a vibration mode is Raman active, that means it has a G symmetry. It cannot be infrared active. But also, I just want to remind you that one infrared vibration mode can be both infrared inactive and also Raman inactive. Alright, so over here it's just infrared and Raman cannot be both active if you have a molecule with a center, inversion center. The intensity of a spin-allowed transition in a molecule not only depends on the value of the squared modulus of the transition dipole moment, it also depends on the overlap between the vibrational wave functions of the initial and final electronic state. The Frank Condon principle states that the electronic transitions are vertical transitions. What does that mean? That means, well, in a potential energy surface, when we do electronic transition, we draw the arrow up perpendicular to the horizontal axis, which is the nucleus coordinates. And simply it means the nuclear coordinates remain unchanged. When you draw a vertical line, that means over here, the positions remain unchanged. Why is that? It's just because the electronic transition is super fast. It takes about 10 to the power of negative 15 seconds. I think this is 1 femtosecond. And within such a short time period, all those nuclei do not have enough time to move. I mean, even if they do, they can move maybe a distance of maybe 1 picometer or even less. 1 picometer is 0.01 angstrom. So typically the bond distance is between 1 and 3 angstroms. And if you just change it by 0.01 angstrom, roughly we can say, well, the bond distance is unchanged. And now let's look at some vertical excitations. Let's say we have ground electronic state, and this is also the ground vibrational state with a wave function. Now we're going to do vertical excitation. So from here to here, not only we need to look at the transition dipole moment, we need to look at the overlap between this vibrational wave function and this vibrational wave function. So you can see we are from this really large value of vibrational function to a large vibrational function here. This is the maximum of a Gaussian function. This is also a maximum of a Gaussian function right here. So very likely from 0 to 2 transition, you will have a larger intensity than any other intensities. All right, and now let's look at examining from 0 to 0. Well, this from 0 to 0, you need the least amount of energy, but look at the overlap. Over here you have a maximum, but over here very low intensity from the vibrational wave function. All right, so that's why the intensity should be small. From 0 to 1, it's also small, because if you look at this, this is quite close to the tail of this Gaussian function, so not much. But from 0 to 2 in this graph, you can see this is the maximum of this Gaussian function, and this is the maximum of this Gaussian function. So from 0 to 2, you probably will see the largest intensity for this electronic transition. Again, the transition intensity is not only proportional to the squared modulus of the transition dipole moment, it also is proportional to the squared modulus of the overlap between the initial vibrational function and the final vibrational function. That's why the transition is like that. So when you look at this kind of transitions, in this diagram I said from 0 to 2, you have the largest overlap between this vibrational function and this vibrational function. So from 0 to 2, you probably will see a larger transition intensity. Chapter 22, Electronic and NMR Spectra of Molecules. Section 22.3, UV-vis spectra of electronic transitions. Most UV-vis spectra of molecules are not vibrationally resolved. Why? The first reason is this: an atom does not vibrate, and therefore the UV-vis spectrum of an atom contains sharp spectral lines. A diatomic molecule has one vibrational mode. The UV-vis spectrum of a diatomic molecule may have multiple spectral lines that correspond to the same electronic transition but different vibrational transitions. For example, let's look at a potential energy surface of a diatomic molecule right here. Now let's do one electronic transition. This is a vertical excitation, because the nuclei do not have time to change their positions during a ultra-fast electronic transition that takes place usually within 1 femtosecond. And now if we look at this vertical transition, we can go from this vibrational quantum number 0 to 0, from 0 to 1, from 0 to 2, from 0 to 3, or to 4 to 5. So the same electronic transition is accompanied by many different vibrational transitions. And in this graph, very likely from this 0 to 2 transition has the largest intensity due to the maximum of this vibrational wave function matching with this maximum of this vibrational wave function. But anyway, we see multiple spectral lines just because the electronic transition is accompanied by multiple vibrational transitions. And not only that, the vibrational transition is accompanied by rotational excitations and also rotational de-excitations. Those rotational excitations and de-excitations may broaden the spectral lines. So those are not going to be really sharp lines. A polyatomic molecule may have 3n-6 or 3n-5 vibrational modes, If you have a non-linear molecule, you have 3n-6 vibrational modes. If you have a linear polyatomic molecule, you're going to have 3n-5 vibrational modes. In that case, the electronic transition may be accompanied by many different vibrational excitations, and each vibrational excitation is accompanied by numerous rotational transitions, including rotational excitation of the R branch and rotational de-excitation of the P branch. Therefore, the UV-vis spectra of polyatomic molecules are not vibrationally resolved. Most UV-vis spectra are not vibrationally resolved, and there are several more reasons. Reason 2, each molecule may be in a different chemical environment, especially in a liquid phase or in a solution. Chemical surroundings do affect the energies of the ground electronic state and the excited electronic state, and that's why the change of the energy in the electronic transition can be slightly different depending on the chemical environment. The third reason is this: the line width of each transition is broadened due to the short lifetime of the excited state. This arises from the uncertainty principle for time and energy. Delta E times delta T is greater than 1/2 of H bar. Well, this is just because the time operator and the Hamiltonian operator do not commute. So we can evaluate the commutator of the time operator and the Hamiltonian operator. The Hamiltonian operator is equivalent to this IH bar d over dt operator. So we do this, it turns out this commutator of time and Hamiltonian is equivalent to negative IH bar. This is non-zero. That means time and Hamiltonian do not commute, and within a very small time period we will have a larger uncertainty associated with energy. A short lifetime of a species in the order of 10 to the power negative 14 seconds results in a very large uncertainty of its energy. So you can just use h bar over 2 divided by this time period, and roughly we have a estimate of the uncertainty of the energy, which can be as large as 10 to the power negative 20 joule or 1,000 joule per mole. The last reason is this: we have rotational transitions and accompanied by some centrifugal distortion, because those rotors are not necessarily rigid rotors. The radius of the rotation may change, and also there's coupling between rotations and vibrations. There are also coupling between enharmonic vibrational modes. All those further broaden the UV-vis peaks. Sharp UV-vis peaks are observed only for atoms. Chapter 22: Electronic and NMR Spectra of Molecules. Section 22.4: The Jablonski Diagram of Photochemistry. The Jablonski diagram depicts the 6 major electronic transition processes in photochemistry: absorption, fluorescence, phosphorescence, internal conversion, vibrational relaxation, and intersystem crossing. So now let's examine this Jablonski diagram. We have several electronic states here. S0, that's the ground singlet electronic state. S1 and S2 are also singlet electronic state. This is the first excited. This is the second excited singlet electronic state. We also have this T1 electronic state. And you see a bunch of lines on top of S0. Those are vibrational energy levels. For S1, we also have many vibrational energy levels. So does this S2 and T1. Now let's look at absorption. So you can see absorptions, those up arrows. A molecule may absorb a photon and gets excited to some S1 or S2 excited states. That's absorption. it takes place within one or several femtoseconds. And now once the electronic state is changed to the higher energy level, for example this S1 state, well, it's not going to be very stable. It's possible for this molecule to under electronic de-excitation, so it can jump back from S1 back to S0. This is pretty fast as well, usually nanoseconds. It's called fluorescence. In the fluorescence process, a photon is emitted. And now let's look at some other processes. So again, we can have this electronic excitation from S0 to S1 or even to S2. And now let's look at this wiggle line. This is so-called vibrational relaxation. So it's possible for us to excite this molecule to this S2 excited electronic state and also excited vibrational energy level. For example, over here, this is the vibrational energy level n equals 0, 1, 2, 3. So from here we can do some vibrational relaxation. That means the vibrational energy may decrease. The vibrational quantum number may decrease from 3 to 2 or from 2 to 1, 1 to 0, etc. Where does this energy go? This vibrational energy may be transferred to some surrounding molecules, and this is vibrational relaxation. And also you can go from S1, so for example we excite the molecule from S0 to S1, and then from S1 horizontally you can go through this so-called internal conversion from S1 to S0. In the internal conversion process, the electron spin is conserved, so it's from singlet to singlet, from S1 to S0. But now you can see over here, although it's the S0 ground electronic state, this is actually vibrational excited state, so really high vibrational energy level, and also it can undergo vibrational relaxation. I can't tell, I think this is probably n equals 11 or 12. The vibrational quantum number can decrease from either 11 or 12 to maybe just lower vibrational quantum numbers. Alright, so it explains this wiggle arrow in purple color. It's called internal conversion. And also you can go from S2 to S1. This is also internal conversion, and then followed by this vibrational relaxation. Now let's look at another process that involves the flip of the electron spin. So this is going to be called inter-system crossing. Inter-system crossing over here from the S1 excited state to the T1 excited state. We have to flip the spin of one electron, and then going from here to here. This is actually a spin forbidden process. So usually this is slow from S1 to T1. And then after you go from S1 to T1, well, we can still undergo this vibrational relaxation from higher vibrational energy level to lower vibrational energy level. And from T1 to S0, well, this is also called inter-system crossing, in which the energy is conserved, but the electron spin is flipped. You need to flip the spin of one electron to go from T1 to S0, and from here we can undergo vibrational relaxation all the way to the bottom line. And also from this T1 to S0 we can also go through this phosphorescence process. In the phosphorescence process you go from T1 to S0 directly and emit a photon. And also from T1 to S0, this is actually spin forbidden electronic transition. So phosphorescence is usually much slower than fluorescence. Fluorescence is spin allowed, phosphorescence is spin forbidden. So you can see this time scale is much longer than this time scale. phosphorescence can take much longer to occur just because it's spin forbidden. And again, in both fluorescence and phosphorescence, a photon may be emitted. That takes the energy difference into account. But over here, phosphorescence is much faster than fluorescence. This is also a Jablonski diagram. In this diagram, we have the S0, the ground singlet electronic state, S1, the first excited singlet electronic state, T1, the first triplet electronic state. So if we go from S1 to T1, it's called intersystem crossing. That involves the flip of electron spin. This is spin forbidden, but it can also happen. And all those wiggle arrows, those are vibrational relaxations. And from bottom up, this is absorption. The molecule may absorb a photon and undergo the electronic transition from the S0 ground singlet electronic state to S1 first excited singlet electronic state. And again, we can see some vibrational relaxation, and also from here to here, this is a vertical arrow pointing down. It's called fluorescence, in which a photon is emitted. This is an ultra fast process as well, usually nanoseconds. And then phosphorus, after we excite an electron here, we can go down here. After intersystem crossing, we can go from S1 state to T1 state. In the T1 state, we have many vibrational energy levels. Again, wiggle lines, that means vibrational relaxation. The molecule may lose energy to the surrounding molecules in the form of heat. And then over here, from here to here, it's from T1 to S0. This straight arrow is phosphorescence. This is spin forbidden. That's why from T1 to S0, the phosphorescence takes much longer than fluorescence. Chapter 22, Electronic and AMR Spectra of Molecules. Section 22.5, Nuclear Magnetic Resonance Spectroscopy. Like electrons, protons and neutrons also spin, which may create a nuclear magnetic moment. The nuclear magnetic moment of a nucleus mu can be calculated using this equation. Mu is G sub n, the nuclear G factor, times the charge of an electron, over 2 times the mass of proton, multiplied by the nuclear angular momentum. I is the nuclear angular momentum. The magnitude of I is the square root of I times I plus 1 times h bar. We can also write mu as G sub n times mu sub n over h bar times I. Over here, mu sub n over h bar is equal to E over 2m proton. Mu sub n is called nuclear magneton. Mu sub n is equal to the charge of electron times h bar over 2 times the mass of proton. It's roughly 5 times 10 to the power of negative 27 joule per Tesla. Tesla is the unit of magnetic field strength. 1 Tesla is 1 joule over ampere over meter squared. 1 Tesla is 1 kilogram over second squared over ampere. 1 Tesla is 1 Newton over 1 meter over 1 ampere. We can look at this equation again. This is the equation for the nuclear magnetic moment. So this is equal to G sub n times mu sub n over h bar times I. It can also be written as gamma I. Gamma is G sub n times mu sub n over h bar. Gamma is the magnetogyric ratio. Gamma is Gn mu n over h bar. Gn is the nuclear G factor. Mu sub n is the charge of electron over 2 times the mass of proton times h bar, and then we have h bar on the bottom as well. So h bar cancels. We have this expression for the magnetogyric ratio gamma. Now for a hydrogen atom, its nucleus has a spin quantum number of 1/2. Therefore, I is 1/2. Its nuclear angular momentum is, well, the square root of 3 times h bar over 2. All we need to do is we replace this I with 1/2, and then you have square root of 0.5 multiplied by 1.5. Therefore, you have a square root of 3 over 2 over here, multiplied by h bar. So it's square root of 3 times h bar over 2. That's the nuclear angular momentum for the hydrogen nucleus with only one proton. Hydrogen 2 has a different value over here because hydrogen 2 has a different value of I. Now let's look at the Z component of the nuclear angular momentum for the hydrogen nucleus. I sub Z, the Z component of this quantum number, can be positive 1/2 or negative 1/2. So the Z component for the nuclear spin is 1/2 h bar or negative 1/2 h bar. The value of the G factor for the hydrogen nucleus is 5.6. So we can easily compute the Z component of this nuclear angular momentum. It's just G sub n times mu sub n over h bar times I sub Z. I sub Z is plus minus 1/2. G sub n is 5.6. So we have this expression. Mu sub Z is plus minus 2.8 mu sub n. Mu sub n is the so-called nuclear magneton. Now let's look at a table of different isotopes. We have elements H, boron, carbon, nitrogen, fluorine, silicon, phosphorus. They have different abundance or occurrence percentage in nature. Well, you can see hydrogen 1 is nearly 100%, and we often do carbon-13 AMR, but it's only 1%. That's why it's more difficult to collect the carbon-13 AMR than to collect hydrogen AMR. So you can see the abundance differ by nearly a factor of 90. Alright, this is hydrogen 2. Hydrogen 2 has a very small abundance. We don't usually collect hydrogen 2 MR, although we can, because it does have a non-zero spin number here. Alright, it's just the abundance is so small, and also the G factor is fairly small. Now let's look at the spin numbers. You can see a bunch of spin numbers. Carbon 12 has a 0 spin number. Silicon 28 has a 0 spin number. That's why we cannot collect the NMR spectrum for any carbon 12 species or silicon 28 species. There's just no magnetic moment in the nucleus. For all others, it's possible to get the NMR for all those other isotopes with a non-zero spin number. So when does this spin number become 0? Well, if you have a even number of protons and an even number of neutrons, it's going to be 0. I think in carbon it's 6 and 6, that's why you have 0 here. In silicon, I think it's 14 and 14, both are even numbers, therefore you have 0 here. For hydrogen 2, well, we have an odd number of protons and also an odd number of neutrons, 1 and 1. So we have a non-zero spin number here, and therefore a magnetic moment over here. This is non-zero. And how do we compute this? I showed you an example for hydrogen 1. It's about 2.8 nuclear magneton. I think it's from here. You have this G factor multiplied by this magnetic magneton over h bar, and then times I sub Z. I sub Z is again plus minus 1/2 h bar. Over here it's given to you. So for hydrogen 1, it's just plus minus 1/2 times the G factor, and then this is the nuclear magneton with this value 5 times 10 to the power of negative 27 joule per Tesla. Alright, so we have this table, and this allows us to analyze, whether it's easier to collect the EMR of a certain isotope. The energy of a magnetic moment or a magnetic dipole in a magnetic field is this. This is the energy is equal to negative mu times this magnetic field B naught. Both are vectors, but then we just need to do the dot product of two vectors. We get negative gamma times B0 times I sub z times h bar. And over here, this I sub z is just the quantum number in the z direction. We're going to just assume that we're going to just look at the z direction, all right? By convention, we just look at the z direction. We are assuming the z direction of the nuclear angular momentum is aligned with the external magnetic field B0. Now we calculate the energy levels of this one hydrogen or hydrogen 1 nuclear spin in a magnetic field of 9.4 Tesla. Alright, the energies of the up spin and down spin are given by this. The energy is just over here. I think we see this gamma, which is the magneto-dielectric ratio, G sub n times E h bar over 2m proton. You know, this h bar comes from here, and everything else is that gamma. We can plug in the numbers. We can plug in all the numbers, plus minus 1/2. G sub n is 5.6 for the hydrogen 1 nucleus. We have the charge of the electron right here, 1.6 times 10 to the power of negative 19. H bar is 1.05 times 10 to the power of negative 34. 2 times the mass of the proton. The mass of the proton is 1.67 times 10 to the power of negative 27 kilogram. And then we have this B naught. B naught is 9.40 Tesla. It's given here. This 9.40 is a very strong magnetic field already. Because I used SI units for every single number in here, the final unit should be the SI unit of energy in joule. So we calculate all this. We get plus minus 1.3 times 10 to the power of negative 25 joule. What does that mean? That means, well, if you have a hydrogen 1 nucleus, it can spin up or down in the z direction. And if we align the z direction with the magnetic field, we're going to observe two different energy levels. One is plus 1.3 times 10 to the power of negative 25. One is negative 1.3 times 10 to the power of negative 5 joule. Just because of the influence of this external magnetic field. Alright, the upspin and downspin have two different values. Now let's look at the difference between upspin and downspin. We're going to just use plus 1.3 minus 1.3, so it's just 2 times this number. The difference between the energies of the upspin and downspin is 2.65 times 10 to the power of negative 25 joule. The corresponding frequency of this energy is this. This frequency is just delta E over H. Delta E is this, H is this. We get 4 times 10 to the power of 8 hertz, or 400 megahertz. 400 megahertz. The corresponding wavelength of this electromagnetic radiation is lambda equals c over frequency. The speed of light over frequency, we get 0.75 meters. Alright, this radiation is around the range of radio waves. For comparison, the typical FM radio wave is around 100 megahertz. So it does have higher frequency than FM radio waves, but not too much higher. Well, 400 and 100, they differ by a factor of 4 right here, given this magnetic field of 9.4 Tesla. The frequency and wave number of the electromagnetic radiation of the hydrogen nucleus due to its energy level splitting in the 9.4 Tesla magnetic field are in the range of radio waves, really close to the FM radio wave. The relative populations of the two states, up and down states, at the room temperature are given by the Boltzmann distribution. The Boltzmann distribution is pretty simple. It's e to the power of negative energy difference over kBT. That's it. So if we look at the population of the upspin versus downspin, well, it's just e to the power of this negative energy difference over kBt. This is the Boltzmann distribution. The result is 0.999936. Only because the energy difference is so much smaller than kBt. I think kb is in the order of 10 to the power of negative 23, and t is in the order of 10 to the power of 2 Kelvin. So kBt is at room temperature, it's roughly 4 times 10 to the power of negative 21 joule, and this is 10 to the power of negative 25 joule. So therefore, this exponential term is really close to 0, and therefore the ratio is really close to 1. It's slightly less than 1. From this result, we see the populations of the two energy levels are nearly the same, with a very small difference, 64 parts per million. That's a very small difference. And this difference can be enlarged at lower temperature to intensify the AMR signal. So if we can lower this T, we can have a different ratio, a ratio smaller than this, and then we have different populations. Alright, and that way we can intensify the AMR signals. The excitation and de-excitation cannot cancel completely. When an atom is placed in a magnetic field, the electrons around the nucleus generates a induced magnetic field, and the direction of this induced magnetic field opposes the external magnetic field. Alright, so we have this equation. This is induced magnetic field, and B0 is the external magnetic field. They differ by, if you have B induced over B0, you get negative sigma. Sigma is usually a small number. We see a negative sign, that means the induced field is opposing the external field. Sigma is the shielding constant, and sigma is very often much smaller than 1. The total magnetic field at the nucleus is given by the sum of the external field and the induced field. So we have B0 as the external field. We have negative sigma B0 as the induced magnetic field. If we sum it up, the B total is B0 times 1 minus sigma. Again, this sigma is very small. How small? Sigma is usually 10 to the power of negative 5, or even 10 to the power of negative 6. So sigma is really small. The induced magnetic field is much smaller than the external magnetic field. By the way, I forgot to mention that if you want to further reduce this number, make it much smaller than 1, you can also kind of increase the energy difference here. So one way is you reduce the temperature, or you can increase the energy difference. Either way, you'll get a number smaller than this. The frequency shift for an atom depends linearly on the shielding constant sigma. This makes AMR a sensitive probe around nucleus with a non-zero spin. Well, if you have a zero spin and this nucleus is not going to be affected by the external magnetic field, there's no energy difference, and there's no up or down spin at all. Two major factors responsible for the chemical shift are this. One is electron negativity. The other is the induced magnetic field. In those conjugated systems, or simply just double bonds or triple bonds. First, let's look at electron negativity. So if you have a electron withdrawing group, such as fluorine, or a electron pushing group, such as methyl, bonded to a carbon, well, these two different groups will somehow withdraw or push electrons, either from the carbon or to the carbon, and that will change the value of this shielding constant sigma. And number 2, induced magnetic field in alkenes with a double bond, alkynes with a triple bond, or aromatic rings such as benzene. You have, especially on benzene, you can see there's an electric current on top of the benzene molecule, right? So the 6 pi electrons forming a nearly ring structure. Now let's look at this chemical shift. Chemical shift is dimensionless without a unit. Usually we express delta chemical shift in ppm only because it's small. It's defined relative to a reference compound. You need a reference first. So first, delta is 10 to the power 6, and then over here we have the frequency of the chemical minus the frequency of the reference divided by the frequency of the reference, and this frequency is proportional to this B naught times 1 minus sigma, and this is the reference. It's 1 minus sigma reference. So we have this equations, and when we look at this equations, B naught can cancel, and then on top we have actually sigma reference minus sigma. On the bottom we have 1 minus sigma reference. And again, sigma is usually much less than 1. Sigma is usually 10 to the power of -5 or -6. It's much less than 1. So over here, this 1 minus sigma of the reference is approximately just 1. And therefore, the chemical shift is just 10 to the power of 6 times sigma reference minus sigma ppm. All right, again, the unit is ppm only because sigma is usually small compared to 1. Delta is usually much small compared to 1. Sigma is also much smaller than 1. Sigma is called the shielding constant. It's just how much the nucleus is shielded by the electrons. What kind of reference do we use? If you have taken organic chemistry, you know we use tetramethylsilane, TMS, as the reference for hydrogen AMR, carbon AMR. We can also use this for silicon-29 AMR, all right, because it contains silicon. All right, in theoretical calculations of the NMR spectra, the shielding constants of the hydrogen 1, carbon 13, silicon 29 in the compound of interest should be calculated and compared with the calculated shielding constant of the reference. So we need to do two different calculations, one for the compound of interest, the other for the TMS, tetramethylsilane, and then we need to compare these two to determine the chemical shift that are comparable to the experimental values from the experimental NMR spectra. The same computational method should be used for the calculations of the compound and of the TMS reference for consistency. Now let's look at a couple AMR spectra. One is hydrogen AMR. You can see over here this is 0.0 ppm. It's just TMS, tetramethylsilane. And all other compounds are compared to TMS. All right, they're just compared. The chemical shift is 10 to the power 6 times sigma of this TMS minus the sigma of the compound of interest. Now let's look at a few examples. When we have alkane, I think this shielding constant is very close to TMS, therefore this is close to 0. Now let's look at a more extreme example. Over here we have RCO2H. Alright, this H is partially positively charged. It's very close to a H plus with a partial charge. That means it's less shielded by electrons, right? Surrounding this hydrogen, there's less shielding than TMS, and then we have very different chemical shift. This is between 10 and 12.5, wide range over here. And also it really depends if you have a concentrated solution versus a dilute solution. We need to discuss the hydrogen bonding effect as well. That's why we have a wide range over here. And also whenever you have hydrogen bonding, again, concentrated, you have more hydrogen bonding, diluted, less hydrogen bonding, and then you can see this phenol that contains hydrogen bonding, ROH, may have hydrogen bonding. We have a wide range. Alright, so again, over here this hydrogen is less shielded. You have a really large delta value. You have a large delta value. Okay, this sigma is really small compared to the reference TMS, and then you have a really large delta. This one, this sigma is close to the reference, and then you have a small delta. And also, if you look at aromatic compounds over here, it's around 7. It's also just due to different electron shielding environment, but this time it's nothing to do with electron activity. It has everything to do with the ring of the pi electrons. You have 6 pi electrons it forms nearly a ring structure on top of the plane that contains this benzene molecule. Alright, so you can see, there are two factors. One is electronegativity. You can see if you have just a hydrogen bonded to alkyl group, it's very close to 1, but if it's bonded to iodine versus chlorine versus bromine versus fluorine, you can see the electronegativity goes up, and then over here this hydrogen is less shielded. Just because fluorine withdraws electrons, that's why this hydrogen is less shielded. That's the electronegativity effect. And then if you look at aromatic compounds, if you look at double bonds, we have some other effects there. Now let's look at the carbon AMR. This is carbon 13 AMR because carbon 12 will not give you any signal. Carbon 12 has a zero nuclear magnetic moment. Carbon 13 has a non-zero magnetic moment, and then we can look at some of this. TMS is again used as the reference right here, 0.0, and over here those carbons are really close to the TMS, and therefore the chemical shift is 0.0. Alright, but then if we look at this end, for example, aldehyde, ketones, this carbon is much less shielded by electrons, and this sigma is much smaller than the sigma of the reference TMS, and then you have a very large delta for the carbon. Over here, that's why you have 200 ppm over here. And also, we need to look at a combination of, electronegativity effect, and also the double bond, triple bond effect, the aromatic effect. Chapter 23, Computational Chemistry. Section 23.1, Potential Energy Surfaces. A potential energy surface shows how the potential energy of the molecule changes with the atomic positions. Here, the potential energy of the molecule is defined to be the total energy of the molecule minus the kinetic energy of the nuclei. Accurate potential energy surfaces are useful in the study of chemicals and reactions. The X, Y, Z Cartesian coordinates are rarely used when plotting the potential energy surfaces. Instead, the internal coordinates, such as the interatomic distances, bond angles, and dihedral angles, can better illustrate the relative positions of the atoms, and therefore are typically used in the potential energy surfaces. For example, the potential energy surface of a typical diatomic molecule is shown here. The vertical axis is the potential energy. The horizontal axis is the distance between the two nuclei. And now we have two different potential energy surfaces in green and blue. The green one is assuming the harmonic oscillator model. The blue one is much more realistic. This is Morse potential. And over here we can see the dissociation energy at the line, this dashed line. And we have d sub e, the depth of the potential energy well, d sub 0 as the bond energy. The Morse potential can be written as a mathematical equation. The potential energy is equal to d sub e, the depth of the potential energy well, multiplied by 1 minus e to the power of negative ax squared. So you can see this x is the displacement of the bond length. When x is 0, that means we have equilibrium bond distance, and then we have 1 minus 1 squared, it's 0. The potential energy is 0 when the displacement is 0. What if x is infinity? When x is infinity, we have this part equal to 0, and then the potential energy is equal to d sub e. Again, this is the simplest potential energy surface because we have the potential energy with respect to just one variable. When you have a diatomic molecule, you just need the distance between the two nuclei to specify the relative positions of these two atoms. Now we're looking at a more complex potential energy surface. When we have a nonlinear molecule, there are 3n minus 6 internal coordinates. Because we have 3n different motions, minus 3 translation, minus 3 rotation, and then we have 3n minus 6 internal coordinates. If we have a linear molecule, we have 3n minus 5 internal coordinates because there are 3 translation and only 2 rotation of the molecule. It's often impossible to plot the potential energy surface versus all internal coordinates. For example, if you just have water, 9 atoms, there are 3 internal coordinates. There's OH bond and the second OH bond, and then there's HOH bond angle. And then how can you draw a potential energy surface that depends on all 3 variables? Bond distance 1, bond distance 2, and then bond angle. So we often just plot the potential energy versus only one of the many internal coordinates. We pick the most important one, the one of interest. For example, if we are looking at the rotation of the carbon bond in a butane molecule, we usually just look at the CCCC dihedral angle. So why 4 carbons here? To define a dihedral angle, we need 4 atoms. It's going to be atom 1, atom 2, atom 3 behind this, and then atom 4. Really, atoms 1, 2, 3 can define a plant. Atoms 2, 3, 4 can define a second plant. So the angle between the first plant that contains atoms 1, 2, 3 and the plant that contains atoms 2, 3, 4, that angle is the so-called dihedral angle. So again, if you have a butane molecule, we have 4 carbon atoms. Carbon 1, 2, 3 can define a plant. Carbons 2, 3, 4 can define another plant. The angle between the 2 plants is the CCCC dihedral angle. So now let's look at this potential energy. So right here, I think we have the lowest energy when this dihedral angle is 180. Well, this is simply just because if you look at this methyl group and this methyl group, the one is pointing up, one is pointing down. We avoided the steric hindrance between the 2 methyl group. That's why it has a lowest energy. Now over here at this point, we have the highest potential energy. Look at the positions of these 2 methyl groups. They are much closer to each other, and same here. That's why we have a high potential energy at this 2 point. Now what about this 2 so-called local maxima? Over here you can see there's a smaller steric hindrance between a methyl and hydrogen here, methyl and hydrogen here, smaller, much smaller than between 2 methyl groups, but still you see the 2 local maxima here and here. Now let's look at 2 other values. When you look at these 2 other values, they are both staggered conformation. So there's not much steric hindrance, but still these 2 methyl groups, they are still fairly close to each other. All right, compare with this 2, the dihedral angle is 60 here. Over here this is 300, which is actually 60, and compared to the middle one, you can see these 2 methyl groups are still closer to each other than this in this configuration, in which these 2 methyl groups are pointing to completely opposite directions. So now we looked at this so-called global minimum, and then 2 local minima, and then the global maxima and some local maxima, and then we can connect those and draw the potential energy surface for the rotation of the carbon single bond in the middle. Again, the energy goes up and down, mostly due to the steric hindrance. It's possible to draw a three-dimensional plot of potential energy versus two coordinates. It's a little hard, but it's possible. So for example, when we have water, there are three internal coordinates. If we force the two OH bonds to have the same bond distance, then there are still two internal coordinates. One is the bond distance, the other is bond angle. So again, the vertical axis is the potential energy, and then we have two other axes. One is the bond distance, the other is bond angle, and we're just examining this curvy potential energy plane over here, and somewhere we have the lowest point on the surface, and the lowest point corresponds to the equilibrium bond distance 0.096 nanometer or 0.96 angstrom between the oxygen and the hydrogen atom. And then we have a bond angle roughly 105 degrees. That's the equilibrium bond angle in water. And then you can just change its bond distance, longer or shorter, and it goes up. Also, you can start from here and change the bond angle. You can make the angle wider or narrower. Also, energy goes up. So this is a three-dimensional plot of the potential energy surface for water when we assume the two OH bonds have the same bond distance. Now let's look at another potential energy surface of a triatomic molecule. This time we're looking at ozone. Again, we're going to have to assume the two O bonds have the same length so that we can make a three-dimensional plot. Otherwise, we are looking at a four-dimensional plot. So by having the two oxygen-oxygen bond distance to be equal to each other, we have only two variables. One is the bond distance, one is the bond angle. So we have bond distance right here and bond angle over here from 50 to 130 degrees. The bond distance is from, I think, 1.1 angstrom all the way to 1.5 angstrom. And you can see this potential energy surface here. The vertical axis is energy in atomic units. One atomic unit is 2,600 kilojoule per mole. So actually there's a large difference between here and here. They differ by 0.7 atomic unit, and 0.7 atomic unit is nearly 2,000 kilojoule per mole. Huge energy difference. So this is one of the input files for doing Gaussian calculation. Gaussian is a computational chemistry package. You can use it to do some calculations. So in the first line, I just specify the method I'm using. Scan means to scan the potential energy surface. And a blank line, a comment, another blank line. 0 means the charge of this molecule is 0, and 1 means the spin state is singlet. 1 stands for singlet, 2 for doublet, and 3 for triplet. And I have 3 oxygen atoms, so 1, 2, 3, 3 rows, 3 atoms. The second oxygen has a distance from the first atom. Alright, this means the first atom. The distance is r. The third oxygen also has a distance from the first atom. Also, the distance is r. So I'm just forcing this two to be the same. And then there's a bond angle. I'm using a name theta here, and then r is from 1.1 to 1.5. So really, we are gonna do 40 increments. Each is 0.01 angstrom. So it's gonna be from 1.1 to 1.5. with an increment of 0.01 at a time, and theta is from 50 degrees to 130 degrees. So again, we're doing 40 increments here. Each increment is 2 degrees, so we're gonna do 50 plus 80 degrees. In the end, that's 130. Just to summarize, I'm gonna just compute the energy of ozone when the bond distance is between 1.1 to 1.5, when theta is between 50 to 130. So really, we need to do more than 1600 energy calculations, because when you look at the values of R, we can have 41 possible values. All right, this is the first one, and then 40 different other values. Also, for bond angle, the first bond angle is going to be 50, and then we're going to do 52, 54, 56, 58, etc., all the way to 130. So since we have 41 possible values for R, 41 possible values for theta, we do have 1681 data points on this potential energy surface. So this is why the calculation of the potential energy surface often takes a very long time. From this potential energy surface, we can identify the minimum. I think the minimum is somewhere, the global minimum is somewhere here. The bond angle is probably 115 degrees. It's a little hard for me to visualize the three-dimensional plot, and also the bond distance. Again, the bond distance is hard to kind of, so it's roughly here. I'm going to draw a line here, roughly 1.25. I'm just estimating this, but if you really do the calculation, you will be able to get the energy value for every single data point on this potential energy surface. Chapter 23, Computational Chemistry, Section 23.2, Molecular Mechanics. The most efficient method to construct a potential energy surface of a molecule is via molecular mechanics calculations, in which empirical equations are used to calculate the potential energy of the given molecular structure relative to its equilibrium structure. The equilibrium structure of the molecule and the empirical parameters used in the equations come from experimental measurements or accurate quantum mechanical calculations. The simplest empirical equation that describes the potential energy of a diatomic molecule is this: 1/2 times the force constant K times x squared, where x is R minus RE, the actual bond distance minus the equilibrium bond distance. The force constant K and the equilibrium bond length R sub E come from experimental data or accurate quantum mechanical calculations. A more realistic model should include the third and even fourth power of x to introduce the inharmonicity of the vibration of the molecule. So this is for harmonic oscillators. For a real molecule, we can either include higher order of x, or we can use Morse potential. The simplest empirical equation that describes the potential energy of a triatomic molecule, such as water, is this: we have 1/2 k x1 squared, 1/2 k x2 squared, and 1/2 k sub theta minus theta equilibrium squared. So here, K is the force constant. For water, we're assuming the force constants for both OH bonds are the same, K. X1 is the displacement of the first OH bond. X2 is the displacement of the second OH bond. And over here, the equilibrium bond angle is roughly 105 degrees for water. The theta is the actual bond angle. And somehow we can obtain the value of K sub theta and this K either from experiments or from high-level quantum mechanical calculations. Again, x denotes the displacement of the bond distance, which is the actual bond distance minus the equilibrium bond distance. Theta sub EQ is the equilibrium bond angle. And this equation is used to describe harmonic oscillations, both bond stretching and bond angle changing or bending motion. A more realistic model should include inharmonic corrections and also the coupling between the change in bond distance and the change in bond angles. The downside of the molecular mechanical calculations are: one, we cannot compute the electronic structure. So all those variables are the positions of the atoms. Two, the empirical parameters are needed to do molecular mechanical calculations. And those empirical parameters come from experiments or high-level ab initio or quantum mechanical calculations. And three, molecular mechanical methods are often inaccurate. For example, if you want to describe the resonance energy of a conjugated molecule, it can be hard to do. Chapter 23, Computational Chemistry, Section 23.3, the Hartree-Fock method and the basis sets. The essence of the Hartree-Fock method is to break a many electron Schrodinger equation into many one electron Schrodinger equations. In the one electron equations, the electron-electron repulsion operators are replaced by the mean field one electron operator. One difficulty in the Hartree-Fock calculations is that one must make an initial guess of those one electron wave functions, one for each electron, to start with. Another difficulty resides in solving these one electron Schrodinger equations. To resolve these issues, it is common to parameterize some Gaussian functions and then use the linear combinations of these pre-parameterized Gaussian functions to describe the waves of the electrons in the atoms and in the molecules. The set of such pre-parameterized Gaussian functions is called the basis set. The Hartree-Fock method is then simplified to the optimization of the coefficients of these Gaussian functions and the coefficients in front of the linear combinations of those Gaussian functions. For example, in the Hartree-Fock energy calculation of the H3 plus molecule, the wave function of the hydrogen y-s orbital can be expressed as a combination of three Gaussian functions. So over here we have 1, 2, 3 Gaussian functions, and this is called STO3G basis set. STO stands for Slater type orbital. 3G stands for 3 Gaussian. So you can see there are 3 coefficients in front of the Gaussian functions, and also you can see those exponential parameters. All those numbers are predetermined before the calculation is conducted. In the STO3G basis set for the hydrogen atom, the wave function of the y-s orbital of each hydrogen is expressed as a combination of 3 Gaussian functions. So you can see e to the power of negative 3 r squared, e to the power of negative 0.6 r squared, e to the power of negative 0.17 r squared. So these 3 Gaussian functions have different distributions. Over here we have negative 3.4, therefore this Gaussian function is very tight with a narrow distribution. And here this Gaussian function has a wider distribution. And then we put some coefficients in front of those Gaussian functions and pre-optimize those coefficients as well. Now let's look at the shape of the combination of these 3 Gaussian functions. It looks like this. It's still a bell shape, but it looks awfully similar to e to the power of negative r, the exact wave function in the hydrogen atom. Let's compare these 2 shapes. We have the linear combination of 3 Gaussian functions here as the blue curve, and the red curve is e to the power of negative r, which is the exact wave function in the hydrogen atom. In the STO3G basis set, the wave function of the y-s electron of the hydrogen atom is expressed as a linear combination of three Gaussian functions, denoted by 3g. The exact expression is e to the power of negative r. So why do we need to use those Gaussian functions, not directly the exponential functions, to describe the electron waves? Well, the main reason is this. When we calculate the electron-electron repulsion using a computer, it's awfully faster to use Gaussian functions instead of exponential functions. When more Gaussian functions are used, the accuracy is further improved. So right now we're comparing this original STO e to the power of negative r, the red curve, so it's somewhere here, with STO 1g, this is just one Gaussian function, thus 1g. STO 3g, this is STO 3g, still look like a bell shape. And then STO 5g. So STO 5g, it's very difficult to see STO 5g because STO 5g almost matches with the original e to the power of negative r exactly. What if we use more Gaussian functions? Well, again, we'll get better and better accuracy, using more and more Gaussian functions to match with the exact exponential solution. But the downside is we will have to use more computational resource to conduct such a calculation. How do we determine the molecular orbital coefficients when we calculate the energy of a molecule? Well, in this H3 plus molecule, we use as example here, there are 3 MOs because we start with 3 AOs, 1 AO from each hydrogen. And the 3 MOs are denoted by psi of MO1, psi of MO2, and psi of MO3. They're all linear combinations of the 1s atomic orbitals of the 3 hydrogen atoms. The essence of the Hartree-Fock calculation is to optimize the molecular orbital coefficients. So those C's, C1J, C2J, C3J. So in this equation, J is from 1 to 3 because we have 3 1s atomic orbitals centered on these 3 hydrogen atoms. Therefore, we have C11, C12, C13 in this equation. We have C21, C22, C23 in this equation. C31, C32, C33 in the third equation. So really, in the end, we actually use linear algebra to solve these equations to optimize those molecular orbital coefficients, the values of those C's. C sub ij is the molecular orbital coefficient in the J's equation, and this I is in front of in the ith equation, and this J is the label for the 1s orbital here. The total wave function of the 2 electrons in the H3 plus molecule may be expressed as a 2x2 determinant. So since we have 2 electrons, we need to make sure this wave function is anti-symmetric upon the exchange of the 2 electrons. Therefore, we use a determinant here. Assuming psi 1 and psi 2 are both normalized, we need to have this 1 over square root of 2 factorial here because a 2x2 determinant contains 2 factorial terms. So this is just to normalize the total wave function. And then we expand this determinants. We get psi 1 of 1 times psi 2 of 2 minus psi 1 of 2 times psi 2 of 1. So psi 1 is going to be the first MO with alpha spin. And psi 2 is going to be also the first MO with beta spin. This is a typo over here. It should be psi of 2. Again, psi of MO1 is the lowest energy MO. All 3 1s atomic orbitals are in phase. And then we can compute the child energy of psi 1, 2. And we can minimize this psi 1, 2, which is going to give us these MO coefficients. The larger the basis set we use in the Hartree-Fock calculation, the more flexible and accurate the wave functions can be. The 631G basis set is one of the larger basis sets than STO3G. So over here, 3G means 3 Gaussian functions, and 6-31G, what does that mean? Well, 6 denotes a linear combination of 6 Gaussian functions used to describe every core electron. 3-1 denotes a linear combination of 2 linear combinations of 3 and 1 Gaussian functions for each valence electron. They are separated by this hyphen here. So core electrons hyphen valence electrons. So look at here, it's a linear combination of 2 linear combinations. So this 3 means a linear combination of 3 Gaussian functions, and this 1 means a linear combination of only 1 Gaussian function. And then we have a linear combination of these 2 linear combinations. And we have a coefficient for each of these 2 linear combinations that can be optimized in the calculation. Again, G stands for Gaussian, and this hyphen separates the core electrons from the valence electrons. For the hydrogen atom, we do not have any core electrons, so it's going to be just 3-1 for the valence electron in the hydrogen atom. Alright, over here you see a linear combination of 3 Gaussian functions. Over here you see just 1 Gaussian function here. The values of A and B are optimized in the Hartree-Fock calculation, including the predetermined parameters in the function. We have this. Again, A and B will be optimized in the actual Hartree-Fock calculation, but all other parameters, such as the coefficients in front of the Gaussian functions, those D's, and also the exponential parameters, those zetas, they are predetermined. So for example, we have a linear combination of 3 Gaussian functions here, 0.3 times e to the power negative 18 r squared, very narrow distribution here, and then e to the power negative 3 r squared, wider distribution, negative 0.6 r squared, even narrower, and over here really narrow Gaussian distribution here. So compared with the STO3G basis function, which contains only 3 Gaussian functions, the 631G basis function is more flexible and can be used to describe the wave of the electrons more accurately. Well, not only we have more Gaussian functions, but also remember this: the values of A and B can be optimized in the calculation, while in this STO3G all parameters are predetermined. So when you have more flexibility, you always can describe the electron waves more accurately. Again, the larger the basis set is used in the Hartree-Fock calculation, then the more flexible and accurate the wave functions of the electrons can be achieved. And also, if you have more parameters to be optimized in the calculation, and then we have more flexibility and more accurate. In the 6-31G basis set for the lithium atom, we have both core electrons and valence electrons. They are treated differently. For the 1s core electrons, we use a linear combination of 6 Gaussian functions. The 6 coefficients are predetermined. Over here, the 6 coefficients are here. And zeta, we have 6 different zeta values. They are here. And you can see this one is 642. So it's 0.6 times 10 to the power 3, so it's really 642. So if you have a function that is e to the power of negative 642 r squared, this function is extremely narrow. And over here we have a wider distribution. All right. So we use the linear combination of the 6 Gaussian functions with this coefficients and corresponding exponential parameters to describe the core electron in lithium. Again, when you have a zeta of 642, this is very tight. But if you have a zeta of 0.6, it's pretty loose. We're just using a combination of tighter Gaussian functions and looser Gaussian functions to describe, the electron wave more accurately. Again, the larger the basis set is used in the Hartree-Fock calculation, the more flexible and more accurate we can achieve. in the 6-31G basis set for the lithium atom. Again, the core electrons and the valence electrons are treated differently. We use a linear combination of 6 Gaussian functions for the core electrons. Now for the valence electrons, we use 3-1G. That means a linear combination of 3 Gaussian functions and also a linear combination of 1 Gaussian function here. And overall, it's a linear combination of 2 different linear combinations, alright? Because the values of A and B will be optimized in the Hartree-Fock calculations. This is the 2s atomic orbital. We know there should be a spherical nodal surface, so we need to include this as a part of the wave function r minus a. A is just the radius of the spherical nodal surface. This can also be pre-optimized. This can also be computed. Now let's look at 2px, 2py, 2pz orbitals. Each of them has a planar nodal surface, so that's why you can see we're going to have this side of 2px over x, 2py over y, 2pz over z as a linear combination of 2 linear combinations. The first linear combination, we have 3 Gaussian functions. The second one, we have only 1 Gaussian function. And then we have those coefficients and exponential parameters. Alright, so the zeta values are here for this combination, and the zeta value from this zeta prime is this. What about the coefficients in front of the Gaussian functions? For the 2s orbital, we use these 3 coefficients. For the 2p orbitals, we use these 3 coefficients. Alright, for this, the first linear combination of 3 Gaussian functions. For the second linear combination of only 1 Gaussian function, we use this coefficient for the s orbital, this coefficient for the p orbital. So these two actually are the same. It's just this is just 1, this is just 1. We can use a larger basis set to describe the electron wave even more accurately. For example, 6-311G. Well, in this case, we'll just use 3 linear combinations for each valence electron. The first linear combination contains 3 Gaussian functions. The second one, only 1 Gaussian, and then another Gaussian. So this is how we make it more flexible. And then we can look up those coefficients. We can look up those zeta values from the database. The values of A, B, and C should be optimized in the actual Hartree-Fock calculations. This 6-311 plus GD basis set is even larger than this one. So this plus means we're going to employ very, very loose diffuse functions for non-hydrogen atoms. Alright, they're called diffuse functions. They have a really wide distribution in space. Diffuse functions are often used for anions or molecules with loosely bound electrons. And D means we're going to use D-type polarization functions on second row atoms like carbon, nitrogen, oxygen. The inclusion of those polarization functions allow for more flexibility. For example, if we have like some bonding orbitals, we know the bonding orbitals are supposed to be linear combination of atomic orbitals, but there's some distortion to those atomic orbitals. For example, when a pi bond is formed between 2p orbitals centered on 2 carbon atoms, these 2p orbitals are slightly distorted in the direction of the molecular axis to have a better overlap. Now this distortion can be better described with the addition of D-type functions. So they look like D orbitals in the basis set. So this 3-311 plus GD basis set is sometimes also written as 6-311 plus G star. It's just by convention. This star means just D polarization functions on 9 hydrogen atoms. So I mentioned that if you have plus, that means diffuse functions on non-hydrogen atoms. for loosely bound electrons. And I mentioned this D is the D-type polarization functions on non-hydrogen atoms to better describe the distortion of the atomic orbitals when they form bonds. But what about hydrogen atoms? Well, we can use an even larger basis set. This is 6-311++ GDP. So now we see three pluses. That means not only we have diffuse functions on non-hydrogen atoms, but also we have diffuse functions on hydrogen atoms. Alright, diffuse functions have really wide distribution. They're used to describe loosely bound electrons. For example, if you have anions, if you have excited states in which electrons are loosely bound, and then we need to use diffuse functions. Now here, D and P over here, that means D-type functions for non-hydrogen elements like carbon, nitrogen, oxygen, and fluorine. And then P-type functions for hydrogen. We know in a hydrogen atom, supposedly this electron should be in the 1s orbital, but by adding those P-type functions, we can better describe the distortion, when this 1s orbital on hydrogen atom forms a bond. So even in a hydrogen 2 molecule, the electrons are not really like two spheres on the two hydrogen nuclei. There is some distortion that can be better described by including some P-type functions. This 6-311++ GDP base set is sometimes written as 6-311++ G star star. 2 stars means D-type polarization functions on like non-hydrogen atoms, and the second star means P-type functions on hydrogen. We can even add more polarization functions. So we just changed this dp to 3d and 2p. So we have three sets of D-type functions on carbon, oxygen, nitrogen, and two sets of P functions on hydrogen atoms. Again, when we have a larger number of Gaussian functions, we can describe the electron wave more realistically, more accurately. We'll get better trial wave function and lower trial energy. The more flexible the trial wave functions is, the lower the trial energy we can achieve. And the lower the trial energy, the closer it is to the exact energy in the Hartree-Fock calculation. In general, using larger basis sets often results in more accurate calculation, but it does require more computing resources. So we have to balance the accuracy and efficiency. There are numerous types of basis sets that vary on the number of Gaussian functions, the coefficients, the exponential parameters. And they also vary in the number of polarization functions, diffuse functions, and their parameters. So how many basis sets are there? I think there are at least several hundred different kind of basis sets. And you can find the most commonly used basis sets in this website. You can just Google basis set exchange and you can find this website. Chapter 23, Computational Chemistry. Section 23.4, Semi-empirical methods. Semi-empirical methods are similar to the Hartree-Fock method, but semi-empirical methods are often much faster. There are three reasons. Reason 1, in semi-empirical calculations, only the minimal basis sets are typically used. In the Hartree-Fock calculations, larger basis sets are often used for better accuracy. Reason 2, in semi-empirical calculations, most two-electron repulsion integrals are simply neglected or estimated without doing the actual calculations. Reason 3, the semi-empirical method uses some predetermined parameters to make approximation of many integrals in the energy calculation. Some of these parameters come from experimental measurements. Others are optimized with a training set of training compounds. Therefore, the performance of the semi-empirical methods are often very accurate for those training compounds or for some other chemicals with similar structures to those training compounds. Unfortunately, semi-empirical methods may perform really poorly for molecules that do not resemble any of those training compounds. Semi-empirical methods are faster than the Hartree-Fock method, often much faster, and sometimes semi-empirical methods are even more accurate than the Hartree-Fock method, especially for chemicals with similar structures as those training compounds. However, the downside of using the semi-empirical methods is this: it's hard to improve the accuracy of semi-empirical calculations systematically. We can perhaps include more empirical parameters for enhanced flexibility, or maybe we can include more types of training compounds in the training set during the process of parametrization. Chapter 23, Computational Chemistry, Section 23.5, Post-Hartree-Fock Methods. In Hartree-Fock calculations, each electron is assumed to occupy one specific molecular orbital described by a one-electron function. These one-electron functions are used to construct a n by n determinant as the trial function for the n-electron system. This treatment somewhat limits the flexibility in constructing the total wave function of all these electrons. Therefore, the Hartree-Fock energy is always higher than the exact energy, even when an infinite number of basis functions are used in the Hartree-Fock calculation. And the difference between the lowest possible Hartree-Fock energy and the exact energy of the system is called correlation energy. In post-Hartree-Fock calculations, there are three different ways to recover the correlation energy. One is to include some empirical functions to compute or estimate the correlation energy and exchange energy at the same time, such as the density functional theory. Another way is to include multiple determinants that allow for more flexibility in describing the electron wave, such as multi-configurational self-consistent field method, the configuration interaction theory. For example, CISD with single and double excitations. That means we include some determinants in which electrons are placed in antibonding orbitals as well. And also there's a so-called coupled cluster theory. For example, a very accurate coupled cluster singles, doubles, and a ternary triples method is often used to get accurate energy of a molecule. Another strategy is to apply the so-called perturbation theory, which introduces perturbation into the Hartree-Fock calculation, such as the molar-placid perturbation theory. For example, the so-called MP2 method at the second level of perturbation. Or if we need more accurate result, we can use MP4 method at the fourth level of perturbation. Over here we provide a chart that compares the accuracy and the speed of various computing schemes. The horizontal axis is computer time, the vertical axis is accuracy. So you can see molecular mechanics, well, it's fast, but it's less accurate, followed by semi-empirical and Hartree-Fock. And then we have some post-Hartree-Fock methods: density functional theory, perturbation theory, such as MP2, MP4, and then multi-configurational self-consistent method, configuration interaction, coupled cluster. In this purple box, we have three methods that all involve inclusion of multiple determinants. So you can see in general, the more accurate result you want, the more computer time you need to invest. Most of the time we use this DFT methods, density functional theory methods, to balance the accuracy and efficiency. Chapter 23, Computational Chemistry, Section 23.6, Hybrid methods. Hybrid methods are often used to balance the efficiency and accuracy of the calculations. For example, in the study of the drug-enzyme interaction, we can use the more accurate post-Hartree-Fock methods to calculate the reactive region of the interaction, a very small region. And we can use the semi-empirical methods to calculate the supporting structure of the enzyme, a larger region. And we can then use the molecular mechanics methods to model the solvent effect. So this is just a diagram over here. If we have a drug molecule interacting with enzyme, for example in water, we can use molecular mechanics to model the solvent effects from water and perhaps some ions in water as well. And we can use semi-empirical method to compute the entire enzyme. Well, because semi-empirical method is much faster than Hartree-Fock or post-Hartree-Fock method. And finally, we're just focused on the reactive region, where the drug molecule interacts with only a small part of the enzyme. So in this small region, we can use the post-Hartree-Fock method to get more accurate result. In total, the energy of this entire system is going to be the molecular mechanics energy of the entire system, and then plus two corrections. The first correction is this: we're going to use the semi-empirical method to calculate the energy of this region, this medium region. And we're going to use molecular mechanics to calculate the same medium region. And we take the difference. So this is semi-empirical minus molecular mechanics for the medium region. This is the first correction. And then we're going to include a second correction. Over here, for the small region, this reactive region, well, we'll do post-Hartree-Fock calculation for this region and use semi-empirical method also for this region. And we take the difference to get the second correction. So again, the total energy of the entire system is the molecular mechanics energy of the entire system plus two corrections. The first correction is semi-empirical minus molecular mechanics for the medium region. And then the second correction is this: the post-Hartree-Fock energy of the small region minus the semi-empirical energy of the small region. And this is how we balance the accuracy and efficiency using a hybrid method.